online for you all through the day. I also have with me my colleague Shivani Pethe.
Hello, everyone.
And we have our in charge of the outreach program here, the academic in charge, Dr. Surud More as well.
Hello, everyone. Hi.
Yeah. So as we know that we are still kind of restricted by the rules of being safe from COVID-19, we have to therefore go online and get you a lot of content for the whole day, which will kind of excite you and inspire you to be with science and to connect with astronomy and our astronomers. So we'll take this as a positive advantage because with this facility of online, we are able to reach all corners of the country, and we are hoping that all of you are joining from various places and feel welcome here, feel free to chat in the YouTube box here, or if you're watching on Facebook or Twitter, please feel free to use the comments and chat boxes around. Please feel at home, because that is how we welcome everybody on the regular science days, in-person science days at IUCAA. We throw open our gates and everybody walks in, goes around the campus, looks around, talks to people, they view posters, see videos, listen to talks, see exhibits, and enjoy the complete day here. So that's what we've kind of have lined up here. But to start the proceedings, let us have a welcome address from our director, Professor Somak Raichaudhuri.
Good morning and welcome to the National Science Day celebrations at the Inter-University Center for Astronomy and Astrophysics, Pune, IUCAA. We've been doing this National Science Day on February 28th for over 25 years now. And every year we celebrate science, we celebrate Good morning. Good morning. Good morning and welcome to the National Science Day celebrations at the Inter-University Center for Astronomy and Astrophysics, Pune, IUCAA. We've been doing this National Science Day on February 28th for over 25 years now. And every year we celebrate science, we celebrate the first research that led to a Nobel Prize for an Indian. C.V. Raman's Raman effect on this particular day. And what we do is remember the contribution scientists make to the nation. We also are this year celebrating the 75 years of our independence, and in that context also remembering how science has played an important role in building our nation. Actually, we should celebrate Science Day every day of the year. But it is good to have a day in which we come together and look at how we can inculcate scientific temper and behavior amongst students, young people, the general public, everybody, all of us. It is very apt that we are celebrating this day here because IUCAA was one of the first scientific research institutions in India to start this event on a very large scale, particularly involving young people and their teachers. And we have an unbroken tradition now of celebrating through hands-on activities, through informative talks, through events, through activities that make it fun for the general public and also for young people. Of course, the last 2 years have been very challenging for us. In 2020, we had a National Science Day celebrations in which we welcomed almost 16,000 people to our campus and in a single day. And then, of course, we had to go online. And this year, I'm sorry to say, we are still online, but we have, I believe, made some very interesting ways of bringing these events to you online through various means, and I hope you will enjoy it. The national theme for this year is an integrated approach to science and technology for the sustainable future. And that, of course, has been one of the main drivers of celebration of Science Day in IUCAA, because we look at how we can sustainably encourage young people to keep science as a focus in their lives all through their career. We believe in inspiring youngsters, and this is why a large part of our celebrations focus on school students and the school environment. But we also believe that we need to bring the science to the general public. IUCAA is involved in some of the biggest projects the country has gotten into, and this is very relevant now, going into the fourth quarter of our first century as an independent country. We are now leading many international science projects along with other countries, some to be built in India, like LIGO, some to be built abroad, like the Square Kilometre Array and the 30-meter telescope. And IUCAA serves as the gateway for these projects to the very large university and higher education sector of the country. This year, we've also been granted by the International Astronomical Union the office of the astronomy education for high schools, so that we will develop science material for high school students all over the world. And so this brings us together with our core activities for science outreach. We are engaged in a lot of the missions that the Indian Space Research Organization, ISRO, is involved in bringing science to space. Later this year, Aditya, India's Sun mission, will fly with a camera built here in IUCAA. And this message we need to give to the young people of the country is that India is now a leader in science in the global scenario, and becoming a scientist, doing science at every level through technology, through core scientific activities, even writing about science and reporting science. Everything becomes very central in our lives now. We are challenging almost every single country in the world in our excellence in science. And the National Science Day thus provides a way of celebrating that and sending this message to everybody that this is the year of science. We are waiting for everybody in the country, particularly the younger people, to come into the effort that we have now in leading the world in science. Thank you for joining us, and I hope you enjoy the rest of the day with us.
तो इसके साथ हम आप सबका स्वागत करते हैं आयुका यानी अंतर महाविद्यापीठीय केंद्र खगोल शास्त्र और खगोल भौतिकी इसके राष्ट्रीय विज्ञान दिवस के कार्यक्रमों का आप सब हमारे यहाँ पर आए हैं, इसके लिए बहुत बहुत धन्यवाद। और अभी आपने अंग्रेजी में सुना, हमारे निदेशक प्रोफेसर सोमक राय चौधरी आप सबको बता रहे थे कि आयुका की क्या क्या गतिविधियां हैं और किस तरह से कई दशकों से आयुका विज्ञान प्रसार के काम करता आ रहा है। विज्ञान ये एक बस रिसर्च का सब्जेक्ट नहीं है, ये हमारे जनजीवन में आता है और हमारे रोजमर्रा के जीवन में हमें बहुत सारी वैज्ञानिक चीजों का इस्तेमाल करना पड़ता है। आजकल हम इसके आदी हो गए हैं, इसलिए हमें ये ज्यादा नजर नहीं आता है और इसके पीछे का विज्ञान भी ज्यादा समझने की जरूरत नहीं होती है। लेकिन वैज्ञानिक दृष्टिकोण एक बहुत ही महत्वपूर्ण एटीट्यूड है जो कि सब में होना चाहिए, और इसी को सबके समक्ष लाने के लिए हम आज का एक खास दिन हम मनाते हैं जो है राष्ट्रीय विज्ञान दिवस। राष्ट्रीय विज्ञान दिवस को 21 अवसर पर मनाया जाता है। तो आपको पता होगा कि भारत के पहले नोबेल पारितोषिक विजेता विज्ञान के थे प्रोफेसर CV रमन। तो आज के दिन 28 फरवरी को उन्होंने अपना जो शोध पत्र है रमन इफेक्ट के लिए वो बाहर निकाला था, वो पब्लिश हुआ था। इस वजह से हम इस दिन को मनाते हैं। तो हालांकि राष्ट्रीय विज्ञान दिन तो कल है, 28 फरवरी को है, लेकिन आज 27 फरवरी जो कि ये संडे भी है और आप सब ध्यान से और समय देकर ये कार्यक्रम देख सकते हैं, इसलिए हमने आज काफी सारे कार्यक्रमों का आयोजन हमारे इस लाइव यूट्यूब पर किया हुआ है। तो आप जरूर देखिए और जल्द ही हम आपको और थोड़ी जानकारी इसके बारे में बताएंगे, शेड्यूल के बारे में। लेकिन सबसे पहले ये जो स्वागत समारोह है इसमें मैं रिक्वेस्ट दरखास्त करूंगा सूरज मौर्य जी को कि मराठी हमारे जो दर्शक हैं उनसे भी थोड़ा उनका भी थोड़ा स्वागत किया जाए। सूरज जी।
नमस्कार मित्रांनो, आज आपण पुण्यातल्या आयुकामध्ये राष्ट्रीय विज्ञान दिवस म्हणजेच नॅशनल सायन्स डे साजरा करणार आहोत। 28 फेब्रुवारी 1930 रोजी सर CV रमन यांना भौतिकशास्त्र म्हणजेच फिजिक्स मधले नोबेल पारितोषिक मिळाले होते रमन इफेक्टसाठी। त्यामुळे त्यांच्या आणि इतर शास्त्रज्ञांनी केलेल्या योगदानाला लक्षात ठेवण्यासाठी आपण हा दिवस साजरा करतो। आयुकामध्ये विज्ञान दिनाचा कार्यक्रम अनेक वर्षांपासून मोठ्या प्रमाणावर सुरू आहे। आमच्या इथे सर्व लोकांसाठी आणि खास करून तरुणांसाठी मनोरंजक कार्यक्रम, शास्त्रज्ञांबरोबर संवाद, प्रत्यक्ष प्रयोग अशा अनेक प्रकारे विज्ञान दिन साजरा करण्याची अखंड परंपरा आहे। मागच्या वर्षी आपण हा दिवस प्रत्यक्ष भेटून नव्हे तर इंटरनेटद्वारा ऑनलाईन साजरा केला होता। या वर्षी देखील असंच काहीतरी आहे, मात्र आपल्या सर्वांसाठी आम्ही काहीतरी नवीन तयारी केलेली आहे जेणेकरून आपल्याला आयुकात असल्याचाच भास होईल, जसं तुम्ही दरवर्षी येता इथे। सध्या आयुका अनेक आंतरराष्ट्रीय विज्ञान प्रकल्पांचे नेतृत्व करत आहे। काही लायगो इंडिया सारखे प्रकल्प आहेत जे भारतामध्ये उभारले जात आहेत, तर काही परदेशात जसं स्क्वेअर किलोमीटर अरे आणि 30 मीटर टेलिस्कोप। भारतातील विद्यापीठ आणि उच्च शिक्षण क्षेत्रातील संस्थांसाठी आयुका या मोठ्या प्रकल्पांसाठी प्रवेशद्वार म्हणून काम करते। यावर्षी आम्हाला हायस्कूल शिक्षणासाठी IAU कार्यालयाकडनं इंटरनॅशनल ॲस्ट्रॉनॉमिकल युनियन कडनं एका नवीन सेंटरसाठी मान्यता मिळाली आहे। जेणेकरून आम्ही जगभरातील हायस्कूलच्या विद्यार्थ्यांसाठी विज्ञान साहित्य विकसित करणार आहोत. विज्ञानाला अवकाशात आणण्यासाठी इस्रोच्या अनेक मोहिमांमध्येही आमचा सहभाग आहे. यावर्षी इस्रोचे आदित्य विज्ञान मिशन IUCAA येथे तयार केलेल्या कॅमेरासह उड्डाण करणार आहे. भारत आता जागतिक परिस्थितीत विज्ञान क्षेत्रात पुढे आहे हा संदेश तरुणांपर्यंत पोहोचायला हवा. याकरिता आपला पाठिंबा आणि सहयोग आमच्यासाठी खूप महत्वाचा ठरेल. आपल्याला आजचा जो कार्यक्रम आहे तो आवडेल अशी मी आशा करतो आणि आमच्या कार्यक्रमात सामील झाल्याबद्दल धन्यवाद. समीर.
धन्यवाद सुरुद. आणि अशा प्रकारे आजचा कार्यक्रम आपला सुरू झालेला आहे. And we will also tell you the schedule for which we are waiting here. And the events actually will start at 10, but we thought we'll just introduce you to what all is there in store for you today. And with that, let me share my screen and show you the schedule for today. So this is what you will be seeing in this particular live stream that you have joined here on YouTube, and we will be basically having a lot of talks which are specially designed by students and researchers at IUCAA. So these all are being live streamed at the YouTube channel, but of course you can also see us on various other social media platforms like Facebook and Twitter. So we'll begin at 9:30, which is coming up very soon, with we'll begin at 10 o'clock with the first talk, which is about nebulas. Then we'll go on to galaxies. आकाश गंगाओं के केंद्र में जो खगोलीय दैत्य हैं उनके बारे में कुछ जानेंगे. So these will be talks specially made. This will be a talk specially made in Hindi for our Hindi audience. We'll have talks on multi-wavelength astronomy from 11 o'clock. Then we'll have a special talk on science and its role in our latest technology, its penetration into daily life. So fiber optics is kind of an unsung hero, which we do not know much about, but it celebrates, but this talk celebrates its invention, which is by an Indian scientist. And we also come to know how integrating technology into our life has led to the development of our society. So we'll hear about that. Then we'll have a special talk about how astrophysicists create a view of the universe, which probably cannot be seen directly, but can be simulated through the data that they receive. We'll also have some special talks about things closer by. 12:30, we have a talk about our next space observatory, which is going up in space, the Aditya L1 mission, which will study the sun. We'll also have our associate from IISER Kolkata speaking about space weather, which is very directly related to sun and its observations. So that will be there. And then we come to the special walkthrough. तो आप सबको मैं आज बताना चाहूँगा कि इसके अलावा इन कार्यक्रमों के अलावा भी काफ़ी दूसरे चीज़ें हैं जो आप हमारी वेबसाइट पर देख सकते हैं. मैं जल्द ही आपको उस वेबसाइट की एक झलक भी दिखाऊंगा. So our website also has a lot of other content to offer to you, including this special walkthrough. Now at 1:30 we will take you through this walkthrough by ourselves, but of course the website is always there and you can go into this 3D immersive environment with which you can take a tour of IUCAA just like any other regular year when you would be visiting us. We have the most popular event after that at 2 p.m. We have Professor Jayan Narlikar, Professor Mangala Narlikar, Professor Somak Rai Chaudhary, and other IUCAA scientists joining you live to answer questions which so many of you have sent to us over the last week, and we'll be selecting a few of them and they will get answered during this session. From 3 o'clock onwards, we have 3 more special talks. Can we see the ends of the universe? And this is about the largest telescopes that are being built to achieve this goal. Then we have quantum sensing using atomic clocks, about these special and precision things that we require while doing science. We also have a highlight conversation about the Square Kilometer Array, which is going to be the largest radio telescope in the world. And two scientists who are actually working on it would be having a conversation amongst them about the journey that has taken place for bringing it from conception to construction. But that will not be the least. We also have afterwards at 6 p.m. our one of the highlights of the day, which is a talk about the James Webb Space Telescope, which has been in the news, and of course it's one of the most anticipated projects of the recent times. The space telescope is right now up there in space, and it is kind of getting ready to start observing and giving us all those new secrets, unrevealing those new secrets. Okay, so we will have Dr. Swara Ravindranath, who is actually an instrument scientist on the JWST project, talking to you live from Baltimore in the United States and telling you about her experience about the design and actual implementation of this huge project by NASA. Following that, we will have at 7 p.m. a Skywatch program in which we'll show you the planetarium views right there on your screen. And we will also have a special telescope trained at special objects in the sky, which you may not be able to see every day, but these objects will be shown to you via this YouTube channel. And on your screen, you'll be able to enjoy the night sky show, just like you would by being in the IUCAA campus. So we've tried to give you all these kind of a feel of being at IUCAA and being together with us. We also feel great about you all joining us here. Please note the website, and it's of course also being advertised at various places. You can also see it in the description. So it's a simple website, and if you click it, we get to the website. Let me just stop sharing and get to the other screen. Then so we also want to share with you this particular website, which you will find as a resource, and you should of course visit the welcome page where everything is mentioned. Our welcome address is there, and below, if you scroll below, you will find these 4 big sections which take you to several of the important aspects of today's program. So I will particularly request you to go to the poster exhibits, which of course you can also find in the menu here. So if you go to the virtual poster exhibition, the research being done at IUCAA has been put up here under various headings, and you can see careers in astronomy, gravitational waves, stellar physics, quantum technologies, instrumentation, mega sciences, and many such topics which are covered under these posters. You can also ask questions to the people presenting these posters through a form which is on the same page. Then another important aspect, which is only there on the website, is what I want to draw your attention to. So through this, you can actually visit our campus in virtual reality. So if you have a phone like this in your hand, you can click, you can go to this page. Okay, there are some instructions, please read them before going on. And then you just click here, and it will take you to the environment, which will allow you to basically roam around IUCAA after you click this button. So I'm not going to show you the exact, I'm not going to show you what happens, because I think you should yourself experience that and not give out the suspense. You will also be able to not just visit the main IUCAA campus, but also we have the IUCAA Giravli Observatory, which is a major observatory in India, situated close to Pune. And you'll be able to go inside, view around things, and also get a lot of information. So these are 2 highlights of our website that I would like you to keep in mind. Of course, do join us for all the other events which will come up. So the schedule is there. We also have all the posters for you to look at if you just want to see the things in brief. and the schedule is given on the website. So that is a short introduction to the various things lined up online here on this stream on various channels and also on our website. So don't forget to visit the website. Please give yourself a chance to go around the whole campus and the IUCAA observatory and look around. तो आप सबसे निवेदन है कि इस वेबसाइट का भी जरूर फायदा उठाएं। आप वहाँ विजिट कीजिए, वेबसाइट के लिंक पे जाइए, डिस्क्रिप्शन में आपको ये वेबसाइट की लिंक मिल जाएगी। आप उन चित्रों पर क्लिक कीजिए और आपको एक आभासी टूर मिलेगा। आप अंदर जा सकते हैं IUCAA के और खुद किसी भी वक्त आप मतलब समय का कोई आप ये मत रखिए, रिस्ट्रिक्शन लिमिटेशन मत रखिए। आप अंदर जाइए, चारों तरफ घूमिए, उस एरोस पे क्लिक कीजिए, अलग अलग दिशाओं में जाइए और सारे जो पोस्टर मैंने बताया, जो रिसर्च पोस्टर है IUCAA में जो रिसर्च होता है, वो भी वहाँ पे हमने डाला हुआ है अलग अलग जगहों पे, अलग अलग कॉर्नर्स पे। तो सारे कोनों को ढूंढिए, वहाँ पे इन पोस्टर्स को देखिए। आपको अगर चाहिए तो आप इस लिंक पे पोस्टर एग्जिबिट्स के लिंक पर जाकर आपके प्रश्न भी हमें भेज सकते हैं। तो ऐसी एक सुंदर सी वेबसाइट और एक अलग से आभासी टूर हमने आपके साथ यहाँ पर शेयर किए हुए हैं, तो आप जरूर इसका फायदा उठाइए। तो इस वक्त हम चलते हैं आगे की ओर। आज के शेड्यूल में जो पहला जो हमारा टॉक है वो है नेब्यूलास पे, right? So we have the first speaker, Ishita Banerjee, coming up just now. So she will be talking about nebulae, which are basically gas clouds, but really beautiful. And one of the, those beautiful images that you see from Hubble's and other space telescopes and terrestrial telescopes also, those, many of those are of nebulae, which are very close by to us. And these beautiful images always inspire us. So if you if you are attending this talk, keep a lookout for those images you may have seen before, but also give attention to all the lovely new information that Ishita Banerjee has collected for us. So please come online, Ishita. Welcome.
Yeah, hi. So actually the screen sharing is disabled. Yeah.
Please go ahead.
Yeah, I hope you can see my screen. Is it visible now?
Just try once more.
Okay, it isn't. Yeah. I think now it is.
Yeah, now we can see it.
You can see it. Yes, great.
Yeah.
Thanks.
Then should I start?
Yes, please go ahead. The stage is yours.
Okay. So hi, this is Ishita, and currently I'm at my second year of PhD at IUCAA. And today I'll try to introduce you to probably the most spectacular object in the universe. So just before that, I would like to ask you a few more questions. So of course, all of us have seen the night sky, and it looks very beautiful because it's full of stars. And there are stars of different size, different colors. And just like a living body, a star were born at a particular point, and then after living a very long life, it eventually die. The life cycle of a star can itself be a very interesting discussion topic. But in today's session, we would try to address some more fundamental questions. Like, have you ever wondered where these stars are coming from and what they're actually made of? And when they die, what happens to all those materials that they have created for billions of years throughout their whole lifestyle? So, and particularly what those events look like. So if you're looking for the answer to these questions, then there are actually a lot of answers there. Because they might sometimes look like some insects. Or flowers maybe. Might look like some animal being. Some facial features of human. Or maybe something just look like this. And in some cases, they might not have any particular shape. And in that case, it would just look like this. What is it? This is called nebula. When they are many in number, We call them nebulae. And they are basically a mixture of gas and dust. So by gas, we have actually meant about hydrogen, helium mostly, and in some cases, in a very little quantity, the other gases as well, like oxygen, sulfur. And by dust, we actually meant the teeny weeny particles of a typical size of a few micron. So just to give you a flavor of how small a micron is, the thickness of a human hair is actually 100 micron. So you can think of that how small they are. And they are mostly made out of silicate, aluminum oxide, calcium. So in your regular life, can you think of an object that is actually made out of gas and dust? Yeah, of course. It's cloud. And in Latin, actually, this word nebula means the same. It's cloud. So this is really a very huge, big jumbo cloud. And it has a very little density. So the air we are breathing right now is actually 100 trillion times more denser than this one. And that is why when we actually can think of an equal amount of gas, just like the volume of our own Earth, then it would only weigh a few kilo. Yet we are being able to see them from the distant part of our sky because they are really huge in size. Typically, they have a diameter of a few light years. So how big a light year is? Well, it actually consists of this much centimeters. And this cloud is actually the nursery of 1,000 young stars. But now you would probably wonder that why it is so. Because the stars does not look like this cloudy. They are more compact, right? Well, then let me describe that process as well. So this is what is our nebula. It is the gaseous cloud. It's a very big cloud. Hence it has a very, it has a long, very much gravitational pull, and that works inward. And at the same time, the gaseous particles, they are pushing it outwards. In normal times, these two things actually balances itself. But then something happens, some events, some accident. I would call them a happy accident because that is what actually giving us the stars. So this can be some explosion in stars, like we know it now as supernova. Now this supernova would actually disbalance this, and the gravity will eventually win the war. And eventually the whole cloud would start collapsing towards its center. And during this process, it would become clumpy, and its density would increase until it becomes so dense that it will be able to produce its own energy. And that is what a star is, right? So this is how a newborn star looks like. And it has like disk, like we can see in our planet Saturn. And eventually these teeny weeny some planets will be formed out of this disk. And the whole cloud would give birth to sometimes thousands of this solar system like objects. And this whole process takes around a few million years to be completed. And that's huge, right? So now probably you will be thinking of that how these things are look like. So this is a very famous picture of three gaseous pillars that belongs to a nebula called the Eagle Nebula. And star formation is going on rapidly within them. And that is how they get the name of pillars of creation. But you can't really see them because the gas is actually obstructing that view. But you would wonder that within thousands of years, say, this whole gaseous clouds would get actually pushed by these newborn stars, and there won't be any trace of them. Yeah, we won't be able to say these pillars anymore. But now you would probably think that, can you see a nebula by naked eyes? Well, the answer is yes. Probably most of you will be familiar with this stellar constellation called Orion that more sort of looks like a warrior. And it is actually consisted of a very bright stars, like these three around its belt. And there is another one which is indicating its shore. But the thing is, this one is not actually a star. Rather, it's a nebula, our very favorite Orion Nebula. So this is where the nebula is. And also, like it is a very active star formation zone right now. And this nebula is actually part of a much bigger cloud, which looks something like this. But we can't actually see it by naked eyes. because it does not have that much energy to glow. Well, probably then you would ask me, then how do I have this picture? Well, wait, why don't you just think about it a bit until I tell you the answer at the very end of this session. For now on, I would move forward. So Orion Nebula is basically an emission nebula. It emits something, right? What? Light, of course. Which light? The light of stars. So it basically absorbs those light that is coming out of the stars, and then it re-emits them. And that is how it glows. There is another type of emission nebula, which we know as planetary nebula. And the difference between any other emission nebula and a planetary nebula is, instead of having any ordinary stars within it, it has a white dwarf. So here is a very beautiful simulated video that I have actually taken from the official YouTube channel of Chandra X-ray Observatory. There are a lot more videos like this. You can have a look. So it would show how planetary nebula is formed from a star. So white dwarf is basically when a typical low mass star is almost at the end of its life. It bursts out and ejects its outer shell, and the very dense hot core, central core, is left, which is the white dwarf. So this is the white dwarf, and see how this gas is actually spreading out almost circularly, almost spherically around this white dwarf, and eventually they would start glowing by the energy which will be provided by this white dwarf, and it would be bloomed as a planetary nebula. Yeah, so see, this is how the nebula is being formed, and this is our very popular one, the Cat's Eye Nebula. Yeah, so here I'm showing you a lot more other pictures of different planetary nebulas. Like this one you have just seen, the Cat's Eye Nebula. This is the Helix Nebula. This is the Lemon Slice Nebula. See how spherical it looks. And also, like, it is not mandated that they would always look like the same. It might look something like this, the Butterfly Nebula. And how it would look like that mostly depends on the type of explosion it occurred during the generation of the white dwarf. So yeah, this is another very famous planetary nebula called Ring Nebula, where you can also see the gaseous rings around it. And most of the time they look very circular. And that is what actually misled the astronomers back then, because they thought they are planets. And that is how they get the name planetary nebula, though actually they doesn't have anything to do with in planetary system. Yes. So moving on, the next is reflection nebula. So again, it reflects light. Which light? Again, the light of the stars. So here you can see the stellar cluster, the seven sister stellar clusters, Pleiades cluster, and which is surrounded by a very dusty nebula. And it looks blue for the same reason that our sky looks blue. So you know that there are dust particles in our atmosphere as well, and the sunlight gets refracted by them, scattered by them, and the blue lights get scattered the most, and that is why it looks blue. And this is the same reason that this nebula is actually looking blue, because it has a lot of dust around it. The next in our list is supernova remnants. So supernova is like an explosion, an exploding star. It's like a pataka. So when a very massive star is almost at the end of its age, it blasts out and leaving all those materials that it has produced throughout its life, and eventually it take a shape of a nebula, and this is Crab Nebula. So it is a very famous one. It was that famous that actually in history, in the old manuscript, it has a mention. So around the year of 1054, the Chinese people have actually mentioned about a very new star. They have called it as a gate star, which suddenly appeared in the sky, and it was very bright that it was even visible during the day. So back that time, they didn't have any idea about the supernova, but now our astronomers have proved that this event is actually the supernova that caused this nebula, this Crab Nebula. And finally, there are dark nebulas. Yeah, they are dark because we can't see the light coming out of them. But that doesn't stop us from seeing them because of this spectacular, very bright background. See, this is Snake Nebula, the Cone Nebula, the famous Hot Nebula, the Coal Sack Nebula, and all of them are actually dark. But that doesn't mean that they does not have any newborn stars within them. Actually, our astronomers have proven that like some very like star forming activities is actually going on inside them, but we can't see those lights. Yeah, it's true. You have heard me right. We can't see all the lights. So this is a spectrum. Spectrum is basically the collection of all possible lights. But our eyes, our rod and cone cells, are only sensitive to this little part of it. We can only see this much, the Vibgeo colors. But we can't sense how X-rays or ultraviolet rays or infrared rays look like. But so what? We have our telescope and they can see all of it. And using their eyes, we can actually see everything, like what is going on even inside those dark clouds. So see this example. This is M78 Nebula, which is basically a reflection nebula where because it's glowing in blue, and there is a very dark cloud in front of it. In normal time, it is dark, but when the same thing is observed using infrared, it starts glowing. And see this active zones, which is very bright and which is forming stars very actively. So I'm almost at the end of my session, and we are again back with our very favorite one, the Orion Nebula. And this is a very spectacular image because it has a lot of colors within it. But the thing is, even if you try to observe it with the best telescope we have right now, it won't look like this. Because this image, the colors within this image is not real. They are artificially mixed by the trained astronomers so that we can observe them and collect the information from it. Well, like you who are watching today's session, you, of course, you are interested in astronomy. And I think that most of you will also like end up choosing this as your career. And in that case, even you will get trained. And in that case, you will be able to tell me that what these colors actually mean. They are actually pointing the presence of different elements. Like this green one, this is actually coming from the hydrogen. The blue is for the oxygen present in this atmosphere. And this one, this red one, is actually coming from the sulfur. And this is the fun part about astronomy. These objects are actually far from us, and we are sitting on Earth. And just by collecting the light from them, we are actually being able to tell that how old they are, what is their mass, how big they are, how many stars do they have right now, and what is their age, and a lot of other things. Isn't that interesting? It is very much to me, at least. Anyway, so we are almost at the end. Thanks. That was my plan for today.
Thank you so much, Ishita. This was really an amazing talk. And it was indeed a treat to all of our eyes. So basically, I'm getting all the feedbacks that you must not be able to see on YouTube, but they have loved the talk, and they are getting interested in all these astronomical objects because of your talk. So very interesting talk, Ishita, beautiful talk. Thank you. So everyone is complimenting, and they are also interested to know a bit about your journey, a short bit, and why you basically got interested in astronomy, or to study astronomy, or to make it your career. We would love to know that.
Well, actually, a part of it I've already answered because it fascinates me more, the things about lights and that they are very at distance apart from us, but here we're actually being able to study them. But there is another reason, like considering the current situation of our world, I feel that astronomy is the only field where all of us are just Earth. There is no other existence of us. There is no difference in between us. And we are just at this much, a very teeny weeny part of the whole cosmos. And that is another thing that fascinates me more, that we are trying to study the same thing and we are looking at the things in the same vision. And to say a bit about my career, so I am from West Bengal. So I did my graduation in the physics honors. I did it from Calcutta University. And then I did my master's degree from IIT Kharagpur. and then I went for INET. This is the entrance for IUCAA. So those who are interested then can also try for that. This is their own exam. And from that, I got into IUCAA actually.
Okay.
Yeah.
So thank you for that. And I'm sure all of our viewers will be really happy to know this. And many of our kids, like 11, 12 standard kids, are also watching you, and they are saying that they are inspired and wow, we enjoyed the talk.
Ishita,
yes.
Johnny, I'll just read out a question from the
Sure.
live chat that we have got right now. So, you mentioned all these beautiful pictures, with all these beautiful pictures, the details of nebula. A question is there asking, why can't we see them with our naked eyes?
Well, actually, you can see them, but the thing is, they are very big, but they are also very far from us. And the far things they start looking very smaller. So you would see that maybe you are standing at the very edge of a forest, and though it has the trees of almost same size, but the trees which are more far from you, they would look small. And this is the case actually. So our eyes is not that much sensitive, or it can't resolve that much like differences within them, because they are very far, and hence they look very small. And just by observing those as stars, because you know that stars are literally point like object, so from that you can't really extract any information, and that is why we need to see their bigger image. And that is what actually our telescopes helps us. They produces the image we want, and hence we can collect all those information from them. But yeah, with a good binocular or something, you can actually see some of them, like I have already mentioned, the Orion Nebula you can see. And yeah,
and actually the Orion is visible these days in the evening sky. So anybody who is interested, if you have a telescope, try it. But if you have a binocular, as Ishita is suggesting, go ahead, try to look for this fuzzy object in the belt of what is called Orion. Orion has various names in India, so you'll have to find out your local name, like Mriga or Kalpurush or something. But then you can still find the Orion Nebula there. So this is a lovely talk, Ishita, and just encouraging everyone in the crowd, in the audience, to ask questions, because this is a good chance to speak to scientists directly firsthand, and they're waiting for your questions to answer them. You'll, of course, you're welcome to put your questions in the chat box in whichever medium you are, and we'll read them out. I think I've got another question here. And so from where does all this gas and dust in space come from? So
okay.
Basic question.
Good one. Yeah. So actually, I have just shown you the supernova remnants, right? So the stars are mostly formed out of this hydrogen and helium, and there was a big abundance, like they are most abundant elements in universe. One of this reason is, of course, the thing what happened just after the Big Bang. It created a huge amount of hydrogen, and from that helium also. And the other thing is, these big stars, these full-grown stars, when they die, they eject all those elements that they have created throughout its life. So that thing, those materials, the supernova remnants, those parts actually get again diffused, and they are the material that helps the cosmos to form the new stars. So it is basically coming from the stars itself. So it's like a star is giving birth to another star. So the grandma star, then the mother star, then the daughter stars. There are like a whole new generation of them.
Oh, that's good to know. I mean, there's a lineage of stars. Which kind of which generation star are we going around?
So there are population 3 stars as well. And yeah, okay. So, so just those who are interested, the sun, our sun, it is also like, because I have mentioned about it, the white dwarf. So our sun is also going to be a white dwarf, but it's not right now. It would take a few more billion years maybe. Yeah. So.
Yeah, that would be interesting. Of course, you still have to go to school and college and do your job, because that's coming only in a few billion years. Lovely. So let me ask you a personal question. So you talked about your inspiration, but what is the kind of advice that you will give at your stage now to the youngsters? Because many of them are school-going students, so they will ask you, what books should I study? What telescope should I buy? So, do you advise some such things to do, or what else?
Well, I myself am not that much experienced actually, but I can tell you what I did. So keep questioning, and like if wherever it may like it catch your eyes, just read that part and be always fascinated. Like never feel like, oh, this is the end. Okay, this is what I have got. When you will think like that, okay, you have understood it totally, ask another questions. Maybe there are a lot of them which are not being answered till then, and you would try to find it. And yeah, keep fascinating. Just keep watching them.
That's a lovely answer. And in fact, that's, I think, the basic theme of National Science Day, that to instill this attitude of questioning. So we have to ask questions, and then we get the answers either through simple reading of other books or by doing cutting edge research like you are. And what I noticed is that your research also has some part of, involves infrared observations. So
yeah, I mostly work in visual range. So I am working in the circumgalactic medium. It is the medium very close to the galaxy, but outside this, outside this galaxy. And we are actually trying to see that how this gaseous quantity is varying in that medium, the hydrogen, oxygen, carbon, everything.
Okay, wow. So all these elements, they vary, and you're studying them. And I was just talking about the infrared because we have been very excited about the James Webb Telescope, space telescope, which has gone up, which will be looking at the infrared spectrum and probably looking at similar objects, right? Some of them will be similar objects.
Yeah, so it would be like, yeah, it would be a lot more like a whole brand of new information we would get because it would work in infrared. Whereas Hubble, yeah, Hubble too had some infrared detectors, but yeah, it was more towards the visible range. But yeah, of course, I think there would be a separate discussion session on JWST, and they would know a lot more from it.
Yeah, no, we are. I'm just saying that we are thankful Hubble had a visual spectrum, because otherwise all these lovely pictures we grew up seeing would not have been there. And
yeah, and most of the pictures I have used in my slides are actually from that. So
Hubble
yeah,
Space Telescope.
I can also give them a website where they can see a lot more other pictures like this.
Oh, sure. That will be lovely. I think the Hubble Space Telescope has a heritage gallery. If you just look up Hubble heritage on Google, you'll get to this gallery of multitudes of objects, many of them nebulae, and there are also galaxies, etc., which are these breathtaking images, which will just floor you. You just keep looking at them and then want to put them as a wallpaper next sometimes. But that's not all. You have just met a scientist who actually studies these what we call pictures, but these are actually astronomical data, and you can know so many things from there. I'll ask Shivani if there's any more questions.
Yes, we have one more question. He is saying hello, and why doesn't the pressure of the gas stop the nebula from collapsing into a star?
Well, good questions, but I think it's not a very easy one, because the kind of disturbance a supernova or any such event cause is it works in a different way. It's more detailed astronomy, but I hope when you would read about it, you would know, and you'll be able to say that, like, why actually gravitation is actually winning the game. So I would leave these questions right now, because I think most of the other people, it would be difficult for them to get.
Yeah, no, we have to do that sometimes, but it's good you asked the question. And I think there's another one which I can see, which asks again similar things about the end stages of stars. Why do some become planetary nebula and some become black holes? But
okay, that basically depends on the mass of the star. So a low mass star having a mass around less than 8 solar mass, in that case they are more prone to be a white dwarf. And during the production of white dwarf, that is what actually gives us these planetary nebulas. And the different shapes of this planetary nebula actually depends on how the situation was near the star in the stellar environment, like where they be binary stars, or there were some nearby planets. or they were just a single star, and that is what actually defines that how the structure, the nebula structure would look like. And the supernova remnants, that is actually for the massive stars. Yeah, and in that case, we get in the center some neutron stars or sometimes a black hole maybe.
Lovely.
So
These are fascinating things. I'm sure, like story of a star. So thank you very much, Ishita, for this lovely presentation. And I'm sure we'll see more of you on our channel in future events where you'll give such lovely talks as well. Thank you again. We'll leave the viewers, since the speaker has to change, we'll leave the viewers with a short video which Ishita has provided us of some more beautiful views. So let's have that.
Thanks, everyone.
Ishita. Thanks so much.
The year 2019 marks the 20th anniversary of the launch of NASA's Chandra X-ray Observatory into space. The Crab Nebula was one of the first objects that Chandra examined with its sharp X-ray vision, and it has been a frequent target of the telescope ever since. There are many reasons that the Crab Nebula is such a well-studied object. For example, it is one of a handful of cases where there is strong historical evidence for when the star exploded. Having this definitive timeline helps astronomers understand the details of the explosion and its aftermath. In the case of the Crab, observers in several countries reported the appearance of a new star in 1054 AD in the direction of the constellation Taurus. Much has been learned about the Crab in the centuries since. Today, astronomers know that the Crab Nebula is powered by a quickly spinning, highly magnetized neutron star called a pulsar, which was formed when a massive star ran out of its nuclear fuel and collapsed. The combination of rapid rotation and a strong magnetic field in the Crab generates an intense electromagnetic field that creates jets of matter and antimatter moving away from both the north and south poles of the pulsar. Astronomers also see an intense wind flowing out in the equatorial direction. A new composite image adds to a scientific legacy spanning nearly 2 decades between Chandra and the Crab Nebula. We look forward to what the Crab Nebula will reveal next.
And again, this was a really nice video. And now I would like to introduce to you all Meenakshi Mount. And we again have a really fascinating talk, I'm sure. And this is also a treat for the Hindi viewers that we have today. So हम अभी जानने वाले हैं कि आकाश गंगाओं के केंद्र पे जो भी खगोलीय दैत्य है उनके बारे में. So I would not delay the talk and I'll hand over the mic to Meenakshi. Meenakshi?
Okay, yeah.
Yes, we can hear you. Yes.
Okay, yeah, sure. So I will be sharing my screen now.
Yes.
Yeah, sure. Okay. Okay, so I guess you can see my screen.
Yes, we do.
Sure. Okay, so I will begin now. So hi everyone, I am Meenakshi. I am a PhD student at IUCAA Pune, and so today I will be discussing you with this talk and on the topic the monsters at the centers of the galaxies, यानी आकाशगंगाओं के केंद्रों के खगोलीय दैत्य. I guess इस पिक्चर से बहुत लोग वाकिफ होंगे. तो ये इंटरस्टेलर मूवी से है एंड दिस इज द प्रेडिक्टेड इमेज ऑफ अ ब्लैक होल. एंड सो दिस ब्लैक होल्स, जिसे हिंदी में कृष्ण विवर कहा जाता है, सो दीज आर द मॉन्स्टर्स वी हैव एट द सेंटर्स ऑफ आवर गैलेक्सीज. एंड आज हमें इनके बारे में ही कुछ जानने को मिलेगा. सो ये इमेज है हमारी अपनी उन गैलेक्सी मिल्की वे यानी आकाशगंगा की. और क्योंकि हम इस गैलेक्सी का ही एक पार्ट हैं, तो इसकी इमेज कुछ इस तरह से दिखती है हमें. और जैसा कि आप ये लेजर यहाँ देख सकते हैं, दिस ऑरेंज कलर्ड लेजर, सो दिस बीम इट पॉइंट्स टुवर्ड्स द सेंटर ऑफ द गैलेक्सी. एंड जिसे 2020 का नोबेल प्राइज मिला है कि सेंटर में एक कॉम्पैक्ट मैसिव ऑब्जेक्ट है एंड मोस्ट प्रोबेबली इट इज अ मैसिव ब्लैक होल, बिकॉज मोस्ट गैलेक्सी में यही होता है. सो एंड विच वी कॉल एज सेजिटेरियस ए स्टार. एंड वो ब्लैक होल सेंटर में इट इज एन इनएक्टिव ब्लैक होल. So it is goes something like this, which is actually a good thing for us, because on the other side there are some black holes which are active. So what does this black holes do? So ये active black holes, because they are very massive, they have a very strong gravitation force, यानी गुरुत्वाकर्षण बल बहुत ज़्यादा होता है, and जिसकी वजह से they accrete matter from their surroundings. जैसा आप देख सकते हैं, ये ब्लैक होल है एंड ये अपने कंपेनियन स्टार जो उसके पास में है, नियर बाय स्टार, उससे मैटर को अपनी तरफ खींच रहा है. एंड ये आसपास एक डिस्क क्रिएट कर लेता है जिसे एक्रीशन डिस्क बोलते हैं. एंड इस वजह से, एक्रीशन की वजह से, ये एनर्जी को क्रिएट करता है एंड उस एनर्जी को अपने सराउंडिंग्स में थ्रो आउट करता है, जिसे हम फीडबैक बोलते हैं. एंड वो फीडबैक जनरली दो तरह से होता है, विंड्स एंड जेट्स. विंड्स जैसे कि विंड्स जैसे कि आप इस पिक्चर में देख सकते हैं, विंड्स दे आर स्फेरिकल इन नेचर एंड वो इस एक्रीशन डिस्क से प्रोड्यूस होती हैं. जेट्स ऑन द अदर साइड दे आर थिन कोलिमेटेड, एक जैसे पानी की पाइप की तरह, बहुत ही तेज गति में बह रही हो उसकी तरह जेट्स. तो आज की टॉक का मेरा मेनली फोकस जेट्स के ऊपर ही है, जिसके ऊपर ऑल्सो मेरा वर्क रिलेटेड भी है. सो वी विल गेट टू नो मोर अबाउट द जेट्स टुडे. सो हालांकि अभी जो ब्लैक होल हमारी गैलेक्सी के सेंटर में है, इट इज इनएक्टिव, बट व्हाट वुड हैपन इफ इन केस वो एक्टिव हो जाए? Well, so hopefully it is not going to happen in our lifetime, so we don't need to worry about that. Although ऐसे कुछ सिग्नेचर्स पाए गए हैं रिसेंट स्टडी में कि कुछ समय पहले, जैसे अगर आप ये जीरोस काउंट करें तो टोटल 6 जीरोस हैं. सो दिस इज 5 मेगा ईयर्स. इतने टाइम पहले कोई एक लो पावर जेट की एक्टिविटी थी हमारे सेंटर ऑफ द गैलेक्सी में. बट अभी करंटली ऐसा कुछ होने के कुछ एविडेंस नहीं है कि कुछ भी ब्लैक होल एक्टिविटी वहाँ पर अभी चल रही है. तो एंड सेकंड थिंग, हम सेंटर से 8 किलो पार्सेक की दूरी पे हैं. 8 किलो पार्सेक यानी आप काउंट करें तो इट्स 3 के बाद अराउंड 21 जीरोस, दिस मच सेंटीमीटर. ये डिस्टेंस बहुत ही लार्ज है. तो अगर सेंटर में कुछ भी ऐसा मिनिमल, कुछ भी लो पावर एक्टिविटी होती है, तो होपफुली हमें उसका फर्क नहीं पड़ेगा एंड वी आर सेफ ऑन द अर्थ, सो वी कैन चिल अबाउट दैट. एंड नाउ आई विल टॉक अबाउट द एक्टिव ब्लैक होल्स, जिसमें ये आप इमेज देख रहे हैं, ये एक सेंटोरस ए गैलेक्सी की है. सो दिस इज वन ऑफ द नियरेस्ट रेडियो गैलेक्सी वी हैव फ्रॉम आवर प्लेस इन द यूनिवर्स. तो ये इमेज डिफरेंट फिल्टर्स में है. जैसे ये जो आप लोब्स देख रहे हैं, ये रेडियो लोब्स हैं, जो जेट प्लाज्मा, जेट बिकॉज वो गैलेक्सी से बाहर निकल चुका है, तो उसके जो प्लाज्मा बाहर फैल गया है, सो दैट इज एमिटिंग इन रेडियो. दिस इज द एक्सरे एमिशन एंड दिस इज द ऑप्टिकल. दिस इज द गैलेक्सी and this is Cygnus A. It is also a very large radio galaxy. I mean, not radio galaxy, but large radio source. So you can see the center of this picture, we have the galaxy. And this radio we are seeing in the magenta color, these are the radio lobes from the jet. So you can see you can compare the scale of the galaxy and the scale of the jets. And this blue region is the X-ray. And this is the M87. I guess ये जो पिक्चर नीचे आप देख रहे हैं, the image of the black hole taken by Event Horizon Telescope, इससे भी I think बहुत लोग वाकिफ होंगे. So this was the first time that we were able to take image of a black hole. And इस गैलेक्सी में भी रेडियो जेट्स पाए गए हैं, जैसे आप यहाँ देख सकते हैं. तो ये टेल्स ऑफ द रेडियो जेट्स. एंड देन सो अभी तक हमने देखा था एक आइसोलेटेड गैलेक्सीज के बारे में, लेकिन गैलेक्सीज क्लस्टर्स में भी रहती हैं, ग्रुप्स में भी रहती हैं. दे कैन ऑल्सो बी अ पार्ट ऑफ दिस. सो इस तरह के इसी एक क्लस्टर की ये इमेज है. एंड उसमें भी आप देखेंगे यहाँ पर रेडियो जेट्स आप देख सकते हैं, इनकी गैलेक्सीज है. और इनमें आप जो ये मैजेंटा कलर की टेल्स देख रहे हैं, दीज आर द रेडियो जेट्स प्रोड्यूस्ड बाय द ब्लैक होल्स एट द सेंटर ऑफ दिस गैलेक्सीज. तो अभी तक हमने ब्लैक होल्स के जेट्स के बारे में जाना, लेकिन हालांकि अभी प्रश्न यह उठता है कि जेट्स प्रोड्यूस किस तरह से होते हैं. सो हालांकि इसका कोई ये भी क्लियर ऐसे पूरा क्लियर आंसर नहीं है, बट द मोस्ट बिलीव theoretical reason for that, that is Blanford-Nazik process. So Blanford-Nazik process, what it says that as you can see in this figure, so center में we have a black hole and उसके आसपास ये accretion disk है. So I will play this movie as well. तो आप देख सकते हैं जैसे ये सेंटर में ब्लैक होल है और आसपास accretion disk है. तो ब्लैक होल के स्पिन की वजह से वो टर्बुलेंट हेलिकल मैग्नेटिक फील्ड प्रोड्यूस करता है. हेलिकल जैसे आप यहाँ देख सकते हैं. हेलिकल यानी अगर आप एक स्प्रिंग लें और उसे दोनों ओर से खींचे तो जो शेप बनती है दैट इज हेलिकल. एंड उस हेलिकल शेप की वजह से, मैग्नेटिक फील्ड की शेप की वजह से वो पार्टिकल्स को बहुत ही तेज गति में एक्सेलरेट कर सकता है. एंड दैट कैन बी क्लोज टू द स्पीड ऑफ द लाइट. सो जैसे आप देख रहे हैं ग्रीन और ये रेड कलर, सो दिस इज द जेट प्लाज्मा, जिससे कि ये मैग्नेटिक फील्ड ब्लैक होल अपनी रोटेशनल एनर्जी की वजह से उस प्लाज्मा को बहुत ही तेज स्पीड में एक्सेलरेट कर पा रहा है. एंड इसी वजह से जेट्स, आई मीन इससे यही जो ये ब्लैंफोर्ड-नाजिक प्रोसेस है, ये प्रेडिक्ट करता है कि इसी वजह से ही जेट्स बहुत ही थिन कोलिमेटेड होते हैं एंड डायरेक्शनल होते हैं. ओके, सो लेट्स ओके. सो जेट्स भिन्न भिन्न पावर के भी हो सकते हैं. तो कुछ जेट्स लो पावर के भी हो सकते हैं, कुछ जेट्स हाई पावर के भी हो सकते हैं. हाई पावर जेट्स अराउंड 10 to the power 48 अर्ग्स पर सेकेंड, इतनी उनकी एनर्जी भी हो सकती है. एंड यदि हम जेट्स के स्केल को देखें तो जो गैलेक्सी साइज होता है, जैसे एलिप्टिकल गैलेक्सीज व्हिच आर वन ऑफ द लार्जेस्ट गैलेक्सीज वी हैव, सो उनका साइज 100 किलो पार्सेक. तो अगेन याद रखिए 1 किलो पार्सेक मींस यू हैव अराउंड 21 zeros आफ्टर 3 अराउंड, इट्स 3 into 10 to the power 21 सेंटीमीटर. सो इतने लार्ज साइज का. एंड गैलेक्सी क्लस्टर्स की बात करें तो वो 1000 किलो पार्सेक तक के हो सकते हैं. जनरली जो हाई पावर जेट्स होते हैं वो एलिप्टिकल गैलेक्सीज, जो बहुत ही मैसिव गैलेक्सीज होती हैं और जो अर्ली यूनिवर्स में फॉर्म हुई थी. अगर आप यूनिवर्स की एज देखें तो आज यूनिवर्स की एज है 13.7 बिलियन ईयर्स. तो इट्स अराउंड, यहाँ पर देखिए 137 के बाद ये 8 zeros हैं. तो ये गैलेक्सीज अराउंड 3 एंड इसके बाद वी हैव दिस 9 zeros. सो इट्स लाइक 3 बिलियन ईयर्स के बाद ये गैलेक्सीज प्रोड्यूस हुई थी. और जो लो पावर जेट है नियर बाय यूनिवर्स में, वो जो गैलेक्सीज पाई गई हैं वो गैलेक्सीज हमारे नियर हैं, हमारे लोकेशन के. एंड लाइक दे आर जस्ट रिसेंटली फॉर्म्ड. सो दैट इज अराउंड 12 बिलियन ईयर्स. सो 12 बिलियन ईयर आफ्टर द बिग बैंग. So they are quite recent as compared to these earlier galaxies we have. So अभी तक हमने जेट्स के बारे में बहुत कुछ जाना. It's enough about them. And now I will talk about jet feedback. Jet feedback यानी जब एक जेट एक गैलेक्सी में लॉन्च होता है from its black hole, I mean जब उसका लॉन्च होता है, जैसे जैसे वो उसका उस गैलेक्सी के अंदर इवॉल्व करता है, यानी उसकी प्रगति होती है अपने एनवायरनमेंट में, तो वो किस तरह से अपने एनवायरनमेंट से इंटरेक्ट करता है. सो उसे हम जेट फीडबैक बोलते हैं. इसके लिए पहले आप एक कार्टून इमेज देखिए. सो ये एक डिस्क है, डिस्क ऑफ द गैलेक्सी. एंड आप इसको, आई मीन आप जैसे अगर आप एक प्रेक्षक हैं, आप ऑब्जर्वर हैं, आप इस एंगल पे देख रहे हैं, तो दिस डिस्क हैज अ फाइनाइट थिकनेस हियर, यू कैन सी इट. एंड ये जेट है जो लॉन्च हुआ है सेंटर से. अगर आप इस डिस्क को टिल्ट कर दें तो दिस बिकम्स एन एज ऑन व्यू. तो आप देख सकते हैं कि यहाँ पर ये एज व्यू है, डिस्क की थिकनेस है, और जेट डिस्क के ऑलमोस्ट अंदर ही लॉन्च हुआ है. तो जैसे जैसे इस जेट की प्रगति होगी अपने एनवायरनमेंट में, जैसे जैसे वो इवॉल्व करेगा, इट विल इंटरेक्ट विद इट्स सराउंडिंग्स. तो वहाँ की वो गैस किस तरह इंटरेक्ट करेगा, उसे किस तरह से अफेक्ट कर सकता है डिफरेंट फीचर्स को, जिसकी हम बात करेंगे आगे. सो उसे हम जेट फीडबैक बोलते हैं. तो इसके लिए मैं आपको यहाँ कुछ सिमुलेशंस मूवी दिखा रही हूँ, टेकन फ्रॉम दिस पेपर आई हैव रिटन अबव. एंड सो वेट, आई विल पुट दिस ऑन लूप फर्स्ट. ओके, सो तो जैसे आप फर्स्ट में देख सकते हैं कि फर्स्ट वीडियो में जेट है दैट इज परपेंडिकुलर टू द इट्स डिस्क. सो दिस इज द डिस्क वी हैव एंड द जेट इज लॉन्च्ड परपेंडिकुलर टू द डिस्क. एंड दैट्स व्हाई वो बहुत जल्दी ही डिस्क से बाहर निकल गया, बिकॉज इंट्रैक्शन बहुत ही कम है, बिकॉज डेंसिटी बहुत कम है इस रीजन में. लेकिन अगर आप देखें दूसरी वीडियो को, तो यहाँ पर देखिए जेट का जो एंगल है विद डिस्क, इट इज अराउंड 45 डिग्री. तो जेट का यहाँ पर इंट्रैक्शन स्केल एज कम्पेयर टू दिस फर्स्ट केस ज़्यादा है, क्योंकि जेट डेंस गैस की वजह से डिस्क से बाहर नहीं निकल पा रहा है. एंड इसलिए वो अंदर ही अंदर जैसे चैनल्स क्रिएट कर रहा है इंट्रैक्शन के. पर कुछ टाइम बाद वो गैस को पुश करते हुए अपने रास्ते में, जैसे आप देख सकते हैं मोशन ऑफ द डेंसिटी, वो यहाँ पर वर्टिकल एक्सिस के अलोंग एंगल क्रिएट कर लेता है, अपना पाथ क्रिएट कर लेता है, और वहाँ से बाहर की ओर इवॉल्व कर जाता है. एंड तीसरे वीडियो में आप देखेंगे इस केस में जेट का एंगल फ्रॉम द वर्टिकल एक्सिस यहाँ पर 70 डिग्री है. मींस इस केस में जेट का जो इंट्रैक्शन है वो बहुत ज़्यादा है एज कम्पेयर टू दीज टू प्रीवियस केसेस. तो जैसे इसमें आप देख सकते हैं कि जेट यहाँ पर डिस्क से बाहर ही नहीं निकल पा रहा है, बिकॉज वो डेंस गैस की वजह से हिंडर्ड है, एंड वो अंदर ही अंदर इवॉल्व करता जा रहा है, उसका इंट्रैक्शन भी बहुत ज़्यादा है. However, jet के जैसे आप देखेंगे, if you see this motion of this dense region, so these regions, they are being pushed away by the jet. So the jet, it is driving outflows and backflows, यानी उत्प्रवाह और प्रतिभा क्रिएट कर रहा है और गैस को पुश करता जा रहा है जैसे जैसे इवॉल्व कर रहा है. So this is what like jet and gas interaction is all about. So jet and gas interaction. एंड अब हम बात करेंगे जैसे जैसे जेट की, हमें देखा कि जेट की प्रगति होती है. यहाँ मैं बस एक ही सिमुलेशन की वीडियोस दिखाऊंगी. देखेंगे कि जैसे जैसे एक जेट जिससे 45 डिग्री एंगल पे लॉन्च हुआ है डिस्क में, जैसे जैसे उसकी प्रगति होगी, डिफरेंट भौतिक माप यानी प्रेशर, टेम्परेचर एंड वेलोसिटी यानी चाप, तापमान एंड वेग, वेयर इट इज जस्ट द जेड कॉम्पोनेंट ऑफ द वेलोसिटी, वो किस तरह से इवॉल्व करेंगे. तो जैसे अगर आप फर्स्ट वीडियो में देखेंगे तो आप देखेंगे तो अर्लियर टाइम पे पूरी जो डिस्क है वो लो प्रेशर पे है. बट जैसे जैसे ही जेट लॉन्च हुआ, जैसे जैसे जेट इवॉल्व करने लगा, उसके उत्प्रवाह और उसके बैकफ्लोज की वजह से डिस्क के जो रीजन है जिनसे वो इंटरेक्ट कर रहा है अपने आसपास के सराउंडिंग से, उन्होंने उसको प्रेशराइज कर दिया है. बिकॉज वो अपनी एनर्जी को, अपने प्रेशर को उन पे इम्पार्ट कर रहा है. तो जैसे आप ये स्केल से देख सकते हैं यहाँ पर. सो ये स्केल लोगैरिथम में है एंड यू कैन चेक द एवोल्यूशन ऑफ द प्रेशर. एंड अगर आप टेम्परेचर की बात करें तो अर्लियर टाइम्स पे जो डिस्क गैस है, बिकॉज किसी के साथ उनका इंट्रैक्शन नहीं है, किसी आउटफ्लो के साथ, तो इसलिए वो लो टेम्परेचर पे है. बट जब सेंटर से जेट लॉन्च हुआ तो जैसे जैसे उसका इंट्रैक्शन स्केल बढ़ेगा तो उसके आसपास के रीजन का टेम्परेचर बढ़ना स्टार्ट हो गया, बिकॉज वो अपने थर्मल एनर्जी है, थर्मल ऊर्जा को भी अपने आसपास के रीजन्स में इंजेक्ट कर रहा है. तो आप देख सकते हैं कि इन रीजन्स का जैसे टेम्परेचर बहुत ही हाई हो चुका है. और अगर हम वेलोसिटी का देखें तो आप देखेंगे कि स्टार्टिंग के टाइम पे जैसे डिस्क की जो वेलोसिटी है डिफरेंट कंपोनेंट्स की, वो रैंडम है, कोई ऑर्डर नहीं है. लेकिन जैसे जैसे जेट की प्रगति होगी वो अपने डायरेक्शन में गैस को पुश करना स्टार्ट करेगा. एंड ऑल्सो यहाँ इस तरफ बैक फ्लोज क्रिएट होंगे जिसे हम प्रतिभा कहते हैं. एंड आप देखेंगे कि एक जैसे यहाँ पर रेड यानी पॉजिटिव वेलोसिटी, यहाँ नेगेटिव वेलोसिटी. सो एक काइंड ऑफ ऑर्डर आने लगा है मोशन में, और जेट क्योंकि अपने डायरेक्शन में ही अपने आसपास की गैस को पुश करता जा रहा है. I will just let, okay. So अभी तक हमने बात की जेट्स के इंटरेक्शन की, वो किस तरह से अपनी सराउंडिंग गैस से इंटरेक्ट कर सकते हैं और किस तरह से वहाँ पर डिफरेंट फिजिकल मेजर्स को अफेक्ट कर सकते हैं. लेकिन अब प्रश्न यह उठता है, एस्ट्रोनॉमर्स जो डिफरेंट वेवलेंथ्स में यूजिंग डिफरेंट टेलीस्कोप्स हम डिफरेंट गैलेक्सीज के इमेजेस ले रहे हैं, हम जेट फीडबैक के बारे में क्या पता कर सकते हैं. आप सबके मन में यही क्वेश्चन आ रहा होगा, व्हाट डू आई मीन बाय दिस. तो मेरा कहने का मतलब है कि विजुअल फिनोमिना क्या है, यानी दृश्य जो हम डिफरेंट टेलीस्कोप से देख सकते हैं, डिफरेंट डायग्नोस्टिक्स एंड मेजर्स, हम किस तरह के माप कर सकते हैं, भौतिक माप किस तरह के कर सकते हैं, एंड उनके नंबर्स क्या हैं. नंबर्स इंपॉर्टेंट होते हैं बिकॉज वो हमें एक कंपैरिजन करने का एक स्केल बताते हैं कि हम कैसे डिफरेंट गैलेक्सीज को या फिर डिफरेंट सिस्टम्स को, जहाँ पर जेट्स लो पावर के हैं, हाई पावर के हैं, जेट्स नहीं हैं, हम उन्हें किस तरह से कंपेयर कर सकते हैं उन डिफरेंट भौतिक माप को. तो इसके लिए पहले मैं बात करूंगी कि जेट्स का स्टार फॉर्मेशन पे क्या इफेक्ट हो सकता है. स्टार फॉर्मेशन यानी तारा निर्माण. तो पहली बात, तारे होते क्या हैं. तारे बस दे आर जस्ट अ बिग बॉल्स ऑफ गैस. सन, सो दिस इज आल्सो अ स्टार, इट इज द नियरेस्ट स्टार वी हैव. एंड देन स्टार्स बनते किस तरह से हैं. तो इसके लिए जैसे आप एक वीडियो देखेंगे सिमुलेशन, तो ये आप देख सकते हैं, ये एक बॉल ऑफ गैस है, स्फेरिकल बॉल ऑफ गैस, एंड ये अपनी ग्रेविटी के अंदर कोलैप्स करता जा रहा है. तो स्टार्स भी इसी तरह से बनते हैं जब इस तरह के एक रीजन जहाँ पर बहुत ही ज़्यादा गैस है, उस रीजन की ग्रेविटेशन एनर्जी वहाँ की थर्मल और काइनेटिक एनर्जी यानी थर्मल और गतिज ऊर्जा से ज़्यादा हो, तभी वो जो रीजन है गैस का वहाँ ग्रेविटेशन कोलैप्स हो पाएगा और जो भी स्टार फॉर्मेशन होने के लिए जो प्रोसेस हैं वो स्टार्ट हो पाएंगे. तो जेट्स का स्टार फॉर्मेशन पे दो इफेक्ट दो तरह से हो सकता है. फर्स्ट जो पॉजिटिव भी हो सकता है एंड सेकंड जो नेगेटिव भी हो सकता है. पॉजिटिव यानी जैसे हमने पीछे सिमुलेशन में देखा, जैसे जैसे जेट इवॉल्व करता है अपने एनवायरनमेंट में, वो अपने आसपास के रीजन्स पे प्रेशर क्रिएट करता है. तो कंप्रेशन की वजह से उन रीजन्स की डेंसिटी यानी घनत्व बढ़ जाएगा, जिसकी वजह से पोटेंशियल एनर्जी बढ़ जाएगी, यानी गुरुत्वाकर्षण एनर्जी उन रीजन्स की बढ़ जाएगी, यानी कि स्टार फॉर्मेशन भी बढ़ जाना चाहिए. और इसका नेगेटिव इफेक्ट भी हो सकता है बिकॉज जैसे हमने देखा, जेट दे हैव अ लॉट ऑफ एनर्जी एंड ऑल दिस एनर्जी दे जस्ट थ्रो इट इन देयर एनवायरनमेंट. सो वो एनर्जी काइनेटिक एनर्जी होगी, थर्मल एनर्जी होगी, तो जिसकी वजह से उन रीजन्स का टेम्परेचर बढ़ जाएगा, वेग बढ़ जाएगा. तो और उस बढ़ने की वजह से वो कोलैप्स, ग्रेविटेशन कोलैप्स होने नहीं देंगे, एंड उसकी वजह से स्टार फॉर्मेशन कम भी हो सकता है। तो ऐसा ही एक एग्जांपल पाया गया है एक रिसेंट स्टडी में, हेनीस 210, तो जिसमें आप देखेंगे, सो दिस इज अ ड्वार्फ गैलेक्सी, स्मॉल साइज गैलेक्सी, एंड आप जैसे इस पिक्चर में देख सकते हैं, ये सेंटर में ब्लैक होल है और उससे दोनों डायरेक्शन में आउटफ्लोज लॉन्च किए गए हैं, एंड आप देख सकते हैं कि इस आउटफ्लो के डायरेक्शन में यहाँ पर स्टार फॉर्मेशन ट्रिगर हो चुका है, जिसे एच अल्फा जनरली वेवलेंथ में देखा गया है। तो ये दिखाता है किस तरह से प्रेजेंस ऑफ एनी आउटफ्लो या फिर एनी जेट और मे बी आउटफ्लो फ्रॉम द सेंटर ऑफ द गैलेक्सी, so it can trigger star formation in the system. दूसरा है, ऐसा भी पाया गया है कुछ सिस्टम्स में जहाँ पर मेनली जेट्स इंक्लाइंड होते हैं, उनकी उन गैलेक्सीज की जो एमिशन मॉर्फोलॉजी है वो डिस्टोर्टेड पाई गई है, यानी उसका उत्सर्जन का जो आकार है उसमें कुछ तरह का विरूपण पाया गया है, जैसा आप इस पिक्चर में देख सकते हैं। सो ये NGC 3393 एक गैलेक्सी है, एंड ये उसकी इमेज ऑप्टिकल इमेज है, बट इन द आयोनाइज्ड O3, so it is the ionized oxygen state, and so you can see, so जो रेडियो कंटूर्स दिखाए जा रहे हैं आपको व्हाइट कलर से, so this is the path of the jet, and जो S shaped आप मॉर्फोलॉजी देख रहे हैं, so this is the distortion that I am talking about. so ऐसा माना जाता है क्योंकि जेट्स वो बहुत ही स्ट्रांगली इंटरेक्ट करते हैं अपने एनवायरमेंट से, so they can actually create pressure in the gas, and also can, due to their outflows, strong outflows, they can push the gas and can distort the emission morphology to give it a shape something like this. एंड तीसरा जो और आखिरी जो है वो मैं बात करूंगी कि जेट्स कैसे अपने एनवायरनमेंट या अपने गैलेक्सी की गति की, यानी डायनामिक्स काइनेमेटिक्स को अफेक्ट कर सकते हैं, जिसके लिए मैंने एग्जांपल लिया है इसका टी कपेजियन। टी कपेजियन इसे इसलिए बोला जाता है, जैसे आप देखिए ये इमेज दो फिल्टर्स में है, जो ब्लू रीजन आप देख रहे हैं वो है हबल आई मीन ऑप्टिकल इमेज, एंड जो आप ये रेड कलर देख रहे हैं, तो दिस इज द रेडियो इमेज। तो आप देख सकते हैं, एंड दिस रेडियो इमेज एक्चुअली इट फॉलोज द जेट। तो आप देख सकते हैं कि ये जो रेड है, इट सीम्स लाइक अ कप, सो दिस इज अ कप एंड इट इज इट्स हैंडल, सो इसलिए इसे टी कप एजेंट बोला जाता है। एंड अगर आप इसका ये इमेज देखें इसके वेलोसिटीज का, तो आप देखेंगे कि ये जेट है, एंड इसके आसपास के रीजन में जो वेलोसिटी डिस्पर्जन है, जिसे आप यहाँ से देख सकते हैं, सो इट इज़ वेरी हाई वेलोसिटी डिस्पर्जन, यानी वेग का फैलाव बहुत ज़्यादा है। सो इस तरह माना जाता है, जैसे हमने सिमुलेशन में भी देखा कि जेट्स अपने आसपास के रीजन्स का वेग को भी बहुत ही सिग्निफिकेंटली अफेक्ट कर सकते हैं, एंड बहुत ही मतलब स्ट्रांगली प्रभावित भी कर सकते हैं। तो इस तरह के इंडिकेशन भी बहुत सारी गैलेक्सीज में पाए गए हैं, एंड दिस इज जस्ट वन एग्जांपल ऑफ दैट। So what is the take home message from my talk? And so this is that कि black holes at the center of the galaxies वो active हो जाते हैं, and they can lead to outflows, jets and winds. So and if you look at jets, so this is an example of one galaxy, Centaurus A. So how these jets affect the galaxy in three different ways mainly. So first है जिसकी मैंने बात की, star formation. So उसका भी दो तरह के इफेक्ट हो सकते हैं, पॉजिटिव एंड नेगेटिव। एंड देन एमिशन मॉर्फोलॉजी, गैलेक्सी के उत्सर्जन के आकार को भी प्रभावित कर सकते हैं अपने इंट्रैक्शन की वजह से, और गैलेक्सी की गति की यानी काइनेमैटिक्स को भी इफेक्ट कर सकते हैं। सो दैट्स ऑल फ्रॉम माय साइड।
Thank you, Meenakshi. It was really a wonderful talk. And again, as you said, the numbers are important. We could actually get a nice feeling from the huge numbers that you had in your presentation. So thank you so much. So we'll see if there are any questions from the viewers.
मीनाक्षी, धन्यवाद आपके सुंदर व्याख्यान के लिए, और हिंदी में खासकर आपने मतलब ये काफी कठिन होता है, जो कि गणित की काफी चीजें हैं और एस्ट्रोफिजिक्स की भी काफी सारी टर्मिनोलॉजी होती है, तो आपने उनको सहज तरीके से सबके लिए प्रस्तुत किया, इसके लिए फिर से धन्यवाद सबकी तरफ से। हमारे पास एक प्रश्न है, क्योंकि आपका व्याख्यान जो है उसमें आपने दैत्यों का रेफरेंस तो दिया था, लेकिन दैत्य ये ब्लैक होल होंगे ये शायद लोगों को अचंभा लगा होगा कि इतने बड़े ब्लैक होल हो सकते हैं। तो इन प्राची पाटिल है, उनका पूछना है कि ये ब्लैक होल कितने बड़े हो सकते हैं और इनका क्या कोई अंत होता है?
ओके, सो ब्लैक होल्स एक्चुअली वो बहुत ही मैसिव स्टार्स, आई मीन सो ब्लैक होल्स का निर्माण असल में स्टार्स के आई मीन एंड ऑफ लाइफ टाइम ही होता है, एंड वो बहुत ही मैसिव, जैसे हमारे जो सेंटर ऑफ द मिल्की वे का जो ब्लैक होल है, हम मानते हैं कि वो ब्लैक होल है, उसका मास 10⁶ सोलर मास है अराउंड, सो दैट इज एक वेरी ह्यूज, बट तो वो इतना मैसिव नहीं है। बट जो बाहर बहुत सारे ऐसे गैलेक्सीज में ब्लैक होल पाए गए हैं जिनका मास अराउंड 10⁻³ 10 close to and maybe 10 to the power 8 solar mass. So it can be very massive.
तो हमारे आकाशगंगा के केंद्र में एक मतलब सूर्य से भी 10 लाख गुना मास रखने वाला ब्लैक होल है, ऐसा आपका कहना है? क्या बात है, मतलब ये तो अचंभित करने वाली चीजें हैं। और ऐसे बड़े बड़े नंबर्स को इसीलिए एस्ट्रोनॉमिकल नंबर्स कहा जाता है। एस्ट्रोनॉमी में हमेशा ही इस्तेमाल होते रहते हैं। तो हम अब ये करेंगे कि आगे कोई प्रश्न है क्या, एक बार देख लेता हूँ। और हाँ जी, एक प्रश्न हमेशा होता है कि जब किसी कृष्ण विवर के आसपास मैटर होती है तो उसमें खींची चली जाती है। कुछ लोगों का ऐसा भी सोचना होता है कि गैलेक्सी उसके अंदर ना चली जाए, जैसे मतलब आपने कोई बेसिन में अगर पानी जमा किया हो, उसके नीचे का प्लग खींच दिया तो वो पानी उसमें पूरा चला जाता है, तो ऐसी होने की संभावना है क्या?
उसके लिए एक्चुअली ब्लैक होल का एक रेडियस होता है, इवेंट होराइजन। सो व्हाटएवर पासेस दैट रेडियस ऑब्वियसली इट्स गोना फॉल इनसाइड इट, बट इतनी संभावना नहीं होती है बिकॉज देयर इज एन एक्सटेंट कि कितने रीजन तक कर सकते हैं। हाँ, बट so actually till now we are safe, it's not going to happen, or obviously we have a very large galaxy.
जी जी जी। हाँ, तो मतलब इसके तुलना में गैलेक्सी इतनी बड़ी है कि ये होने की संभावना कम है। और जैसे आपने अभी दिखाया, ये तो एक अलग ही चीज थी जो आपने दिखाई कि ब्लैक होल के इर्द गिर्द से चीजें बाहर की तरफ आ रही है, जो कि एक मतलब साधारण हमें पता नहीं होता है, हमें लगता है कि ब्लैक होल सबको खींच।
हाँ, तो ये जो आउटफ्लोज हैं ये ब्लैक होल के अंदर से नहीं, ये ब्लैक होल के आसपास जो डिस्क बनती है, जैसे वहां से विंड्स, क्योंकि एक्चुअली जो आसपास एक्रीशन डिस्क बनती है जिससे वो मैटर एक्रीट करता है, तो वहाँ फ्रिक्शन की वजह से, बिकॉज वहाँ वी हैव आयोनाइज्ड गैस जिससे ब्लैक होल पुश कर रहा है, तो आयोनाइज होने की वजह से, वहाँ फ्रिक्शन की वजह से ये आउटफ्लोज क्रिएट होते हैं। एंड जो जेट है वो होता है मैग्नेटिक फील्ड की वजह से, क्योंकि जो आयोनाइज्ड गैस है ये मैग्नेटिक फील्ड के साथ मूव करती है एंड फिर वहां से इजेक्ट होती है एक ऐसे पाइप की तरह। तो ये जो आउटफ्लोज हैं ये ब्लैक होल के अंदर से नहीं है, ये ब्लैक होल की सराउंडिंग से हैं।
धन्यवाद ये क्लियर करने के लिए, ये जरूरी है ये जानना। तो फिर से धन्यवाद आपका यहाँ पर आने के लिए और ये एक बहुत ही सुंदर व्याख्यान तैयार करके सबके सामने प्रस्तुत करने के लिए। आपने हमारे लिए कुछ वीडियोस भी दिए हुए हैं, तो चलिए हम मीनाक्षी का धन्यवाद करते हैं और ये इन वीडियोस को देखकर अगले व्याख्याता के पास चलेंगे। धन्यवाद मीनाक्षी।
श्योर।
तो अभी हम एक वीडियो देखेंगे, इसमें जैसे उन्होंने बताया कि ब्लैक होल की जो पहली इमेज बनाई गई थी वो कैसी बनी, इसके बारे में ये वीडियो है, तो जल्द से देख लेते हैं।
This is the giant elliptical galaxy Centaurus A. Radio and X-ray images reveal features associated with jets driven by the galaxy's supermassive black hole. Now, the Astronomy project has provided the best ever view of these jets. In this radio image of the galaxy's core, the black hole is invisible, but the jets show in great detail. Features as small as 15 light days across can be resolved. The powerful jets feed vast lobes of radio-emitting gas that reach far beyond the visible galaxy.
तो ये एक सुंदर वीडियो था ब्लैक होल के चित्र के बारे में। और आगे एक और सुंदर वीडियो है जिसमें हम इसके पहले का जो व्याख्यान था, जो नेब्यूला यानी आकाश में दिखने वाले निहारिकाएं या गैस क्लाउड्स के बारे में था, उनको ब्लैक होल से कनेक्ट करता है और आपको एक ऐसे नेब्यूला के अंदर से एक टूर करवाता है। तो चलिए देखते हैं ये एक सुंदर सा वीडियो।
This composite of data from NASA's Chandra X-ray Observatory and the Hubble Space Telescope is another look for NGC 6543, better known as the Cat's Eye Nebula. This famous object is a so-called planetary nebula that represents a phase of stellar evolution that the Sun should experience several billion years from now. When a star like the Sun begins to run out of fuel, it becomes what is known as a red giant. In this phase, a star sheds some of its outer layers. a fast wind streaming away from the hot core rams into the ejected atmosphere, pushing it outward and creating the graceful filamentary structures seen with optical telescopes. In the case of the cat's eye, material shed by the star is flying away at a speed of about 4 million miles per hour. The hot core left behind will eventually collapse to form a dense white dwarf star. Chandra's X-ray data of the cat's eye, which are seen as blue in this image, show that its central star is surrounded by a cloud of multi-million degree gas. Structures in optical light by Hubble are colored red and purple. By comparing the two, astronomers determined the chemical composition in the region around where the hot gas is found is like that of the wind from the central star, but it is different from the cooler outer material.
तो इस प्रकार हमने देखा कि एक सुंदर दृश्य जो हमें एक नेबुला के अंदर दिख सकता है उसका एक नज़ारा, और ये था आपके लिए खास एक हिंदी प्रेजेंटेशन जिसको हमारे पास लाई थी, हमारे सामने लाई थी मीनाक्षी मोहन जी। तो अभी हम अगले व्याख्याता की ओर चलते हैं। सो लेट मी इंट्रोड्यूस Dr. Vishal Upendran, who is also a research scholar at IUCAA, and he is a very, would say, enthusiastic person who loves to speak to everyone about his work. And he has compiled a set of slides and a lot of information. In fact, he has hand drawn a few things, so I will not say too much to give up the suspense, but that's the kind of dedication that he has given to bring us this particular presentation. Now, I will, of course, mention that we are doing this live on YouTube. So all the people who are watching this while we listen to the talk, please make sure that if you have any queries that come to your mind, if you have any doubts that cross it, please put them in the live chat. We have all our speakers around and other scientists around who can answer them right there in the chat. We are also seeing this on Facebook and Twitter. So आप वहाँ भी अगर ये व्याख्यान सुन रहे हैं, if you're listening to all this on these various social media channels, make sure you put in these questions, because this is your chance to actually interact with a practicing scientist who is here, who has taken out time to come to you today on this online celebration of National Science Day with IUCAA. So without further ado, let me bring to stage Vishal Upendran and ask him to deliver this talk, which tells us about the many ways to learn about the universe. Vishal, stage is yours.
Thank you, Samir. Let me share my screen. Okay. So I hope now we can see my screen in slideshow. So thank you, everybody. Thank you, Samir, for inviting me. And I hope everybody is enjoying this wonderful program that we and the Science Center team has put together for the National Science Day celebrations this year. So before we start our talk, let's go to a small story. Okay. Yeah, let's start with a small story. Once upon a time, there were 4 blindfolded people, and these people were wandering across the cosmos, and they encountered a mysterious beast. Now, they didn't know what this mysterious beast was because their primary source of gaining information was through eyesight, and they were blindfolded. So what did they do? They went and touched various parts of the beast, or what they thought was various parts of the beast. So that's the beast there. And each person touched this beast to figure out what this beast actually was. So one person touched a part of this beast and sort of figured out there's a pipe-like thing it has, and maybe it's a snake. The second person touched the beast and found it was cylindrical and sturdy, and he couldn't lift it. So he thought maybe this is not a beast, it's a tree, and it's a trunk of a tree. The third person, this person touched another part and found out it's flat. There's no cylindrical shape here. It's just plain, hard, flat. And he thought, come on, this is not a living thing. It's a wall. And the final person, when they touched this thing, they found out it is actually very thin and it looks like a rope. So each person had a different idea as to what this beast is. They couldn't figure out. They sat arguing, discussing, debating, until they came to realize they had just touched different parts or different aspects of this beast. So the beast was one, but then these were different people and these were different aspects. And so they came together to figure out what this beast was. So what is this animal? This animal, if you know the story, was an elephant. So when you touch the trunk of an elephant, it looks as if it's more like a snake. If you touch its stomach, its belly, it's really hard like a ball. If you touch its tail, it feels like a rope. So this is a very important story in the sense that in our Indic philosophy, we know truth is one, but the wise know it as many. We see what we see is not possibly what is actually happening, but in there are multiple aspects to it. So why am I telling you this story? This is basically how we do science. What we basically have is an astronomical object. So think of this to be any astronomical object. It's just doing its own thing, and I don't know, giving rise to some flares or something. And what we want to study is the various processes that occur in this astronomical object. So the physics of this astronomical object is what we astronomers generally study. And so to study this object in the first place, you must know that this object exists in the first place. And so the object must send us a message to know what is happening. Only then can we infer its existence. So fine, the object has sent a message, but how do we receive it? Do we have receivers? What we basically do is we basically measure a bunch of particles. We measure these particles and to figure out what the message these objects has sent us. Now, as astronomers, the most ubiquitous set of particles that we have are the photons or light particles. So light particles is how we measure, or light is how we measure or look at various things in the universe. So let's look at light now. Light has what is called a spectrum. So this spectrum is basically, if you consider light to be a wave, this wave has a wavelength, and this wavelength can be multiple orders of magnitude, as it's called. This wavelength can be as large as a set of buildings or as small as the nucleus of an atom. And so depending on the wavelength, we see different things. And humans don't see all the wavelengths of a light. All we see is the visible aspect, only the visible part. This is a very small wavelength that we see. We don't see anything else. And that is how we infer various things about the world. Now, different processes gives rise to light at these different wavelengths. And these different processes have a characteristic temperature or energy. And what generally occurs is shorter the wavelength, more the energy. So this temperature graph shown here, if you want to generate, let's say, gamma rays, which are extremely energetic, you need a lot of energy for generating gamma rays. Whereas in radio waves, you don't need that much energy. So from radio to microwave to infrared to visible, ultraviolet, X-ray, and gamma ray, that is how the spectrum goes. And that's how much energy you keep requiring. The more shorter wavelength you have, the more energy you require. So again, what's the point of talking about light? Because we study light, right? So let's do a thought experiment as Einstein would do. And that's how we figure out various things. Let's do a thought experiment involving two stars. There are two stars, A and B. And this is you. You are having a visible telescope. Maybe it's in your backyard, or you have come to a science center and looking at these two stars. And you figure out in some way that A is brighter than B in visible light. Now imagine that there is an alien, this little green man, somewhere in the outer space, in some other planet, looking at the same two stars, but now in X-rays. Now, do you know, or can you comment which star is brighter in X-rays? It's not so easy. It's like saying I have a tail, I have a rope, and that's like a tail of a beast. Now this beast is an elephant. We all know that's not true. Various animals have tails, right? So you can't infer just through one observation. So it's not so easy to say which of the stars will be brighter in X-rays. So what we require is multi-wavelength astronomy. So multi-wavelength astronomy means you see an object in different wavelengths of light. So let's understand this concept with one example, the Crab Nebula. So here's the Crab Nebula, a beautiful picture of the Crab Nebula. So Ishita must have talked to you about the Crab Nebula, and this is the picture I took from Hubble, and it's extraordinarily beautiful. Now, the Crab Nebula is very interesting because this was actually a star more than 1,000 years ago, but now it's no longer a star. it underwent a supernova explosion in 1054 AD, which the Chinese astronomers recorded as a guest star, and they implored their king to take care of this guest star so it may not curse us. Now, the remnant of this explosion, of the supernova explosion, is what is today we see as the Crab Nebula. Now, what we'll do now is we'll take 6 astronomers and study this object in different wavelengths. So as we keep adding one more astronomer to the set, we'll try to figure out what all processes that occur in this object and see if we can get closer to the truth of what this object is. That's the general idea. Okay, let's move to the visible light image. So if you take a telescope and look at the Crab Nebula just from the ground, let's say, of course, this is taken from Hubble because Hubble is amazing. This is what you see. The Crab Nebula looks astounding in this picture. And there are multiple observations you can make. The first thing we know, the first question we should generally ask is, what is the process that gives rise to this emission? So this is just gas, composed of different ions, which is giving rise to this emission. So if I'm not wrong, this is possibly sulfur or oxygen emission that's giving rise to this light. So which means that it is tracing the presence of different ions present in this nebula. And again, you must have seen Ishita's talk regarding this. What can we infer from this image? The first thing we can infer is that the shell that you see around, all the shell of gas that you see around, is basically the shell of the star that underwent supernova. So the outer layers of those, if you know what a supernova is, it's basically a star just explodes. The outer layers of the star just expand outwards violently, whereas the inner core of the star just compresses and becomes a dot. Now this doesn't become a dot, but it becomes really small. So this outer shell of the star is what is expanding today as the outer shell of the Crab Nebula. And when this shell interacts with what is called the interstellar medium, it gives rise to what are called gas instabilities. Because of these, you find these filament-like structures that are marked here, wherein the gas is actually flowing inwards into the nebula itself. And this is so just by looking at this one wavelength, we can infer so many things about what this nebula is actually composed of. Now, this is something that we see in visible light. What happens if we go to, let's say, longer wavelengths, let's say in infrared? So if you go to infrared, this is the kind of image we see. So infrared, you can see that the image is blurred, and that's because the instrument is different. It is Spitzer this time. It's not Hubble Space Telescope. So resolution is poorer, but then you can see that the structure itself is slightly more different when compared to what was seen earlier. And this structure is different because infrared traces what is called the dust emission. So by and large in astronomy, if you find infrared emission from somewhere, you can be kind of sure that there is a lot of dust that is giving rise to this emission. Now, how does this dust give rise to infrared emission? So what happens? So again, you should always ask, what is the process that gives rise to this emission? So the process that gives rise to this emission is you have ultraviolet light that shines on a dust grain or dust grains, and these dust grains get really hot, and then they give rise to infrared emission. So this is how infrared emission occurs. So they trace the presence of dust particles. So by adding one more wavelength to our existing wavelength repository, just again visible light, we can see that Crab Nebula not just has just gas, it also has dust. And so we can always keep asking, right? What happens if we go to longer wavelengths? What happens if we go to radio? Radio image again is very different. You can see that this filamentary structure is sort of persisting. The structure now is quite different. And again, so now that I've told you, we'll ask the question, where does the emission come from? What is the process that gives rise to this emission? The process here is what is called synchrotron emission. So the name sounds really fancy because the process is also very fancy. What happens is you have a magnetic field line there, and you have an electron that goes around in this magnetic field, and the deceleration of this electron gives rise to radiation. And that radiation is what we see now as synchrotron emission. So basically, what this emission traces is it traces the magnetic field lines present in the Crab Nebula. So we are not just seeing gas, we are not just seeing dust, we're also seeing the presence of magnetic field. And this is a long-range magnetic field. These are pretty large structures, right? So it's a very long-range magnetic field. So these are 3 key observations that we now have and 3 key inferences that we have. So like the ever inquisitive human mind, we again ask, What happens if we go to shorter wavelengths now, or more energies? What happens if you look at ultraviolet? We see something very different, or is it very consistent with what picture we have? So similar to the elephant example, we see something very different now. All of the filamentary structures are gone. All we see is a blob of a blob kind of structure, and there are a lot of stars in the background. So this ultraviolet emission occurs because of the existence of hot gas. If the gas is really hot, it emits an ultraviolet. And what you also see is these are the hot stars in the background. These hot stars in the background are seen in this ultraviolet image because they are young stars which are generating a lot of heat, and this heat is predominantly seen in ultraviolet. Now, what you can also see, if you look very carefully near the center of the Crab Nebula, we can see that there is some disk kind of structures very hazily being seen. So is that a disk there, or is there something going on in the center of the nebula? Let's figure it out. Let's look at much shorter wavelengths or higher energies and see what happens. So if you look at X-ray, let's say, the X-ray image is breathtaking. Hold your breaths. This is what the X-ray image looks like. This is a very, very different structure when you compare it to all of the observations that we have had. It is very different from radio, optical, infrared, and even the ultraviolet. So the first question now we should ask is, what is the process that gives rise to this X-ray emission? So the process is what is called Bremsstrahlung. It's a very handful word. It's difficult to pronounce. Bremsstrahlung is a German word which means breaking radiation. If we have a very hot gas, it can emit through this process. It's a very specific process called Bremsstrahlung. So what happens in this process? You basically have a bunch of really, really fast electrons that go through a barrier. And as they go through a barrier, they decelerate. And as they decelerate, they release a lot of energy. And all this energy is what we see now as Bremsstrahlung in X-rays. So what happens here, so what you can infer from this picture is that there's a lot of very fast moving electrons that are suddenly being stopped, or the speeds are getting reduced. So that's what is happening in this whole picture, which means that these electrons were accelerated to that energy in the first place by something or some mechanism. And clearly, it's not some random process, because you can see some very nice structure in this image. The first thing you can see is that there is a central dot there. This central dot is a remnant core of the star. So in the other wavelengths, we are seeing the outer shell of the star, but in this image, we are seeing the central core of the star. This core of the star is a driving pulsar that has a lot of magnetic field again, and it's also rotating very fast. And this is what is giving rise to these really hot electrons. And this rotation is also symbolized in some sense by this swirling disk of plasma that's going around the pulsar. And clearly, you also see that there is a jet kind of structure that's coming out of this pulsar. And this jet is aligned along this axis approximately. So we were looking at very large scale structures in the earlier images. And that was all of the outer atmosphere of this old star that existed at some point in its time. But now you're looking at the central core region and the way it dominates the dynamics in the whole system. Simply because it has magnetic field, it's going really fast. There's a lot of gas and dust present all around. And finally, you can also ask, what happens if you look at it in gamma rays? So don't expect something impressive, because this is what the Crab Nebula looks like in gamma rays. It's a dot. And it's a dot because if you want to get gamma rays, you need a lot of energy. So much energy that there are also all sorts of particle processes that occur. But then we know that the pulsar is rotating really fast. There's a lot of magnetic field present in the pulsar. So that is going to do something and give rise to these large energies. And now think of magnetic field to be like a bunch of wires. And if you take a bunch of wires and if you rotate them really fast, you will expect them to get tangled up. And when they get, and magnetic field lines are not just wires, they are live wires. They have current flowing through them. So if they get tangled up, they'll also get short-circuited. And when they get short-circuited, they'll give rise to flares, which means there'll be large bursts of energy arising from the interaction of magnetic field. And that's something we see. There is a normal state to the Crab pulsar, and there is a flaring state to the Crab pulsar, wherein the emission drastically increases. And because we found both of these states of the Crab pulsar in gamma rays, we can estimate that, these regions, this crab pulsar must have really strong magnetic field. It must be rotating really fast. That's going to get tangled up like crazy and give rise to these flares. These kinds of flares occur not just in an object like pulsar, they also occur in the vicinity of black holes, and they also occur on the very own sun. So these are very similar to solar flares that occur in the sun. So if you put all of these pictures together, all of the 6 astronomers have come together to debate on what the actual truth is, and they find out an image something like this. They see that at the center there is a pulsar which is driving a lot of plasma in the form of jets, in the form of disk. Is also driving winds, and it is also having a lot of magnetic field that is sort of controlling the overall dynamics of the region. But then all of this gas is hot, but as you move outward, you see that the gases also start getting colder, but there's also dust that forms a lot of dynamics. And finally, you see that because of the interaction of this expanding bubble with the interstellar medium, there are also instabilities that occur, which causes plasma to flow back into the system itself. So this is the kind of amazing process that goes behind what apparently seems to be a simple object like the Crab Nebula. You can now ask a new question. Are photons the only particle we can measure? I mean, we have talked about photons all along because astronomers are very comfortable with photons and we see stuff, right? But are photons the only thing that we can measure? Does the object only send us photons and not anything else? The answer to that is actually no. There are other particles that come out, and these we can see other particles through what is called multi-messenger astronomy. So photons are one form of messengers, and you can have multiple messengers that can come from different objects. So what is multi-messenger astronomy? On one hand, you have this photon here, like Thanos. It's inevitable because that's how we see. So it has no charge, it has no mass, it's all energy. And any form of electromagnetic interaction, for example, gives rise to photons. So if you have plasma, if you have magnetic fields, if you have electric fields, photons will be there. But on the other hand, you also have something called neutrinos. So these neutrinos basically have no charge. They have very small mass, but they come in multiple flavors. And these neutrinos are formed when you have particle reactions. So if you have nuclear reactions, for example, depending on what particles participate in these reactions, you can have different kinds of neutrinos or different flavors of neutrinos. So different kinds of particles tell us about the different kinds of physics that go behind a given system. So what do we learn from neutrinos? So to know this, we had to go back a couple of years, a couple of decades actually, to 1987. So in 1987, on this date, neutrino detectors across the world detected a surge of neutrinos in the detectors. So you can see here that the neutrino count has gone up. There are no beautiful images here. I'm so sorry, because that is all neutrino physics has offered to us as of yet. There are good observatories coming up, but this is what we had at that time. You could only count the number of neutrinos that come in. But we could estimate possibly in what direction these neutrinos came in. So we have some estimate. So what people did, or what astronomers did, was to point the telescopes at the approximate sky location where the neutrinos possibly came from. And then 3 hours after this surge was detected, a star went supernova there. And astronomers could capture the death of a star for the first time in history. And we see the star, the supernova, like this today. So the Crab Nebula, may possibly just after the explosion had occurred, would have seen something like this. And here you can see what is called the microwave emission from the center. That's by and large, it's a dust emission. And then on the sides, you have the X-ray and the X-ray in the visible image. And these are pretty hot plasma. So the bubble is just expanding out. So as it's expanding hot, it's really hot now. So it's not become really large now. It's really hot since the supernova just occurred, right? And in astronomical time scale, 30 years is nothing. It's just a small fragment of time. And we know this supernova today as 1987A. And by studying neutrinos, by continuously monitoring how much neutrinos is going through, we can get a handle on the supernova physics. Because remember, neutrinos have flavors. So different kinds of supernovae may have different kinds of particles participating in these reactions, and that will give rise to different kinds of neutrinos. So that's the amount of information that we can get just by looking at another messenger from the universe. So how much more can we study? The human mind is something that always thirsts for knowledge. So you always want to know more about our surroundings, about the cosmos. So how much more can we study? So first thing is photons just don't have energy. They also have something called polarization. And depending on context, polarization can give you information about various things. For example, in solar physics, if you look at polarization, it can tell you something about the magnetic field that's present in the sun. And if you look at the CMB, for example, the cosmic microwave background, you also have some polarization expectations, and so on and so forth. You can also look at different energies of the neutrinos. So just like how gamma ray photons require a lot of energy, neutrinos of specific energy also require particles of specific energies. And by detecting neutrinos of different energies, you know what kind of stuff is happening at different locations. You can have other messengers too. For example, you can have gravitational waves. So you might see the gravitational wave demo setup at the campus today later on in the walkthrough, and you can see the gravitational waves from yet another messenger from the cosmos to help us detect what's going on. And finally, there might be something more exotic lurking for us out there in the cosmos and waiting for us to make a detector and see it. But regardless of what we see or what we do, always remember that we are starstruck. Thank you.
Okay, so star stuff, that's what we are. And thank you, Vishal, for this lovely and very catchy presentation. We are seeing comments from everywhere in India that they are liking it, and we have so many curious questions about various things here. I'll quickly get to the questions because otherwise we run out of time. So one of the questions is that also I was wondering about, so you're showing Crab Nebula a lot. Thankfully, you showed 1987 in the end, and the Crab has been shown by others also. So why is Crab so important, and why does it feature so much in these presentations?
Crab is just so beautiful, right? I mean, that's the first answer I would want to give. Crab is also what is the first object in the Messier catalog. So for those of us who have been doing amateur astronomy for quite some time, the first object that you want to find is the Messier 01, that's the Crab Nebula. And it's also the fascination that this is one of the earliest recorded supernova observations in history of mankind. But as much as we know, there could be others too. So we have a specific fascination for Crab because we have seen, our ancestors have seen it explode with their naked eyes. It was really bright. It formed a new star in the sky. And now we can have pointed telescopes and look at all these wonderful processes that go about. But yeah, Crab is beautiful. That's the answer.
So Crab is like this superstar. You can't ask why this superstar is in so many movies because they are the best.
Exactly.
Right. Okay, good. And so another question which I'll put in a different way is that in various mythologies, like Indian had the messenger of gods, Narad Muni, and Greeks had Mercury as the messenger. Now in the modern times when science really discovers the things, we have photon as the carrier of information. So the question here is that how does the photon fly?
How does the photon fly? The photon always flies. It doesn't stop. So Vivekanand said something, arise, awake, and stop not until the goal is reached or something. It's very similar. Photons will not stop. They'll always keep going on. They can't stop actually. Special relativity forbids them from stopping because they have zero mass. They can't stop. So they always keep flying. And you can think of photon as to be a self-sustaining system of electric and magnetic waves. So electromagnetic radiation is why is photon called. So it keeps flying all the time, but then it has to be generated at some point. So the generation part is where different processes come in. And that's what I try to emphasize in this talk.
Right. So it's in the way you look at photons, they're flying or they're just motions of fields, variations of fields. That's lovely. So fields bring me to another question, which is asked by Prachi Patil. How are magnetic fields formed in the Crab or any other nebula?
That's a very good question, actually, because why would you expect magnetic fields to be there in the first place? The question actually is interesting because the star that gave rise to the supernova explosion, that had some magnetic field. And that magnetic field, so that star just got compressed. And all that magnetic field that was there in the star got trapped. And so it got really strong. Where does that magnetic field come from is something we don't know. there are a lot of models and a lot of theories. Maybe convection in stars is giving rise to these strong fields, but why did magnetic fields come in the universe in the first place? I don't know, Professor Kandaswamy might answer this, if he is available, because that's his field of work. But then the star, at least for our context, the star that gave rise to supernova, that had a lot of magnetic field. And once it exploded, the magnetic field stayed with it. It didn't go out anywhere. And it's contained in the plasma that gives rise to the star. So that's how you get the magnetic fields out.
Great. Yeah. So it's still something which people may be able to research. So it's not like all answers are known in astrophysics. So all these
absolutely.
All the youngsters watching, please remember there are open questions, and we are not just presenting to you finished books. They are open books, and many of these question marks there are there to be studied more. I'm just looking for more questions online. Please feel free to put in questions here on the chats wherever you're watching, either on YouTube, Facebook, or Twitter. Please put in your questions here. So while we wait, maybe I'll ask a personal question for you. What kind of inspired you to come into astrophysics?
That's a very difficult question to answer because as a kid, this is the personal answer. So when I was in class 1 or something, first or second standard, somebody gifted me the second-hand book, which is sort of like a dictionary. So for each alphabet, there would be something that starts with A, something that starts with B. And there was a section on planets for the letter P, and the solar system for the letter S. And I was fascinated by reading this book. And I was asking my dad, what is this? I was asking my mom, what is this? What are these planets? What is this star? What are these stars? And then that sort of developed. And then we studied physics at some point in the future. And that's how I got into astro. So this is like a lingering love. You look up in the skies and you always ask, what are these things that keep twinkling? Of course, you can get a lot of answers, but then it's also the physical aspect as to various processes that give rise to what you see. And so the beautiful pictures were the starters in class 1, but then now it's more of the magnetic field data that inspires me in my research.
Nice, very, very lovely story there. Lovely journey from very basics and fascinating stuff to equally fascinating stuff, but which looks very different now.
Absolutely.
Right. But thanks for taking out this time and all your effort in making this beautiful presentation here. You have given us one more video to show to everyone. So what we'll do is we'll play that again after we thank you and take your leave. So over to the video, which shows something which is already mentioned on this screen here about neutrinos, how they were discovered and how they are also messengers of astrophysics. So let's have a look. Thank you, Vishal.
Yeah, thank you.
The IceCube Neutrino Observatory at the National Science Foundation's Amundsen Scott South Pole Station in Antarctica, the world's largest neutrino detector. A cubic kilometer of clear ice, armed with more than 5,000 light sensors arranged in a grid beneath the South Pole. One of its missions is to help solve a 100-year-old riddle. Where do cosmic rays come from? To do that, it looks for cosmic sources of high-energy neutrinos. Cosmic rays are high-energy charged particles born like neutrinos in some of the most cataclysmic events in the universe. But where cosmic rays are knocked around by the powerful magnetic fields that permeate interstellar and intergalactic space, neutrinos are ghostly subatomic particles that can travel usually unhindered in a straight path through galaxies, stars, and anything else nature throws in their path. So find a source of neutrinos, and you might have found a source of cosmic rays as well. The challenge? Neutrinos rarely interact with matter. But whenever a neutrino does happen to collide head-to-head with atomic particles of an ice molecule inside or near the IceCube Observatory, it creates secondary particles that, in turn, create a cone of blue light that IceCube's sensors detect. And that's what happened on September 22, 2017. IceCube's alert system flashed coordinates of a potential source of that neutrino to many telescopes worldwide to follow up with observations. And multi-messenger astrophysics went to work, scanning these coordinates for more information. Fermi, a NASA gamma-ray space telescope which had already observed enhanced gamma-ray activity from a blazar at these coordinates, and the Major Atmospheric Gamma Imaging Cherenkov Telescope, or MAGIC, in the Canary Islands, looked in the direction the neutrino came from and detected a burst of high-energy gamma rays from the blazar. These converging observations could mean only one thing. The blazar was the source of that neutrino. A blazar is a giant galaxy with a massive, rapidly spinning black hole at its core, and twin laser-like jets of elementary particles and light that shoot out from the poles along the axis of the black hole's rotation. And it seems that one of those jets was oriented towards our planet Earth. Because this blazar produces cosmic gamma rays and neutrinos, we now have evidence of a source that produces cosmic rays as well, thanks to multi-messenger astrophysics that helped solve a 100-year-old problem and revealed significant insights into objects and events far more powerful than any we will ever witness on Earth.
So this was another beautiful video. So now we are done with 3 amazing talks. And here we have our 4th speaker. We welcome you, Anu. And yeah, you're mute. Okay,
Yeah.
thank you. Thank
Hi.
you. Hello. And I'm really fascinated and very excited to tell you all that she will be presenting a demonstration for us in this talk. And it is going to be a demonstration on what she actually works. So it will be really fascinating to see the lab around. So all of you can actually get a bit of a flavor where all these scientists sit and how their labs look and what instruments they have all around them and how do they work also. So Anu will be talking on optics, and then she will also have a bit of a flavor about fiber optics. So the basic thing will be fiber optics, and she'll be talking about an unsung hero, an Indian unsung hero, and that will definitely, I think, will fascinate us all. And this will also the talk will also consist of spectroscopical demonstrations that I just said. And we welcome you, Anu, and she's like a postdoctorate fellow in IUCAA, so you have another great speaker with you. So I think without any further delay, let's see the talk in the lab.
Thank you. Hello everyone. Today let's talk about light, its different aspect. Let's discuss about optical fiber cable, which has revolutionized our telecommunication and made its mark in different scientific and industrial areas. I'll be also showing you a demo of a fiber-fed spectrograph, which is a great scientific instrument for astronomy and astrophysics and various scientific disciplines. Now, first things first, why do we see things? Why do we see different things in the nature? So, the light, which is either reflected, emitted or scattered from an object, falls in our eye, and our eye forms an image of that object in our retina, which is processed by our brain, and we see things. Now, you might have seen in nature different colors. Now, even if you see a prism, when the light passes through it, it actually splits into a band of light, and this band of multicolored light is called a spectra. Because of the properties of light, the red and violet end of the light will not fall at the same place. Now, this is called dispersion. Now, we might have seen this band of light in different places in nature. Can you imagine few of them? So, say a rainbow or an oil drop which you see in the ground. You might have seen this multiple colors. Now, next question comes. You have a pink flower here, a yellow flower here. Why do you see things in that color? Why it should be pink? Why it should be yellow? So the reason is that the object, which is the pink flower, it actually absorbs every other light, every other band of light, and only emits or reflects back the pink color. The same for the yellow flower. Now, is it the only place you might have seen things? There is this candle, a burner, and a iron rod which is being heated up. You might have seen this. So there is some difference between these two. The pink flower you cannot see without sun or in night without your torch or whatever. But this candle and this iron rod you can see even in a dark room. Why? So the pink flower is a non-luminous object. It needs a object, luminous object, to shine light on it so that you can see it. At the same time, this candle or an iron rod is a luminous object. It can emit light on its own, and depending on the color of the light, you can actually say about the intensity, you talk about the properties of that object, how hot it is, in different aspects. Now you get an idea of these things. Now let's talk about spectra. So I told you in the beginning that band of light is called the spectra. Now you have a black body here, and then there is a cool gas which is absorbing some of the light. Now I told you when you make the light fall through a prism, it disperses or it gets split into various components. Now the light which is coming from the black body or the main luminous source, it is allowed to pass through the prism. Now what happens? You get the continuous spectra. But at the same time, the light which has started from the luminous object, and it has passed through this cool gas which is absorbing some of the light, and then it comes out. What do you get? You get something called the absorption spectra, where you can see some of the lines are black. You can see there is no light in those things. Now that is an absorption spectra. Now what if you take the spectra of this cool object alone, which is actually taking out some of that light? You see the light which is reflected or processed by that light, cool gas, which is the emission spectra. Now you have this different kind of spectra. What it means is, this is a unique thumbprint or a fingerprint information kind of thing about each of these bodies. Each of these gases, you can see they have different kind of spectra. They are very different. Each of them are very different. So what happens is, by this information you can actually know about a lot about that object you are studying. This is where the spectra is very important for various scientific fields, where you can actually study about the object. Now let us see a basic layout of a fiber fed spectrograph. There is a source, then there is a fiber which is feeding the light into the spectrograph. There is the lenses. See, it can be either a converging lens, as you can see here, or a diverging lens which diverges the beam. Then there could be a dispersive element which could be a prism or a grism. Now how the system works is, fiber feeds the light into the spectrograph. The first lens arranges the light for the dispersive element, and the dispersive element feeds the light into the imaging lens, and the imaging lens take it to the camera. And through the camera or a detector, you can actually see the spectra of whichever object you are trying to study. Now let us talk about certain properties of light, and also about the optical fiber cable, which is there as a very humble system in this entire spectrograph, but it is one of the remarkable inventions of our generation.
Hello,
so let us first study the properties of light. Light likes to follow in a straight line path. As you can see here, the light is shined through water into a screen through the air medium. So the light is entering and it is following in a straight line path. There is a bending of the light, but as you can see in this image, when the light is entering at a larger and larger incident angle, there will be a place where the incident angle I is greater than the critical angle of the light IC. So what happens then is that light bends. So I told you light goes in a straight line. Now you can see light is bending. Now we can use this property to actually manipulate light, to take it from one end to the other end in a way we like, because we are bending light. So see, now there is a light pipe. So the pipe what you are seeing here, it is actually taking the light from one end and it is coming out through the other end of the light pipe. So you actually bend light. You can now take this light pipe and feed light at one end and give it somewhere else. Can you imagine the use of such a thing? You can do enormous scientific things using this. When we talk about fiber optics, there is a person who needs to be mentioned in a great detail. That is Dr. Narendra Singh Kapani. He was an Indian-born Indian-American physicist known for his work in fiber optics. He is named as the father of fiber optics, and he was the first person to actually transmit an image from one end to the other end through fiber optic cable. Fortune named him as one of the 7 unsung heroes of the 20th century for his Nobel Prize deserving invention. He was awarded India's Padma Vibhushan in 2021, and he served as an scientific advisor to the Defence Minister of India under the Jawaharlal Nehru government. Now, what is the advantage of this fiber optics cable over other kind of communication systems? We have this copper wire based coaxial or twisted cable communication systems, but the fiber optics cable surpasses them in great level because of the bandwidth it can transfer, and also silicon dioxide is the next abundant material on earth after oxygen, and fiber is made out of silica, so it is very sustainable also. So in the coming times also, the fiber is going to be the power behind lot of 5G or 7G telecommunication systems. The fiber is going to power behind AI, artificial intelligence systems. So fiber optics is basically going to guide our technology in the future generation for quite some time. So you can see here also the fiber has taken a great detail, fiber has given a great detail of impact in the medical field, in kind of laparoscopic surgeries, endoscopy, and various operations which was kind of very complicated till now, where the patient has to take lot of time to recover, has reduced in its time substantially, because you can basically make a small hole and do the entire operation, which is possible due to the fiber optics. So if you think about it, the application of fiber optics in various scientific aspects are only going to increase. So the fiber optics cable is a humble giant which is leading the technology in different aspects nowadays. Now let's go to the demo of the fiber fed spectrograph. So now let's see the demo of a fiber fed spectrograph. So as I explained earlier, there is a source of which we are actually taking the spectra. There is a fiber, as you can see here, a group of fibers. The fiber which delivers the light into the spectrograph in a very flexible manner, and the other end of the fiber, it actually forms a slit arrangement, so that it arranges the fiber in a straight line and the light is delivered into the spectrograph. So just like you see here, like many fibers, the similar kind of fibers are inside this fiber tube. Okay, now let's see a source and a group of fibers. Let's cover the source, and I fed. See, the fiber is transmitting light from the source through it and delivering it at the tip of the fiber through a very flexible manner. You can actually bend the fiber, you can actually redirect the light in any way you want. So now you can see the light coming out of the tip of the fiber. Now let's see the other end of the fiber, where the fibers are arranged to form a fiber slit. Now there is the collimator which feeds the light into the dispersive element. From the dispersive element, the light is collected by the imaging lens, which forms an image of the spectra into the camera. The camera image can then be used in any display device so that you can see the spectra. Now let's see the spectra of a continuous source. See, we saw that the fibers are arranged in a line like a slit. So, each of those fibers are dispersing the light in the vertical direction and creating the spectra. That is the reason for the lines in between the spectra. Now, let us see, when I move the dispersive element, I can actually see different colors, the light dispersing in the continuous spectra manner. Now, let us put another source and see how that spectra works. Okay, now let us see the spectra of a CFL lamp. So, inside the CFL lamp, there are gases which absorbs the light passing through it. So, what happens is, in the spectra you can see this dark areas where the light was absorbed by the gas. Now, this shows a clear difference between a continuum spectra and a spectra of a different source. So, through this we can understand, by studying the spectra we can actually get an understanding about the source which you are trying to observe. So, thank you for attending the talk. I hope you would have enjoyed this talk and learned quite a bit of things. So, we would be giving more descriptions about different details of this talk in the description section. If you have any doubts, please post it in the comment section, and happy Science Day.
Thank you, Anu. This was a really nice presentation and a really nice demo. So let's see if we have any questions.
Let me also thank Anu Jacob for presenting this very unique kind of a perspective on astronomy, because we always think it's all about the beautiful bodies up there in space, which are colorful, etc. But there's also another aspect of doing spectroscopy, not just the photographs, the images, but there's also spectroscopy, which can give a lot of information. So thank you for bringing that world to us, and also a peek into your lab. Right, so it's not just a telescope there; it's a very different setting. So tell us more about that a little bit. How does it feel like to work in the lab, and as an instrument engineer?
Yeah. So in astronomy, we basically work on astronomical instrumentation. So a lot on light. So a lot on different kind of optical aspects. So that means lenses, prisms, fiber elements, different things. So these components are very sensitive, and usually because you work with light, usually they are in a dark room. Like the light which you are trying to study is only present, no other interference from other lights are there. So that's taken care. So that's why the room, you can see it is mostly dark. So the components, everything is dark. So that is one of the important aspect, and they are very sensitive. So you behave with the blouses, masks, your hair will be covered. So you have to take them like a very precious, like in a medical field, like you are doing a surgery, you have to work like that. So the most important or happy aspect of this research for us is the output you get at the end of it. So the pictures you see or anything comes out of a telescope, that is first demonstrated inside a lab. So that gives us, what you are going to see in the sky at the end will be first designed and developed in the lab. So we do get a lot of happiness in actually, being able to work for such aspects.
Sure. A lot of happiness and a lot of pride in making these technologies, which may be a first actually. You might be developing the new technologies here in the IUCAA labs, right?
Yeah. So astronomical instrumentation has contributed technologies to various different fields. So if you want to say, like in a lot of fields. So optical fiber, even though it's mainly for optics, so it has taken over a lot of our medical telecommunication fields. Then there is this medical field itself. If you talk this what you call CT scan or MRI scan, what you use, they derive technology from astronomy or related sciences which we have developed for astronomy. So astronomy has been the mother to kind of develop this cutting edge technologies, because here the requirements are very tight. So it always pushes the technology boundaries further and further, and we contribute to further people.
Okay. Yeah, that's what I think this year's theme of the National Science Day also is kind of pointing to, that having an integrated approach of science and technology towards a sustainable future growth of our human race. So, and I'm happy that the offshoots of a lot of astronomy research and the requirements of astronomy research are actually getting into popular use, including, as you said, I think CCDs are one of the examples.
Yes.
CT scans are another one, which radio, astronomers have developed imaging techniques for, and they are now being used widely in medical as well as many other things. That's a great thing to know. So I don't see many questions. Do you spot any, Shivani?
No, they just want to know what exactly a spectrum is.
Okay. So whatever I've shown in the talk, that is visible spectrum. I basically discussed about visible spectrum. So spectrum is the entire electromagnetic radiation spectrum, which our eye can see, or the most of the spectra our eye cannot see. So it's the arrangement of different electromagnetic radiation in the order of its wavelength. So that is basically a spectrum. So light is, electromagnetic radiation is composed of this different band of light. So if you study the band of light, you get an idea about that radiation and also about the body which is emitting that radiation or absorb, either way.
Okay. So there's one more, I think, interesting question. Ma'am, how to know that which gases are which colors that you see in the spectrum?
For each of these gases, whatever we have seen, there is a simulation spectrum. We have data calibrated for each of these gases. They are tested in the lab. So, hydrogen gas has this spectra. So when you observe the same kind of lines from a star, you know that that gas is that object.
Okay, that's nice. So I think we'll take one more question before we see the video. So there's one more question. Does a polarization gradient of a light beam change after carried by the fiber optic cable?
So fiber optics does polarize light, it does, but the studies of this fiber optics polarization is very kind of, it's a different field where you actually you can actually model it, how a polarized beam is transmitted to the fiber and how it is changed. So depending on the material, you can model it and then study how it is going to affect if you have an input polarized beam at the output of it.
Okay. So that's I think a more complicated audience or a more grown-up audience will appreciate the answer to that. So there's options, as we were saying, in careers of astronomy, of being in astronomy, and Anu is actually a engineer, right? And
I'm a technical PhD. My doctorate is in astronomical instrumentation. Right. So I'm a technical doctor. That's a technical scientist. Right. So so in astronomy there is a different path other than the science. There is an instrumentation path where you actually make this instrument so that the scientists can do the observation. So astronomical instrumentation, the basic things like optics and all those things, they are used in different fields. Like there is medical optics, there is electronics, which is used in astronomy. A lot of electronics is there. A lot of this, the big data, data processing, which is also used in other fields. So astronomical instrumentation is linked with many other fields. So you can actually diversify your field, like start from astronomy, or you can go ahead and do different things, or you can have multidisciplinary knowledge and come work in astronomy to actually develop new things. You actually need to know a lot about different fields.
Yeah, that is a good thing because we get a lot of inquiries what we should study after 10th so that we can do astronomy.
Yeah.
So this is a good answer. You can do convene varied fields to do astronomy.
You contribute to astronomy knowledge or the process of astronomy at least. It's lovely to see you contribute to that, Anu. And also thank you for bringing out this unsung hero, the fiber optics itself, which is not known to people. It's being used everywhere. And the creator of fiber optics, the person who named fiber optics, Professor Kapani, and such a great scientist who passed away just about a year back, and was given the Padma Vibhushan posthumously. So a great recognition. Again, I would say that it's very apt for the theme where something very specialized and technical could easily find use in the sustainable future. So thank you for bringing us this talk, and we'll keep in touch with you. We hope to hear more of you in other good events. The audience is also looking forward to that. Thank you.
Thank you. Thank you.
We'll now look at the video which Anu has shared with us, which she wants us to show you while we wait for the next speaker to come in. So thank you, Anu, and let's have a look at this video.
Thank you.
Thanks. Great. So a few more demonstrations there, which you saw happening, and all sorts of lovely colors, but that's not, sorry, somebody needs to mute. So, so all sorts of colors there, but then that's not all. It's also a lot of astronomical information that you can get from light, which is, as you just saw, is a messenger of light. And the people who are working in our labs, optics labs, instrumentation labs, are helping the astronomers collect light with telescopes and provide them the information to study further astrophysics. Now, what happens after you have collected all this information about the universe? Then you create a kind of a picture of what is happening in it, right? What are the things that are going on? And these things are kind of done through simulations. You cannot have a complete picture of the universe because it is evolving all the time, and this evolution can be simulated, and a lot of new information can come out of it. So right now, let's go on to the next talk, which is by Sukanya Malik, and who's another researcher at IUCAA, and she is bringing to you some nice simulations, some again, a lot of good images, but then there's also the background information and the background complexity, the background struggle to get proper information and sense of the universe. So Sukanya, welcome. You can turn on your camera. Hello, and your mic, please.
Oh, hello.
Great to have you here, Sukanya. Yes, yeah. Good. So we'll be showing a talk recorded slightly earlier, and then Sukanya will be happy to field questions, which you should put in the YouTube chat. So let's have the talk. Thank you.
Hello everyone, welcome to the National Science Day celebration at IUCAA. I am Shukarna. In this talk, we will try to understand the universe through simulation. The universe is everything from the tiny fluctuations to the largest of galaxies and the existence of life itself. But how did it all begin? The origin of universe is the origin of everything. So what we see around us, the earth, the sun, the stars, the galaxies, these are only 5% of the total energy budget of the universe, and rest of the universe is made up of dark energy and dark matter. So this is a video illustration of the universe made by the illustrious simulation group. So after the Big Bang, the universe was very tiny, and it was hot and dense, and it was mostly homogeneous. This homogeneous universe had some tiny density fluctuations. These density fluctuations grew, and after the growth, it started forming the structure. The video shows the dark matter distribution of the universe. Here we see that some dense clouds are there. These dense clouds are forming wave-like structure. These are dark matter distribution. We see that some massive portions are getting more and more mass and becoming dense. So baryons will follow the gravitational potential formed by the dark matter, and it will form the galaxies in the densest part of the dark matter halo. After the galaxy started forming, the gas will cool and condense and form the galaxies, and inside the galaxies the stars will be formed, and the stars will form different elements beyond helium. We say these elements as the metals of the and these metals will be formed inside the stars and go outside of the stars in different feedback processes. So now the video shows the metal distribution of the universe, and we can see that the metals are densest in the position of higher density region, and then they are going in the surrounding region also. So now we are going back to the dark matter structure again. So this dark matter structure is very similar to the structure we see in nowadays. So this is done by a simulation, and this is the history of universe. We want to know the details of the physical processes associated with this evolution. So how do I know that? the history of the universe. How do I know that? The answer is light, because light takes a finite time to reach us. For example, light takes 8 minutes and 20 seconds to reach from sun to earth. So, whatever has happened in sun 8 minutes before, we will know it on earth after, we will know it on earth now. So, this finite light travel time is the key concept to understand the history of universe, and like that, if the source is farther away, it will take more time for light to reach us. From the center of our galaxy Milky Way, light takes 30,000 years to reach us, and if we talk about the farthest observable galaxy, it will take 13.6 billion years to reach us. So, this finite light travel time is the key to understand the history of universe, and also if we want to know the exact time when the light was emitted, we have to know that we say the universe is expanding. Initially the universe was small, and as the time passes it grows like this balloon shown in this slide. So, it grows and grows, and after some time the light, when we detect the light, the emitted spectrum will not be same. So, the relation between the emitted spectrum and the observed spectrum is related by one quantity called the redshift. The light will be shifted toward the redward. So, we call this a redshift. So, this relation is shown in the slide. So, from the value of emitted light wavelength and the observed light wavelength, we can know the redshift, and from the redshift we know the exact time when the light was emitted. So, what information can we know from the light coming from different sources of the universe? The answer is spectroscopy. So, what is spectroscopy? It is very similar to the spectroscopy we use in our labs. So, if there is a continuous light source like the source shown in the slide, so this source will emit a continuous spectrum. This is a continuous spectrum. Now, if the light is passing through a cloud of gas, then the cloud of gas will absorb some of the energy from the light. So, the energy absorbed from the light will depend on the element present on the cloud. So, and after the absorption, the elements in the cloud will emit some of the energy, and this will be manifested in the emission spectrum like shown in the slide. So, if we now see the source through the cloud, then we will get some absorption spectrum. So, the clouds will absorb some portion of the energy from the continuous spectrum, and the rest of the continuous spectrum will be shown. This is known as the absorption spectrum like shown in the slide. Now, this is an illustration of the similar thing. So, this is a source and light is coming from that source and being detected at this telescope. So, we see that this light is coming through the intervening medium, intervening gas it is coming through, and at different portions of the intervening medium, the light is getting absorbed by the gas, and such kind of absorption lines are being produced. This video is made possible, special thanks to Pesky for that, and this is a video illustration of how the absorption line can form. So, this is what we see in the observation. So, this is actual observed spectra, and this is our universe. There are different stars and galaxies shown in the universe, and this is a background light source called quasar. So, from this quasar, light is coming to us, the earth, and it is coming through the intervening gas. So, intervening gas can have neutral hydrogen. So, the neutral hydrogen at different positions will absorb the light, and due to the difference in redshift of the gas clouds, the absorption will be seen in different wavelength. In x axis we see the wavelength. So, at different wavelength we can see the absorption. So, such kind of absorption systems will be formed due to the Lyman alpha or neutral hydrogen absorption. So, also apart from hydrogen, there can be some other elements in the cloud also, like oxygen, carbon, neonate, different ionization states of these elements. So, these are called metal lines, and we can also observe metal lines. So, from these lines we know what are the constituents of the cloud and at what redshift they are forming. So, from that redshift we know the structure of the cloud that is present. Now, unlike other branches of science, we can't do lab experiment with our source. We can't touch our subject actually. So, for understanding the actual physical processes underlying such observation, we need to probe, we need to have some models to explain the observed data. So, what we do is that we simulate the actual universe, and we propose some models, and if the models can produce the result consistent with the observation, then we say that the model is good enough. So, I will discuss mainly about the cosmological simulations here. So, in our present day standard cosmological scenario, we say that the universe is expanding and the main constituents are dark energy and dark matter, and there are some amount of baryons also. So, this is a simulation box. So, inside this simulation box we put some dark matter particles and some baryons. So, the box size and the number of dark matter and baryon particles can vary in different simulation depending on the computation power and also the physics we want to resolve. But these two things are important to understand, and also in different observations we see that the universe is homogeneous and isotropic on large scale. So, to mimic that homogeneity and isotropy, what we do is we employ the periodic boundary condition. What is periodic boundary condition? That is, we connect side 1 to side 2, these opposite sides we connect. So, this is periodic boundary condition to mimic the homogeneity, and any opposite sides are connected. So, this is a continuous kind of structure. So, we set the initial conditions. So, initial conditions say that the universe is very homogeneous and there are some tiny density fluctuations, and these density fluctuations in the dark matter will start to grow. Now, dark matter only interact through gravity. So, gravitational interactions is put in the dark matter particles, and there are baryons also, because all the visible galaxies are made up of baryons. So, we have to input the baryonic physics also. So, baryon is treated like an ideal gas. So, hydrodynamical equations are also inputted, and now all these structures are being formed. So, the gas must cool. The gas can be heated due to the background radiation field. There is a background radiation field which can heat the gas via photoionization, and gas can cool through various processes like collisional ionization, etc. So, these heating and cooling depend on the background and the model we are using. So, this is also important, and after the gas is started cooling, it can condense, and these condensed clouds will form the star. So, inside the simulation, if a set of particle is very dense and it is being cooled, and then we put a star particle at that position in the simulation. So, like that star is formed in the simulation. Now, star is formed, so some portion, some fraction of the star will be exploded into supernovae. So, what we do is some star particles we identify randomly and then treat them as supernovae, and the energy and mass from that star particle will be ejected out in the surrounding medium. So, this is known as supernova feedback through the stellar winds. So, this is important in various simulations. Hello everyone, welcome to the National Science Day celebration at IUCAA. I am Shukarna. In this talk, we will try to put in the dark violet, that is, there is a source just behind the simulation box, very early stage of universe, and as energy will be coupled to the surrounding medium. So, this is known as the AGN feedback. So, this kind of feedback processes are important. So, there are four important things that we consider. One is cosmological framework, which cosmological framework we are using, initial condition, and the force equation, that is gravitational equation, and hydrodynamics we are using, and star formation prescription, and the different feedback processes. So, different simulations have different models of such factors, and it can produce the observational result. If they are consistent with observational result, then we say that models are good enough. So, this is how the universe evolve in the simulation. So, this shows the initial state of the universe in the simulation box at redshift 27.36. It is very early stage of universe, and as the time passes, we can see this is showing the dark matter field only. We can see that the tiny density fluctuations are getting denser and denser, and it is forming wave-like structure, and this is the present day simulation. So, in the present day, the structures are formed, the galaxies are formed. So, this is how we see how we evolve the universe. So, it is a very exciting thing that we can actually see how the universe has evolved and come to the present day state on our laptop. So, now about the observation. So, can the simulation produce the similar kind of observed spectrum that we have already discussed? So, this is the observed spectrum I already discussed. So, can the simulation produce the similar observed spectrum? Yes, it can. What we do is that we assume that there is a source just behind the simulation box. Light is coming through the particles inside the simulation and being detected at the opposite edge. So, we know the density, the temperature, the velocity of the particles in the intervening gas. This is very similar to the realistic situation where the light is coming through the intervening gas, and the intervening gas absorbs the lights and form the absorption system. So, it is very similar to the realistic situation. So, here the light is being absorbed and we detect it here. So, this is one such simulation where this is taken from the shaded simulation box, where we see that violet portions are under dense region, the white portions are the dense region. So, we see that white wave like structure in the region in the simulation. So, these white waves are showing the structures formed inside the simulation, and there are some very dense portion of the simulation denoted by brown. So, the blue line here shows the density fluctuations in the simulation box. So, we see that at the point of brown points, the density is very high, and in the point of violet, the density is very low. So, this is the flux due to that density fluctuation. So, we see that flux, the absorption is more for the over dense point and less for the under dense point. So, this is a more clearer picture of observed and simulated spectra. This observed spectra is taken from Danforth et al. 2016, and this shows the absorption lines for mainly neutral hydrogen and some other elements like oxygen 6, silicon 2, etc. And this is a simulated spectra from the shaded simulation suite. I have only shown the neutral hydrogen absorption here. So, we can say that simulation can fairly produce the similar kind of absorption spectra we see from the observation. So, using such kind of simulated spectra, we can know we can probe the different physics associated with the actual processes. We can vary the feedback methods, we can vary the star formation models and see what effect it produces in the observed results. So, I will end with some prospects. What we have discussed in this talk is that the simulation, how the simulations work, and there are different important parameters of different simulation, that is varying box size, resolution, the different processes, etc. So, using the simulations, we can probe in different scales. We can probe the large cosmological scales and the galaxy formation scale, the star formation scales, and also can know the different physical processes, and from that processes we can know the fundamental physics also. So, it is a very exciting subject to explore, and thank you.
Thank you, Sukanya. We are unfortunately was facing a technical glitch, because of which you could see the slides only for a little while. But then the talk was quite interesting, and it revealed to us a lot of details about what goes on behind finding out the general structure of the universe, the cosmic web, as it is clubbed here. So Sukanya, can you tell us more about your journey into astrophysics and how you got into doing this work, this fascinating work?
As every child, I was curious about the stars in the sky, and that is the main inspiration that it inspired me to know why. As we know, we generally in our childhood, we know our family, then our neighbor, then our just outside our state, our country. So just like that, I really wanted to know what is just beyond our planet. So that is the main inspiration. Then in BSc, I took physics as my major. So that is just fueled my curiosity. And then I applied for IUCAA, and here also there are many inspiring things happening around us. So that is my.
Right. So we have a lot of youngsters attending, and so is this a typical career direction that you would suggest them to take if they want to get into astronomy, astrophysics?
Yes, I can tell about my career path. So it is not such a career as of now. So just studying, just learning. So I did my BSc in President's University, then MSc in Kharagpur, IIT Kharagpur, and then joined in IUCAA after INET. So I was interested in astronomy. So that is my motivation to join IUCAA. There are other institutes in India and abroad which people can apply. So the key point is that if you are interested, then you can join anywhere. So, and it is very rewarding that at the end of the day, you can actually know that is far beyond our scope of touching this. We can actually reach there. So this is very rewarding thing. So.
And what is the latest exciting thing from your field that you're researching on right now?
Yeah, so I actually do this kind of simulation. I use this kind of simulation to probe the intergalactic medium. So what is intergalactic medium? There are many galaxies roaming about, and what is in between is called the intergalactic medium. So I want to probe that medium. Okay. So by probing that medium, we know different things about the galaxy formation, and also some basic fundamental processes that I already discussed in the talk, yes. If people can hear that. So many feedback processes, etc. So my specific research field is to study the metal distribution in the universe. Mm-hmm. So via the absorption line spectroscopy.
And so is there a difference between, because we were just listening to talks about local things in our galaxy, nebula, interstellar medium. So is there a particular difference between what lies between two stars, let's say, and what lies between two galaxies?
There are differences in the density and temperature field.
Okay.
So we probe different density temperature field, and also the scale. The scale are very large in IGM. So we know that within the galaxy we probe very small, not very small, but smaller scale than IGM.
Right.
So that is one of the difference.
Right. Because in general, the popular concept of space is emptiness, and then when we talk about mediums in between stars and galaxies, then there might be some curious questions like this, and that's why I wanted to ask this. But there are people are still asking questions, so we would encourage them to put in anything that they want to ask about it. Okay. So does your simulation also lead us to any reflection about the formation of the universe, or can we also simulate it and rewind it back towards the Big Bang in simulation?
So we don't rewind back. We start at a very early stage.
Right.
So after we put some condition on the particles, etc., and after that we evolve. So. Okay. we have the result in present universe and certain epochs of the universe, certain times of the universe. So we match different observable in that epochs. Okay. So if these observables are matching with what we actually observe from the sky, then we say that our modeling was good enough, or we can suggest some modification.
And so there is a question, specific question, which asks about the size of the universe box that you have taken in your simulation here.
Yes, so I specifically use 100 megaparsec. So people have used anything between 20 megaparsec to 300 megaparsec. So this is co-moving distance. So I use typically 100 megaparsec.
Okay. So and the parsec is something like 2 light years, so double in light years terms. Lovely. Okay, so that's quite a bit of information about the simulation work that you do, and the information about much larger scales of the universe that we are probing here. So it's a great range of topics discussed till now, right from tiny neutrinos to this largest scale cosmic web structures. Amazing this field of astrophysics is. So thank you, Sukanya. We will again, apologize for the few slide goof-ups that happened. But then we are also eager to look at this video that you have shared with the audience. So while we say thank you to for being here, we'll now play the video and then move to the next.
Yeah, thank you for listening.
Thanks
Thank you.
For me, it's the most exciting thing ever that happened in my life, right? And I feel like I'm incredibly lucky to be participating on this bonanza of new data.
Hello, Janvijay, and we welcome you here from IUCAA.
So welcome, Janvijay. Now we are moving on to things closer by to our particular planet that we inhabit, and we are celebrating Science Day on it. The science which is allowing us to know about the whole universe again. So it's a lovely cycle. So thank you for being with us, Janmejay. Do you know Shivani? He is joining us from Bangalore, where he's actually right now working at the ISRO lab on this particular instrument which is going on this particular satellite, this telescope which is coming up, and that is what he's going to talk to us about. So Janmejay.
Like he is actually there working on it, the things that he is going to talk.
Yes, so we were actually it was a difficult communication because all day long these are tidbits you get to know when you're in the field. So he doesn't have his mobile close by, and there's restricted access because these are very sensitive information. So he's working in these labs, and today on his off day, he has come here to give this talk. Thank you, Janmejay. Welcome to the stage. And he's present. Thanks.
Can you see my screen?
Yes, perfectly.
Okay. So shall I start? Okay. All right. So hello everyone. Today I'm Janmejay Sharkar, and today I'll be speaking on exploring the sun with India's first space solar observatory. That's Aditya L1. So all of us are really psyched about the upcoming ISRO mission Aditya L1, and you'll be very excited to know that even IUCAA is playing a very important role in this mission, because IUCAA is contributing an ultraviolet telescope to observe the sun. And today I'll be speaking on the Aditya L1 mission, as well as on the different payloads of Aditya L1, and why is it necessary that we need to send this telescope and we need to send this entire spacecraft up in the sky. So, yeah. Okay. Is this fine? Is this fine? Okay. Okay, fine. So first off, I'll start with why should we study the sun? So like all of us know, the sun is the largest source of energy that we have, isn't it? Like our crops, our weather, our climate, everything is guided by the sun. And like the sun provides us the resources for growing crops, the sun also has the power to destroy crops and cause famines, cause dehydration, and kill animals. So the sun can have huge adverse effects as well as huge beneficial effects on the earth. I mean, that's why, in fact, it's because of the sun that humanity and also life is existing on the earth, because it's warm enough on the earth for life to exist and water to exist in liquid form. But at times, the effects of the sun can be really drastic. It can cause famines. Sometimes it causes these things called solar flares and solar storms, and that destroys lots of satellites in the sky. Also, you might have, if you are using a DTH connection at home, you might have come across one such message through Tata Sky or any other DTH service, Dish TV or something, that a satellite has directly fallen in line with the sun, and therefore there's a sun outage. You can't watch TV for a couple of minutes or a couple of hours. So these things are necessary, these things are important to predict, and we need to understand the sun in a much better way. The sun also causes beautiful things like rainbows, like aurorae. And you know that because the sun has been so mysterious to mankind since the beginning, that nobody could predict the sun. That's why humans have come across different deities and different gods to worship the sun, because they believed, our ancestors, they believed that if we worship the sun, then maybe the sun will be happy on us and the sun will give us good crops instead of causing famines. And this is all over the world because the sun is universal. I mean, universal meaning it's all across the earth. So in India, we worship sun as the sun god Surya Devta. In Egypt, the Egyptian civilizations worshipped him as Ra, and the Greeks worshipped him as Helios. So there are, as you see, across all different civilizations, there has been a sun god, somebody to personify the sun and to worship the sun. So first off, that's why it's very necessary that we study the sun, because till now we don't know the mysteries of the sun. It's very mysterious to us. Now, next coming to this, that what makes Aditya L1 so special? So there are space telescopes that are observing the sun. Like there is the Hinode, there is Stereo. Stereo is a collection of, it was a collection of 2 telescopes that used to observe the sun to generate 3D images of the sun. And there is SDO, Solar Dynamics Observatory. There is IRIS. But what makes Aditya L1 so special is this thing L1. L1 refers to Lagrange 1. So as you see, this is a diagram of the sun and the earth system. So there are some points in and around the earth where the gravitational forces of the sun and the earth are just right to keep an object balanced at that point. So like over here, this is the point called the L1. It's around 1.5 million kilometers from the earth. And any object you keep at this L1, it's like an equilibrium point. So any object you keep it there, it kind of tends to stay there. Although it's not very stable, you need to follow an orbit, satellite or anything. It needs to follow an orbit. It needs to go around the L1 point, but it's more or less a stable position. Now, what is the advantage of L1? You see, the advantage of L1 is if you put a satellite around the Earth, then there will be a time in which the satellite goes behind the Earth and is in the shadow of the sun. I mean, is in the shadow of the Earth, and it cannot observe the sun for a couple of hours or so. But if you put a satellite at L1, it can continuously observe the sun. So that is the interesting thing about Aditya, that Aditya will be equipped to continuously observe the sun. And like, there are several other solar instruments, sun sensing instruments like wind experiments and solar wind detectors and all these things placed at L1, but the numbers are very low. There are very few objects placed at L1. The last solar telescope that was placed at L1 was SOHO. And the next one that we'll be putting is Aditya L1. So it's a big leap for India to place a satellite at L1. It is a very challenging task. And if we can do that, and we will do that, once we do that, we'll be observing the sun 24/7 without any interruptions, which is very commendable. So first, going into the different instruments of our Aditya L1, we'll first discuss the basic anatomy of sun. So sun has several layers. It's like an onion. Onion has a lot of layers. There's a core inside the onion, and there are several layers on top of it. Sun has a radiative zone and a convection zone. The radiative zone generates a huge amount of power that passes onto the surface of the sun, and from there the light is emitted and we see it in our sky. So then there's the radiative zone. After that, there is the convection zone where it's kind of like a boiling water. If you boil water in a pot, you will see that the water bubbles. It comes out from the bottom and comes to the top, and again it goes back inside. So it's kind of cyclic. That's convection of heat, and the same thing happens in the sun too. On top of that, there is the photosphere, which is essentially responsible for the light that we see on Earth. So the name suggests photosphere means photos meaning light. So the sun that you see during a sunset, that is essentially the photosphere of the sun. On top of that, you have the chromosphere. The chromosphere lies on top of the photosphere, but the intensity of chromosphere is very less. It's not as bright as the photosphere. So during a sunrise or a sunset or during the day, we don't generally see the chromosphere, but with some specialized telescopes like hydrogen alpha telescopes, we can see these structures in the chromosphere. There's another phenomenon when we can see this chromosphere is during a total solar eclipse. So when the moon covers the earth, when the moon covers the sun, you can see these red patches of fire around the sun. These are basically parts of the chromosphere of the sun. And on top of that, you have outside the sun, you have the corona. The corona is a huge region of very hot gas around the sun, very hot gas and plasma. And this corona is also visible during the total solar eclipse. But the interesting thing is that you see, to observe the chromosphere and the corona, you need a total solar eclipse. But it's not possible to generate, it's not possible to see a total solar eclipse all the time. You maybe get 1 or 2 total solar eclipses a year. and that too for a couple of minutes or a couple of seconds. So what we do is we send spacecrafts in the sky and that observe the corona of the sun. So as you can see, this is the corona of the sun, and special instruments are used to cover the center of the sun and observe only the sides of the sun. These instruments are called coronagraphs. Then you see, with all these different instruments, earth-based as well as sky-based, we observe different layers of the sun with different filters, with different telescopes. So we see the visible light, the photosphere of the sun. We can find out the magnetic field of the sun. We can see the sun in UV, in hydrogen alpha, and then there are different images of the corona of the sun. But the interesting thing is that between this range, that is between UV 1600, that observes the sun at around 8000 Kelvin, all the interactions happening at around 8000 Kelvin, and interactions happening at around 15,000 Kelvin, between this temperature range, there is very limited observation from space. So we need to send something in sky that can observe this temperature range. So you see there's a huge jump from 8,000 Kelvin to 15,000 Kelvin to 50,000 Kelvin. There's a huge jump. So SOOT will be used to observe in between this temperature range. Now, you might ask me that what is the reason? That why should we send so many telescopes, so many instruments in the sky and pollute our entire sky? So why can't we make do with just one telescope? I'll just compare this with one very popular story that every one of us has come across in the childhood. So there were six wise blind people, and they were asked to feel an elephant and describe it. So different people were asked to feel different parts of the elephant. So the person who felt the leg of an elephant said that it's a tree. An elephant is like a tree. While a person who felt the stomach of the elephant said an elephant is like a wall. And the person who felt the tail of an elephant said, no, you all of you are mistaken. An elephant is just like a rope. It's comparable to a snake. So the problem was all of them had a different idea of an elephant, which an elephant is actually not. An elephant is completely different from a wall. It is completely different from a tree. It is completely different from a snake or a rope. Now, the problem that they were facing with is that they did not come together and discuss among themselves that what they have felt, because their senses were limited. So if they would have come together and discussed that, okay, I felt this and you felt that, okay, so probably an elephant might have been like this, a huge animal who has a big stomach, thin tail, and thick legs. So it's the same thing that we are doing. We are feeling different parts of an elephant with different telescopes. Now, what we need to do is, like Vishal before me explained on multi-messenger astronomy and multi-wavelength astronomy, we need to collate all these observations, all these ideas, because the sun, the stars, everything looks very different in different wavelengths, in very different lights. So we need to collate all those ideas and come up with one common idea that will explain the sun. So for this purpose, Aditya has been equipped with a wide arsenal of instruments. So there is the visible emission line coronagraph. It's a coronagraph that will be observing the corona of the sun by blocking out the center bright region of the sun. Then we have the solar ultraviolet imaging telescope that we at IUCAA are building. So SOOT will be observing. SOOT is like a telescope that will be taking photos of the sun, just that it will be observing in what is called near ultraviolet light in the wavelength range between 200 to 400 nanometers. There is Solexis, and there is Helios. Solexis and Helios are two X-ray spectrometers. So Solexis will be observing low energy X-rays, and Helios will be observing high energy X-rays. There is Aditya Solar Wind Particle Experiment, ASPEX. ASPEX will be observing or will be detecting solar winds. There is Plasma Analyzer Package for Aditya, PAPA. PAPA will be observing the plasma outbursts and the plasma from the sun. And then there is a magnetometer, because in the sun, the magnetic field keeps varying and it's very, very dynamic. So what we need is, we need a magnetometer similar to the one that we have in our Android phones that says which direction is north, but the concept is similar, but it's more complicated than that. These instruments are more sophisticated. These instruments are used to measure how strong a magnetic field is that's getting generated on the sun. So this is SOOT, IUCAA's contribution to Aditya L1. This is the structure of SOOT, the inner structure, and this is the assembled photograph or assembled design of SOOT. So as you can see, this is the front of SOOT. The sunlight will enter from this side, and there is a thermal filter assembly. So, and thermal filter, what it does is it cuts down sunlight, because sun is extremely bright. So if the entire sunlight falls inside the telescope, the telescope is going to heat up very much, and it's going to spoil everything. So we need a thermal filter to reflect out maximum amount of sunlight and pass around just a few tiny fraction of sunlight inside the telescope. So this light goes through the telescope, falls on the primary mirror, and then it reflects and falls on another tiny secondary mirror. This light goes through a field curvature lens, goes through different filters, and then it falls onto the CCD, a charged coupled device, imaging device for photography, for imaging. And this, all the data that is being gathered over here, that all this data will be sent into the Aditya electronics and the Aditya computers, and that entire data will be relayed back to Earth. So what is SOOT going to observe? Like we said, SOOT will observe within the wavelength range of 200 to 400 nanometers. So why 200 to 400 nanometers? Because you see, from the Earth, this wavelength range is not visible. So you have UVA, UVB, and UVC. You come across these terms when you see advertisements for sunscreen lotions: UV protection, UVA protection, UVB protection. So what they essentially mean is that these are basically wavelength ranges. So UVA is between 400 to 315 nanometers. UVB is 315 to 280 nanometers. UVC is more high energy, 280 to around 100 nanometers. So what SOOT will do is SOOT will observe a fraction of UVC, a lot, the whole of UVB, and again a fraction of UVA. And why these specific lights? So the reason is these lights are generated in this region of the sun. You see, this is the photosphere, then there is the chromosphere, and then there is the corona. So what SOOT will do is SOOT will observe from the photosphere through the chromosphere, and it will also observe a little bit of the corona also. So this is the region called the transition region. Transition region is the place from the chromosphere to the corona. So what happens is, as you can see, the temperature of the sun, what we come across our school textbooks, is that the sun is around 5,000 to 6,000 Kelvin, right? But the textbooks don't tell us what's there on the other layers of the sun. So on top of the photosphere, you have the chromosphere, which is at around 4,000 Kelvin, 4,000 degrees Celsius, around 4,000 Kelvin. After that, you have the chromosphere, where you see from the inside of the sun, the temperature keeps decreasing till the lower chromosphere. And then again, when you go to upper chromosphere, the temperature increases. It's around 10,000 Kelvin. And from upper chromosphere, when you go to corona, you see it goes to 10 lakh Kelvin or 10 lakh degrees Celsius. So there is a huge temperature jump from upper chromosphere to corona. This region where there is a transition, there is a change from chromosphere to corona, this region is called the transition region. So SOOT will also be observing this transition region. So what are some special features of SOOT? SOOT has a very special feature which helps in automatic detection of solar flares. It can automatically detect when a solar flare is happening with the help of the payload Solexis and Helios. So Solexis and Helios, they will notify SOOT that, okay, hey SOOT, there is a solar flare coming. There's a solar flare coming. And what SOOT will do is SOOT will change its imaging mode to very fast imaging mode. So essentially, what SOOT will do is SOOT will take full resolution images of the entire sun. Like you can see over here, this entire solar disk. The SOOT will be imaging this. And SOOT will be imaging this with all of its science filters, all of its different 11 filters are there. And SOOT will take around half an hour, that is around 25 minutes, to go through all the filters and start all over again. SOOT will keep doing that. And then suddenly, if there is a solar flare happening, Solexis and Helios will detect that, because they're X-ray instruments. So they will detect it and they will tell SOOT, hey SOOT, there is a solar flare coming. And SOOT will change its imaging mode and try to look for the solar flare. So once it finds the solar flare, it will lock into the solar flare with a box called the region of interest. and it will photograph only this tiny box, and it will photograph it very rapidly, very quickly. But you see this flare, this image of the sun is from SDO, that is Solar Dynamics Observatory, and there is a solar flare happening. Now you notice what's happening over here. The solar flare can be so bright that it can completely saturate out image sensor. What saturation means is there is no detail. It's completely washed out. See, it's totally white. You can't see what's happening inside it. So what you need to do is you need to decrease the exposure time so that you can observe the bright features. So what suit will do is, after it generates a region of interest, it will do auto exposure control. Automatically, it will control the exposure so that we can see what is happening inside the solar flare. So once we set the proper exposure and the region of interest, it will automatically keep taking images of that region at very high speed. And also, see, the sun is rotating, and so is everything in the solar system, all the objects. So as the sun rotates, the solar flare will also move with the sun. So suit also has an algorithm that this region of interest, it will keep tracking the solar flare across the surface of the sun while the sun is rotating. So these are this is one very important feature and very nice feature to study the birth of solar flares on the sun, because apparently, as you can see in all the telescopes, what happens is it just washes out. It's completely saturated. And on top of that, there is another big advantage, is that we can compare the solar surface images with SUIT with the image from the VELC, that is a spectrograph. So the outside region, this box shows the region that VELC will be observing. And this yellow ball, this shows what SUIT will be observing. So you see, if you overlay these images, you will get to understand how these dynamics are passing on from the photosphere to the chromosphere to the transition region to the corona. We'll get the detail for every single layer of the sun, and we'll understand how these variations or how these dynamics are getting carried from the lowest surface, from the surface layer of the sun, that is the photosphere, out to the corona, or sometimes from the corona or the chromosphere back to the photosphere. So finally, I would like to end with a simple motivational slide and motivate all of you to, whoever is here, school students, college students, to take up solar physics and to study solar physics. No doubt astronomy is very interesting, but I feel that although astronomy is interesting, but the sun is directly linked to our lives. And we have been worshipping the sun, we have been observing the sun for many ages now. Like you see, this is the Konark temple in Odisha. I think many of you must have been here. This is from the 13th century. And not only this, this is from 25th century BC, the sun temple of Usarkaf in Egypt. So civilization has been worshipping the sun for ages. And you see, sun affects like our lives like no other celestial body. The sun causes solar flares that can totally destroy our satellites, that if proper protection of these solar flares will help us save thousands and thousands of rupees, thousands of dollars. It can improve our lives in a great way. And also the sun is, as with global warming and these environmental and climatic changes are happening, we are getting more sensitive about how the sun affects our weather and our climate. So sun will also be, the sun is also a great, factor in affecting the weather and climate of the earth. And in spite of saying this, although the sun has been there for around 4.5 billion years, but we still don't know a lot about the sun, because mankind is very young and there is a lot to learn. There are lots of mysteries of the sun that are yet to explore. And the advantage is that the sun is a star which is right in front of us. We can do so many things, and we can observe sun at such high resolution, which we cannot do for the other stars. If we observe the sun, we'll get a good picture of how dynamics are happening in other stars, in other galaxies. And like these blazars and supernovae, black holes, how these are happening, we can get a good idea of these things if you understand the inner dynamics and inner workings of the sun. So with this, I would like to end my talk. Thank you, everyone.
Thanks, Janmejaya. think that was a very comprehensive look at solar physics and this amazing instrument that you guys are building, which will basically go on to this very path-breaking kind of a solar observatory to be there in space. Such a proud moment it will be when we see it launched very soon by ISRO, with all your efforts, including people, and not just you, but all your colleagues in the labs working hard in contributing to this. So thank you for doing that all through the year, and also for taking out this time to share all this on our National Science Day online celebrations today. Since it was very comprehensive, and we have the next talk also about space weather, which you mentioned at the towards the end, which is very important. We'll not go too much into questions, but there are questions on the YouTube chat. If you're looking at the YouTube stream, please feel free to answer them there. But I will catch you for one question, which is, how did you get inspired to come into this field? And if there are any, pointers that you would like to give to the youngsters in the crowd here, please feel free to do so.
Yeah, sure. So my first inspiration would be my father. So he has been an amateur astronomer since the 80s. Okay. And he works very actively. He runs an organization called SWAN, and he works very actively in science popularization, imaging, chasing eclipses. So I have been doing these things since I was a kid. I got exposure. This is one thing that many children don't get, but I was lucky enough to get all the exposure through telescopes, cameras, and equipment, and that got me interested in instrumentation. And I've always loved the instruments more than the sky, actually. So I would say that it came from my father. But one thing is that I've always wanted to come into astronomy, but it's no doubt it's a tough journey, passing through all the exams and masters and bachelors, then entering PhD. That is no doubt a tough journey, but if you want it hard enough, somehow something will happen and things will fall in place. I believe so. So you just have to want it hard enough, and you have to love astronomy. That's it. If you like it selflessly, then things will work out automatically. That's how it happened for me. Things just fell in place.
That's so wonderful. Yeah. So love and hard work both went into your success story. And I hope many youngsters will follow, and then we will have actually, people using these facilities that you're putting your efforts to build. I'm sure they will be generating a lot of data also. There will be students required to analyze it and make sense of it. So great, and thanks for the inspiration, and thanks for coming here. We'll go on to our next speaker now. At this hour, 1 o'clock, we have Professor Divyendu Nandi joining us from IISER, Kolkata. Well, let me just say that, hi Divyendu, welcome.
Good to see you.
Good to see you here. From so far off, it's lovely that we are able to travel online and meet you there. So I was just mentioning IUCAA's associate program, which basically links together various researchers and teachers from all over India in the university sector. And the Inter-University Center for Astronomy and Astrophysics, as our full form stands for, is the link to all the researchers who are interested in astronomy and astrophysics coming together on various platforms and using resources at IUCAA. But then Professor Divyendu Nandi leads a particularly active group which studies the sun and its effects on the surroundings. And so that is something we are eager to hear about. And without taking further time, I pass on the stage to Professor Nandi. Thank you.
Thank you, Samir, for that welcome note. And it's a pleasure to be part of this celebration of sciences in India. And thank you to the IUCAA Skype Up division for putting this act together, involving people from around the country and enabling joy of science to get through to all the students. So thank you, Samir, for also inviting me. So today I'll be speaking about uh, the weather in space and why should I bother about the weather in space. And I hope that you can see my slide and it is full screen now. So as Samir said, I come from a different place. I'm not in IUCAA. I'm from the Institute of Science, Education and Research in Kolkata, where I'm a physicist at the Department of Physical Sciences. And I am also associated with the Center of Excellence in Space Sciences, India, where we have significant collaboration with IUCAA in solar physics, in national space mission development, as well as the LIGO India network. Okay, so many of you have sort of grown up, even I did, with the textbook understanding of outer space, or the space between planets, with the sense that it is completely empty and void of any significant dynamic activity or changes. And this is the notion that most of us actually still have, unless you are an astrophysicist or unless you are somebody who's directly involved in studies of our space environment. In fact, the outer space around Earth is not empty. It is filled with the radiation, high energy photons, energetic particles, and magnetized plasmas that is being spewed out by our parent star, the sun. What you see here is not cartoon, it is not a model, it is actual observations based on certain techniques that can image the passage of this plasma disturbances from the sun outwards. And you see the sun in the center here, and you see for comparison, in order to understand where is the perspective from Earth, Earth's orbit has been put here and the Earth has been placed here. This is obviously not to scale because the sun is much bigger. But what you see here is in this actual observations of this interplanetary, what I call interplanetary transients or storms from the sun. They originate in the sun, they move through interplanetary space in every direction, and sometimes they can be Earth direct. This image is been reconstructed through months of observations at the radio astronomy facility in Uti, TIFR, from one of our senior colleagues, PK Monoharan. I really like this image because this is an Indian facility which drives home the point that there is weather in space and it is changing. And the point is, what does this changing weather do to us? Before we get there, let's talk about the origin of space weather. Where does it originate from? So when you look at the solar system, the most dynamically active astrophysical object in the solar system, in terms of how fast this activity can change, in terms of how much energy is there in this activity, is the star that we orbit, which is the sun. So if you look at the sun very closely through telescopes, then you see sunspots, which are very concentrated dark regions. It appears dark because it inhibits the convective transport of energy from the interior of the sun. This magnetic structures sometimes seems to go unstable and generate what are known as solar storms. Technically, they're called flares or coronal mass ejections. These are extremely energetic. They're so energetic that a solar flare or a solar storm has the equivalent energy of a few billion atomic explosions happening at the same time. So a solar flare has the energy equivalent of a few billion atomic bombs. So imagine the amount of energy that's being liberated in each of the storms. And there are often multiple storms in a month when the sun is in a very active state. When there is a high energy release within sunspots on the solar surface, this explosion energizes the hot outer atmosphere of the sun, which is known as the corona. And you see that in this satellite image. These are all, by the way, observations from space-based satellites. You don't see the sun like this because the atmosphere cuts out this high energy radiation. But if you place these instruments, which can image the sun in extreme ultraviolet or ultraviolet and X-rays, you can see this beautiful dynamics that's going on in the solar atmosphere. So when there's a storm, this outer part, a little bit of that atmosphere is energized and thrown out of the sun, and it travels at supersonic speeds out of the sun, and it's made up of super hot million degrees plasma, which is also magnetized. And what we see here is another movie which has been made from multiple satellite observations from the European Space Agency SOHO satellite. So you block out the sun because it's very bright, and if you have the sun there, you don't see the faint structures outside. But if you block out the sun, then you can see the propagation of these faint structures from the outer atmosphere of the sun, and you see these coronal mass ejections, or a large part of the corona being ejected out of the sun, and these storms travel through space. And when Earth directed, they can create significant disturbances in the near Earth space environment. And this storm occurred on 29th October of last year and generated severe geomagnetic storms just during Diwali. So we sort of dubbed it the Diwali storm of 2021. So what happens when these energetic particles from the storms, which are accelerated due to this high energy and heating of the solar atmosphere, reach Earth? So these particles travel close to the speed of light, and they reach Earth in about 8 minutes, and they impact the sensitive sensors of our satellites, and they can screw up the electronic elements in the sensors, and therefore sometimes render satellites completely useless. Often this magnetized plasma, which has a larger density than the interplanetary medium, while it's moving through, can create enhanced friction or drag. It's like you are walking into a cyclone and you feel the wind and the dust, and it kind of pushes you, something similar. And that reduces the energy, the velocities of the satellites, and they can deorbit. So their lifetime can reduce. And this is what very recently happened. Just, I think, 2 weeks back, to about 40 Starlink satellites, which was hit by a solar storm soon after launching. And unfortunately, they and deorbited, and this whole suite of satellites was lost. These energetic particles are also hazardous to astronauts who are out on a spacewalk, and therefore they also impact health of humans who are out in space. They also create beautiful phenomena called aurora. When these energetic particles impact the Earth's upper atmosphere, they energize atoms to a higher energy state, and when it comes down, emits a photon when it comes down to the ground state. And based on this energy of the transition, you can see these photons emitted at different wavelengths, which then lights up the sky in beautiful colors, which are distinct and is dependent on what sort of atoms or molecules are transitioning down and emitting this light. You see these auroras primarily in the northern, very high northern or southern latitudes because of certain reasons, which I'll not go into, but this is one of the most beautiful phenomena that you observe in Earth, and this is actually due to the space weather. The sun's high energy radiation also changes with time. And typically when there are this active regions or magnetized sunspots on the solar surface, it tends to emit more high energy radiation. And this is an image from, again, the SOHO satellite. And you see that whenever there is this magnetic structures, the extreme ultraviolet radiation that the satellite is measuring is enhanced, and you see the structures bright in extreme ultraviolet. They in fact also bright in high energy X-ray radiation, and therefore this variability of the sun also introduces such a changing radiation environment in space. We are lucky that this high energy radiation is cut off by the Earth's upper atmosphere, so we are not subject to this. Otherwise, this would be disastrous to human health. Now, it is interesting that the sun's radiation is variable, because until the 1970s, we were not aware of this and used to call the solar energy output as the solar constant. Now, in 1978, we put satellites up in space. And since then, we see this variation in what is known as the solar irradiance. These are small variations, but nonetheless, they're there. And you see the sun has a magnetic cycle of sunspots. It increases and decreases the 11-year period. And it turns out this variable radiation is perfectly coupled to the sunspot cycle. So whenever there are more sunspots or more magnetic activity in the sun, the variability in the radiation output is increased, and a more higher flux of high energy radiation comes into Earth. And this is in fact primary natural source of energy driving all planetary systems, including Earth. And this is what provides life. It provides the energy for photosynthesis. If we could harness solar energy in half an hour with a reasonable sort of surface area with solar cells at a very highly efficient manner, in half an hour, we could have enough energy from the sun, just the light of the sun that reaches Earth, to power the whole annual needs of humanity. That is significant. And this is why there's so much research going on right now to try and harness sunlight through solar cells, more and more efficient solar cells. Okay. But what is the other impact over long term? So over very long term, over hundreds of years, centuries, the variability in the sunspot cycle is very strong. And sometimes the sun becomes completely inactive in terms of its magnetic cycle. And that happened last time between 1645 and 1715 AD, a period known as the Maunder minimum, during which it is known that some rivers which never freeze, like the Thames and the Seine, actually froze. And you see this painting, I think by Henrik Averkamp, which shows a river near Holland, in Holland, near, I think, Amsterdam, completely frozen over during this period, and people getting out there and walking and skiing on the snow, which is highly unusual. So this most severest part of what is known as the Little Ice Age coincided with the Maunder minimum. And the question is there then a direct link between sunshine, or the amount of energy the sun gives out, and the changes in global climate? Well, over long term there is, and people have been worrying about this particularly because we want to figure out what is the primary cause of global warming. People have done thorough research on this, and we now know that over the last 100 years or so, the sun is not the primary driver of the global climate change that we're seeing. It is human-made or anthropogenic causes like greenhouse gases, which is the primary driver of climate change. And to reach that conclusion, one must carefully study the contribution of solar energy changes to climate change and distinguish that from anthropogenic causes. So this field is extremely important for our future. Now, space weather actually impacts all of us. It impacts you. This is because you are probably sitting somewhere right now. If you have a mobile phone, you are probably on YouTube live stream, listening to this talk, or you are sitting in front of a laptop, which is in the backbone of an internet, which is either being beamed out through a modem, which is connected to the nearest tower, from there to a satellite, and then to the whole wide internet. Or if you're in a mobile, the same thing happens. You're connected to a tower and then again to the internet, right? That depends on satellite telecommunication backbone and technologies. This is impacted by space weather. GPS navigational networks, if you've used Google Maps, you would know how important it is for our lives in order to find a place, how dependent we have become on navigation. The global navigational network of satellites is completely dependent on space weather, particularly because when there's a big solar storm, there are positional errors in the satellites. They basically almost are in a wave which shifts their positions quickly. And errors arise in sort of triangulating where you are communicating with the satellite with the satellite. For example, each of our phones has a GPS receiver, and that's how they track where you are and place you on a map. And this kind of positioning gets compromised. When you are in a high latitude country, like for example, Canada, US, Sweden, Russia, any element which has very long conductors like electric power grids or oil pipelines are subject to space weather, because these geomagnetic storms are most intense in these high latitudes, and they can completely take down a power grid when a strong solar storm hits. This is rare, but it happened in 1989, where a solar flare took down the North American power grid, and Quebec, Montreal was out of power in the springtime for about, when it's very cold there, for about 3 days. And the underground rail came to a stop. Heating in the houses, which is very important in this winter time when it's very cold. was compromised, and it impacted millions of people. And you see that the headline from the newspapers around that time. Air traffic over polar routes. If I'm flying from New Delhi to New York, conserve fuel, aeroplanes generally chart a flight track, which is over a great circle. I mean, mathematics and geometry tells you if you're on a sphere and I want to connect 2 points in the sphere, I should follow a great circle. So the great circle goes over the North Pole if you're going from New York to New Delhi or vice versa, for example, right? But the polar regions are more susceptible to the impact of a changing space environment because the Earth's magnetic field lines are open there and the storms can rush in to lower altitudes. So sensors in flights and high frequency communication between the flights and the ground stations gets impacted. So flights are in fact compromised. So whenever there's a prediction for a solar storm, generally the flights are not routed through the polar regions. And so there is this multiple different ways in which each of us are being impacted, and we're not even aware of it. The space environment plays such a big role in modulating or influencing the technologies that we have taken for granted. Even satellite-based broadcast, TV broadcast that has come through satellite dish is dependent on space weather. Okay. We also know that over long periods of times, like millions to billions of years, over generations, that is way beyond us. Okay. Changing star, changing sun, and the output of this changing star influences planets and its atmospheres. So the sun's radiation, its plasma wind, and the storms, they impact the atmosphere of planets. How does it do it? So these flowing storms and winds can literally couple to the atmosphere of planets, and through frictional coupling, slowly erode away the atmosphere. It's like you take a bunch of like powder or some tiny dust grains in your hand and you hold it up in a strong wind, and the wind will blow away those dust from your hand, right? Something similar. Now, this is a process that can be stopped if the planet has a surrounding magnetosphere. So the Earth, for example, has a magnetosphere. This magnet from the sun and doesn't let the storms and winds enter the Earth's atmosphere, and therefore we are protected. However, for Mars, if you look at Mars, about 1.5 billion years into its lifetime, when Mars was 1.5 billion years old, it had a magnetosphere because it had what we call a dynamo mechanism in its interior, which produced a strong magnetosphere which could protect its atmosphere. And it is thought that at that point in time, Mars had an atmosphere, significant atmosphere with greenhouse effect, warm temperatures, moist atmosphere, which was conducive to life. Then something happened and Mars lost its magnetosphere. And if you look at the Mars that we have right now, the atmosphere is pretty much almost lost. There's a very thin, almost like literally 100 meters or something like this, thin atmosphere, rich in carbon dioxide. And we believe the impact of that is the surface of Mars is now no longer suitable for hosting life. And this has happened because after the loss of the Martian magnetosphere, this invisible magnetic shield of the planet, the solar storms and solar plasma winds, which is extremely fast, supersonic, traveling at 500 kilometers per second, essentially eroded away the Martian atmosphere and has resulted in this inhabitable planet that we see now. And therefore, our activity of the star also impacts planetary atmospheres, its environment, and determines whether planets can host life. So essentially, habitability depends on this astrophysical ecosystem that is shared with our parent star. Now, how do we explore this physics, this domain of astrophysics, the solar system? We can do this via 2 ways, via observations through ground-based telescopes and through space-based satellites. For example, there are multiple spacecrafts now observing the sun and the space environment around us, which is primarily developed and launched by NASA and ESA, and a couple of them by JAXA. India is planning its first satellite to observe the sun, the Aditya L1 satellite, which is to be launched hopefully sometime within the next 1 year. And in fact, IUCAA who's hosting this Science Day celebrations, is developing an instrument called the Solar Ultraviolet Imaging Telescope, which will look at the ultraviolet emission from the sun and image these magnetic structures which produce solar storms, and also look at the contribution of changes in the ultraviolet radiation to the total energy output from the sun, which is fundamentally important for feeding into models of global climate change. So this mission has 7 instruments, and we are involved with IUCAA in building one of them, which is the Solar Ultraviolet Imaging Telescope, and many of us are involved in science that will be coming out from all the different instruments that are there. It's a comprehensive observatory, and I'm not going to details of that because you have a talk on the Aditya mission anyway, which you're going to listen to. India is also going to develop the National Large Solar Telescope and place it in this beautiful location. This is the most likely location of this, near Pangong Lake. Many of you would remember Three Idiots. The last scene of Three Idiots was shot near Pangong Lake. This is where the National Large Solar Telescope will be placed. It's going to be one of the largest telescopes in Asia, if it is deployed in time. And it will study this magnetic structures of the sun in very high resolution. And these structures are the one that generate this dynamic activity and the storms. And we hope that through this very high resolution observations, we'll have a better idea of what produces this severe magnetic storms and perturb our space environment. We also use computational modeling to capture the internal plasma flows that occurs inside the sun to generate this magnetic activity. And this is one of the models that we have built. And you see here, the sun opening up in this simulation, and inside this different components of the magnetic fields being generated and transported in the interior, and then they escape out to the surface, producing what we call sunspots, which then generate this other set of activities like solar storms. We can also, through modeling in a computer, simulate the magnetic fields in the corona, which eventually give rise to the solar storms. Because instabilities in these magnetic structures in the solar corona generate the solar storms. And we can compare these models during eclipse observations when the corona becomes visible. And here you see one of our modeling results being compared to the background white light corona, which gave a very good match. And this is the way we sort of either constrain our models or prove that the model is in the right path or rule out certain models. This is how theoretical work and modeling work in conjunction with observations help us advance knowledge in the sciences. This is an interesting thing I want to talk to you about it. I don't think many of you know, where did the name coronavirus come from? This is something that all of us worry about today. This is something that we are living through, this pandemic. Well, this is the solar corona. And this is how the spike protein structures of a COVID molecule, SARS-CoV-2 molecule, looks like. Okay, I'll show it to you again. And now you realize that the name corona has actually come from the solar corona, which is essentially crown, Greek for crown. And the structures, these magnetic structures, which kind of looks like the spikes here, is similar to the spike protein in the COVID molecule. And therefore, we call this the coronavirus. We also produce models of the interaction of solar plasma winds and storms with the Earth's atmosphere and its magnetosphere. And what you see here is the solar winds, and the white lines are the magnetic fields of the sun coming from the left. And these closed lines which converge on the Earth here are the Earth's magnetic fields. And you see that this bunch of compressed field lines from the Earth's magnetic field facing the sun essentially forms a dense region which literally stops the solar storms and solar wind from penetrating further, closer to the Earth's atmosphere, thereby protecting it. So these simulations and models, this theory that we develop, helps us understand how stars and their activity interact with planetary atmospheres, and helps us assess the space environment as well as conditions that make life possible in planets. So I will just summarize now. Take-home points that you should remember, having seen this talk, is that our star, the sun, is actually variable. It's not constant. We just feel that it rises in the east and sets in the west and doesn't change. It changes. And I hope that I've been able to convince you through observations from satellites. It's highly dynamic. So the sunshine, the energy from the sun sustains life and drives planetary climates. The activity of the sun also controls and modulates the environment around us, which is known as space weather. And this changing environment can sometimes become extreme and is hazardous to our satellite-based technologies, much of which we use on our daily lives, as I've talked about. And we also, from our theory and modeling, know that over very long periods of time, the activity of the sun also influences planetary atmospheres and the possibility of hosting life in planets. So it can be a life giver. It can also take away life from planets when a planet loses its magnetosphere. And it is important for us to be able to understand this intimate relationship that planet Earth and we share with our star, the sun, so that we can understand it and predict our space environment and the weather in space, not only to protect the space-based technologies that we have, but also to understand what is our future in this astrophysical ecosystem that we share with our parent star. So with that, I thank you for your attention, and I end by just leaving this slide here where you can find my contact information and more information about our institute and the Center of Excellence in Space Sciences India, which also has IUCAA as a partner, where we jointly run research programs in solar physics, space weather, and also in gravitational waves. And we have multiple programs that may interest you, starting from integrated BSMS programs to MS in space physics program to a PhD program. Thank you.
Thank you very much, Dipendu. This is, I don't need to, you've summarized the topic very well. And then this is another guideline which all the youngsters are expecting on how to come into astronomy, how to contribute to astronomical science. And this is, I think, one of the best places to join amongst all the great research institutes in India. So we look forward to more talks coming up in the next few hours. Bendu also mentioned the talk about the Aditya L1 mission. It was just prior to him. And if you have missed it, please visit our YouTube channel and you can just rewind this live stream and look at it again. So with that, I think we are coming to the end of this half an hour. But of course, we have like some young tiny tot to answer. So this global view that you have created of the space weather and its importance is well taken, but they are slightly curious about, just hold on. So they're curious about what is the sun made up of? What is the form? Is it solid, liquid, or gas?
Okay.
The young students, Revan and Prachi, I think, in school level.
Right. Okay. Thank you for that question. It's a nice question. So the sun is made up of hot plasma. Plasma is often called a fifth state or another state of matter after solid, liquid, and gas. So because the sun is extremely hot, the interior of the sun exists at temperatures of exceeding million degrees Kelvin. The center is like 15 million degrees Kelvin. The atoms get completely ionized. They get energized and get broken into a ion and the electrons, which essentially come out of the atoms, thereby leaving a positive charge and this negative charge. So a matter which has been made up of these charges, positive and negative charges, is known as plasma. So super hot plasma, and it is in a fluid state. So for example, water, gas, our atmosphere are also in fluid state. The interior of the sun is also in a fluid state. There are motions of this plasma inside the sun, which produce this large-scale electric currents, and that is at the basis of how the magnetic fields is generated. Someday we'll learn about the Maxwell's equations, and we'll learn about it, how this electric fields and the motion of plasmas end up generating magnetic fields. So yeah, so it's like a fluid.
Great. That's a great answer and simple enough for them to understand. Thank you. We also had you tweeting a few days ago, because you're very active on social media. So please follow him, everyone. So you had tweeted in detail about these Starlink satellites which got affected by a solar storm coincidentally. Is there some place to find more information about it, or maybe if you could?
Yeah, so there are no research papers yet. People are sort of, I think many people are working on this. We are too, trying to figure out what exactly happened. So if you look at, so I actually tweeted out a link to the official release from SpaceX, who did their own in-house analysis to conclude that what happened was, as soon as the satellites were launched, and they were low Earth orbiting satellites because they need to be close to Earth to be able to communicate with the ground stations for giving the internet services that's their business. As soon as they launched, there was this solar storms which hit, and it hit up the Earth's upper atmosphere, which expanded up. And due to the increased atmospheric drag on the satellites, they lost energy and sort of fell further down into the atmosphere, lost more energy, fell further down. It is almost like a runaway unstable situation, but they essentially completely burned out by entering the atmosphere. There is this release from this preliminary analysis in the SpaceX website. And if we just do a Google search on Starlink satellite space weather SpaceX, just use this keyword, Starlink satellite space weather SpaceX, you will find those resources.
Great. So I'm sure people will be at it right away. So thank you for this lovely talk, covering all sorts of effects that space weather has on us, and really highlighting the importance of it, and also the importance of youngsters to join the new team, the new age team, to study it in the future. We'll be a spacefaring race very soon, I'm sure. This will be one of the most important things to be studied. So thank you for
hosting me as well. I wanted to kind of also acknowledge the service that IUCAA Skype is doing in terms of engaging researchers from around the country in doing this outreach events, which is quite inclusive and nice. So thank you to IUCAA for hosting me and for doing this event.
It's a pleasure. It's a pleasure. So with this, we'll go to the next event. Thank you, Dipendu. We have actually a lot of good events lined up in the coming hours. And one of the most popular ones would be Professor Jayan Narlikar answering several hundred questions, not all of them, but a selected few from the several hundred questions that we received over the last few days. So please stick around till it starts at 2 p.m. And then in the afternoon, we have three special events, three special talks, and they are covering instruments and observatory facilities that India is a part of. And these are not just small, partnerships, but India has a major chunk and major role to play in these huge observatories that are coming up either in India or in somewhere in the world. So these will be covered under Great Observatories in the afternoon session with three special talks. In the evening, we have a talk about a very trending observatory which has just been launched on Christmas Day, 25th December. The James Webb Space Telescope went up into space and everybody saw it live. But where is it now? What is it doing? What are the people working on? You can listen to it right from one of the main scientists working on commissioning the telescope. So Dr. Swara Ravindranath will be with us from the Space Telescope Science Institute in Baltimore, and she will be giving us more insights and a lot of tidbits about this telescope. So stick on this. Please make a note. This is at 6 p.m. and it will be followed by a live sky show. So all these things are lined up nicely, and we are hoping you will keep joining us, and you are also going to tell your friends and family to join us during the whole of the day. So I'll pass on the baton to Shivani now, who will introduce the next event, which is also very interesting. So please stick on.
Yes, sure. Thank you. So now we are done with a lot of talks about astronomy, and we will be going further in the day with many talks yet to come. So now, before we have the Ask a Scientist session at 2 o'clock, we would like to show you, unfortunately, as you people could not visit us here in the campus, like every year, all of you visit us in the campus, and like there are like 15,000, 16,000 footfall. So we would be happy to show you a walkthrough, and so that you can get a flavor of it. Not only our campus, but we'll be showing you the IGO campus too. And I would like Atharva to join us. Yes. Okay. So good afternoon, Atharva, and he will be guiding us whole through the walkthrough. And he is also a project assistant here at IUCAA, and we all together have contributed to make this a great event for you all. So thank you so much, and over to you, Atharva.
Without further ado, let's begin. So before I start the walkthrough, now I'm going to leave my video off, so it will not get in the way of the walkthrough. I'm going to keep the whole walkthrough screen active all around, and I'm going to keep on talking in the background. So I hope now you will be able to see the website that we have already hosted, right? So in this website, you can see that there is IUCAA campus in virtual reality, which is mentioned. And then when you move over to the, you just scroll down, you can see two images. So this is image of the main IUCAA walkthrough, and this is the one about the IUCAA Gravity telescope. Now let's enter IUCAA. So once you enter IUCAA, and once this play button appears, your walkthrough has loaded, right? And on clicking the play button, the walkthrough will start right at the entrance of IUCAA. Now, for those who have visited IUCAA before, you must know that this is the exact central spot just opposite to the IUCAA main entrance, and exactly behind me, I will be able to find the Chandrasekhar Auditorium, right? Let's go full screen now for a better experience. Now, you all can try this with me on phones also. You can also do this on any of your iPads, laptops, computers. And those of you who have special VR gear, which allows you to attach your mobile phones into a VR gear and get a lot more immersive experience. So let's begin the campus visit. So you will find such posters floating around in the different parts of the campus, right? So this poster will tell you about the different activities that our scientific public outreach program does, so which is known as the IUCAA SciPow. Now let's begin with the main campus visit first. So let's head to. So before I begin the IUCAA campus visit, let us just carry it on as we do it on every Thursday. So on every Thursday, IUCAA is open for the common public to visit, and this is when there was no COVID restrictions. So we hope that we will be able to see you all again very soon. So as you can see, this entire campus is made up of different types of granites, and different modern architectural techniques have been used. And this campus has been designed by the famous architect Dr. Charles Correa, and he and his team have done a wonderful job in designing this campus. And you will find a lot of thought has been put, and a lot of good use of mathematics and fractals has been used in designing this campus. So we will talk more about that. So when we enter IUCAA, you can see the big IUCAA logo in front of you, right? So this IUCAA logo represents the infinity symbol, as well as it represents the collaboration. So IUCAA is nothing but the Inter-University Center for Astronomy and Astrophysics. So this is an inter-university center which helps universities get together and collaborate to do research activities. Now we are a research institute, which means we have students, but we are also involved in a lot of mega science projects as well as other research projects, both at a national as well as the international level. Now, when you enter IUCAA, you can see there is a video by our director, Professor Somok Rai Chaudhary. And if you click on this video, a YouTube video will start where he will welcome you. So you can also find the IUCAA introduction when you click on the logo over here. And similarly, you will be able to play learn more about the IUCAA in itself. And all across the campus, you will find these images attached. So the red symbol will represent where you are in the campus. So why we have put up these images? So there are different places in our campus which have been named after different astronomers or mathematicians from India. And to get an idea of what Aryabhatta complex is, what Bhaskar complex is, what Varahamihir complex is, so these maps have been added. So over here in the walkthrough, you can also find the schedule, right? If you click on this, then the schedule will open, and you can immediately take a look at what all programs are aligned next. So coming back to the walkthrough, let's enter the Kund area. So Kund is actually a metaphor for the expanding universe. Okay, so the Kund is basically the central foyer or the central region of the IUCAA, from where you can see all the characteristic elements of IUCAA. So once we enter to the central Kund area, you can see that the map shows that you are in the central Kund, and around us there are all these different important elements of IUCAA. Now in this Kund houses basically 4 statues of prominent astronomers and scientists and mathematicians. So this is none other than Albert Einstein, and you can also find the story of Albert Einstein, and there is also a science toy after that story. So if you watch these videos, and you can also show these videos to kids, so they will easily be able to make the science toys, and these are animated stories. So these are always fun to watch. You can also find our social media handles set up all across the campus. So you can feel free to follow us, and you can keep on getting updates on what we do. So this is the statue of Aryabhatta. As far as I know, this is the only statue of Aryabhatta in India, I think. So there is no other statue of Aryabhatta. You will find a lot of photos, lot of images in museums and different science centers, but this is the very popular Aryabhatta statue. Then this is the statue of Galileo Galilei. So he was the pioneer of he was a pioneer of observational astronomy, and he was one of the first people to use telescopes for astronomical observations, right? And this is the characteristic sky dome of IUCAA. We will also see that. And here you will find the statue of Isaac Newton, and another very famous scientist and another very famous astronomer. And he was a pioneer, and he discovered, or he gave us, the laws of motion and laws of gravity. So this is one more interesting feature in IUCAA. So this is the sky dome. Okay. Now what is special about this sky dome is this dome represents the sky on the night on the night when the IUCAA was formed, right? So IUCAA was established on 28th of December in 1998, and at the time, I'm sorry, 28th of December 1988, and at the time, on the evening 8:30 p.m., this was the star pattern in the sky. So this dome has been designed and built in such a way that on the night of 28th of December, this is something that you will really see in the sky. So this dome kind of simulates the sky on that night. And then all across the campus, you can find these information icons, right? So now you see these floating posters over here. So this is a poster exhibition which has been created by the PhD and the postdoctoral students as well as faculty at IUCAA, and they have done some amazing work. They have created these PowerPoint presentations, and they have put in a lot of efforts and a lot of details. So you can see in each presentation, if you go to some link, then you can simply scroll and navigate, and you can learn more about the individual topics. You can go back to the main presentation, and once you are done, if you close, you will return back to the walkthrough exactly where you were, right? So then this is the solar physics poster, and similarly you can go back to the posters homepage, and once you are done visiting the posters, you can go back to the walkthrough. Now we have divided this campus into 8 sections. Now if you want to jump directly to a section, so there is this home button over here, right? If you click on it, you can just simply scroll down and you can jump to any section. So let's jump to mega science section, right? So this is a very colorful and a very occupied section, I must say. Now notice that there is something interesting at the bottom. So you can see there are a lot of triangles. So these triangles are nothing but a fractal garden. So the smallest element is repeated multiple times to create the outer shape. So such designs or such objects are known as fractals, and can be generated mathematically. And this has been this is what we call as the fractal garden of IUCAA. And this complex is called as the Aryabhatta complex. So in front of me, I am looking at the Aryabhatta complex, and on my left hand side, exactly in front of me, this is called as the Devayani complex. Okay, so this is the area in which the students of IUCAA have their housing and accommodations. Now, if you go to the mega sciences area, you can find a lot of mega science project logos which are floating around, right? Now, just below these logos, you can find some information icons. So these icons are nothing but the resources of individual astronomy projects. For example, this is this is the link to AstroSat Science Support Cell. So IUCAA and ISRO and many such institutes are running different types of space telescopes and instruments in the space. So IUCAA has what is known as a Science Support Cell, where we work with ISRO and operate one of the payloads on the satellite called AstroSat, which is India's first multi-wavelength satellite. And similarly, then there are so many more projects. There is LIGO India, which is the upcoming project by IUCAA, in which the IUCAA is a major partner, but there are so many more institutes. These are the ones. And coming back to the walkthrough, you can find all the important resources around it. Now that we have seen the mega sciences section, we can now go back towards the code. So this is one way to go. So either I can keep on navigating like this, or I could have used the direct jump to section using the home icon. Now in this, let's also see another important structure in IUCAA. So over here, just besides Aryabhatta, if I enter inside the complex, I can find there is a Foucault's pendulum, right? So this is a replica of the Foucault's pendulum, but it is actually a working model. And the original Foucault's pendulum was built and it was kept at the Hall of Pantheon in Paris, right? And you can learn more about the Foucault pendulum using this video link. So all across the campus, you will find a lot of floating video links. So those are very short videos and those are very interestingly done to explain you more about whatever the exhibits have, right? Now going back, let's go back to the home or the IUCAA main gate now. Now once you enter the main gate, there is another block over here called Bhaskar complex. So in IUCAA, we have these Bhaskar complex, Aryabhat complex. So for example, here you see on the building name, right? So this is the Aryabhat complex. So this houses our offices, our administrative section, Foucault's pendulum, and also a couple of cubicles of postdoctoral fellows and PhD fellows, and our seminar rooms. Now, if you enter IUCAA, on the right hand side, you will see the Bhaskar complex. Okay, so we have 3 halls called Bhaskars 1, 2, and 3. And when you enter the Bhaskar complex, this area has currently been assigned to the gravitational wave section. So you will find excellent resources and a lot of resources about the LIGO India project. Then there will be these are the posters of GW section. These are very nicely done. You should definitely take a look. So these are some posters about additional links that you can visit. On this top over here, you can find careers in LIGO poster, right? So if you click on this information icon, the links to this QR code will open and you will be able to visit all of this. If you move ahead towards the Bhaskar 2 foyer, you will be able to see that there are these posters over here. So you can always zoom in and read, but if you are not able to, there is this PDF link to the posters which are displayed in front of you. Similarly, on the top, there are some important citizen science project links, which you will find all across the campus relevant to the respective posters. Now, over here, you can find some interesting exhibits. So these you ought to see. So this is the LIGO India suspension module. This is the vortex demonstration. So if I click on it, the vortex video will directly play, and you will be able to see these different simulations that we have put and different demonstrations that we have put. So going into the Bhaskar 3 complex or Bhaskar 3 foyer, you can see these beautiful artworks which are all over the IUCAA, and these have been drawn by different artists. Over here, we have set up 2 exhibits. So one is a stellar physics exhibit and there are some important citizen science project links at the bottom. And then there is a cosmology exhibit over here. So IUCAA has some of the best professors who teach cosmology, stellar physics, solar physics, and all such niche topics. And we have some excellent resources that we have enlisted here. So you should definitely take a look at it. Going further, we have a very interesting project that has come up in IUCAA, and we are building this new lab called Precision Quantum Measurement Lab. So how does a PQM lab work? What do they do in it? And all these things are going to be answered in the next sessions. So there is going to be a session on astronomy instrumentation. There is going to be a session on the radio telescopes. And there is also going to be a session on precision quantum measurement or an optical atomic clocks. So let's move on to this area. You can notice that there are these two banyan trees over here. And these two banyan trees are basically nothing but a Lagrange point exhibit. Okay, so this is another interesting structure at IUCAA. So you must have heard about the Aditya L1. So this is the L1 point. So imagine one of the banyan trees to be sun, one of the banyan trees to be earth, and around any two objects in space, there exist 5 Lagrange points. And then these Lagrange points are represented with the help of this structure in our campus. Then there are 2 more posters over here, and you can also find some important links. So this is the PQM facility or the quantum lab at IUCAA, which is on this side. And then there is instrumentation lab at IUCAA, which is on this side. And you can find the posters, and you can also take a look around in the campus. So let's go back to the Kund area, which is our central foyer region. And you can find a lot of, you can see the campus in much more clarity without too many hotspots over here. So these blinking arrows or information icons are called hotspots. Now moving ahead, let's go back towards the Varahamir lab. Okay, let's go to Bhaskar solar physics. Very well. So we have visited the Bhaskar complex, Varahamir complex, the Sky Dome, and the Foucault's pendulum. Now what we will do is we will visit the Science Center of IUCAA. So let's go back to the home, and in front of the home we have the Chandrasekhar Auditorium. So this auditorium has been named after the Nobel laureate Professor S. Chandrasekhar, and he himself has been to IUCAA, and he was we were lucky to have him inaugurate this particular auditorium. This has a capacity of 500 people, and usually we would be having all the sessions, live sessions and Ask a Scientist sessions over here. So in another 5 minutes we are going to start the session on YouTube live, but had we been offline it would have been over here. So this is the Chandrasekhar Auditorium. So this is the IUCAA Science Center complex. Moving along, so you can see in this region there are these exhibits, right? So this is a circle and there is a ring around it. So this is the planet Saturn. Then this object denotes the planet Uranus. This object denotes planet Neptune. And so all in all, the overall central theme of the Science Center complex is basically the solar system. So this gap over here is nothing but the asteroid belt. Okay. And if I move towards the Science Center building, you can see the planets between the Sun and asteroid belt. So this is Mercury, this is Venus and Earth, this is Mars, then this is asteroid belt, and over here there is planet Jupiter. And if you look here, there is planet Saturn. So we can go to Science Center, which is called as the Muktangan Vigyan Shodhika, and this has been built with the support from Shri Pula and Sunita Bai Deshpande, and this Science Center hosts a program called the Vigyan Tarang Lab, which is called as the famous Science Toys Lab at IUCAA. And Dr. Arvind Gupta was one of the important personalities who helped us build and spread the activities of this lab. So there are also video links with which you can learn more about what the Vigyan Tarang program at IUCAA does and what all activities are there. So now we can move to the Science Park, which is another important feature of IUCAA, after which we will conclude the IUCAA walkthrough. So in the science park, you can see a lot of different science exhibits. So this over here is the IUCAA sundial or the Samrat Yantra. And in front of each exhibit, you can find the details about what the exhibit is and how does it work. So there are these sympathetic swings over here. Then there is a lunar surface model. So let's not see these models in detail. You can spend your time and take your time seeing through the walkthrough. This is one of the first buildings of IUCAA. So when IUCAA was being built, this was the first building that they had constructed called the Aditi complex. Now this Aditi complex is our telescope making facility, a BSNL telephone exchange, and a small creche for our young children at IUCAA. Then we have this maze, which is a replica of one of the maze in London. And if we go towards the IUCAA main gate, you can see the sundial from the outer view. So going back to the main entrance, this was all about the IUCAA walkthrough. And just like IUCAA, we can also visit to IUCAA Giravli Observatory. So now I can fly to IUCAA Giravli Observatory. So I am back towards the Devani complex now. Now I'm going to click on this drone over here, right? So as soon as I click on this drone, I'm going to fly and enter the IUCAA Giravli Observatory campus. There we are. So this is the IUCAA Giravli Observatory campus. Now interesting thing about this walkthrough is we have added some good vantage points to take a good look at the sunset and the observatory. So this is the security cabin and you can climb up on top of it. Right? When you climb up, you can see a beautiful landscape because IUCAA Giravli Observatory is situated on the top of a peak, right? So we can see a beautiful landscape. Now we can go back to the entrance gate and we can go towards the accommodation and the canteen area. So I'm going to rush through this walkthrough because we want you to take your time and take a look at this walkthrough in detail. Now I will quickly head towards the telescope. And here you can see, you can directly jump onto the terrace or you can enter IGO. So this photo was taken right during sunset. This tells you that this is west. And I can enter IGO. This is the IGO control room. And this is where we really operate the IUCAA Giravli Observatory from. But we also are capable of controlling this telescope remotely right here from the IUCAA Pune campus. Now we can go and move on to the telescope dome. Now this is how the IUCAA Giravli Observatory looks like. And these hotspots are basically the more information about the telescope's mirror, what type of instruments are used, what type of cameras are used and all that. You can also go to the outside of the dome. So we had a hotspot over there which allowed us to jump directly to the dome, right? So we can go to the other end of the dome. We can see the landscape over here. We can go to the other end of the terrace, see the beautiful river and also the landscape over here. And then we can go to the upper level, which is used for the maintenance of the dome, right? So this is all about the walkthrough of IUCAA Giravli Observatory as well as the IUCAA main campus. Now we are going to switch over to the Ask a Scientist session, and we will come back to you in another 1 or 2 minutes. So stay tuned, don't go away. We are going to switch over. Until then, I'm going to play a small video which will tell you about the which will give you more information about IUCAA.
In the mid 1980s, UGC had started a new experiment that was to create centers of excellence in the university sector known as inter-university center. We got the first set of buildings in 1991 and the main campus was completed in 1992.
We have about 17 faculty members. At any given moment, there are 30 research students and there are about 25 postdoctoral fellows. Between them, this pool of very talented people are very productive.
between two
They
meetings.
carry
So
out
yeah,
excellent
so I
research
welcome
in
you all,
theoretical areas of
and
astrophysics,
the
in
audience is
cosmology and
really
gravitation
eager,
theory,
and we have
and also
like lot of
in observational
bulk of
areas
people
and
joined
in
at
making
2 o'clock
absolutely
for this
excellent
Ask a Session,
astronomical instruments.
Ask a Scientist
The
session.
research work which we
So
do in
I'm really
IUCAA spans
overwhelmed
a wide
that
variety
we
of
have
topics,
got
both in
the
theory and in
questions, and we
observation.
have got
In
entries even
theoretical
if this is
areas,
online,
we cover
and we have
almost all
received
areas
so
in
much of
astronomy and astrophysics.
enthusiasm from the
In
audience.
particular,
And so
cosmology
I'll not
and
take up
general
much
relativity
time, and
is
I'll
one of the
pass
main
on the
thrust
session
areas.
to
In
Anuprita and
addition,
Suraj.
there
Please.
is quite
Thank
a
you.
Welcome everyone to IUCAA's Ask a Scientist program. We are your hosts for today. I'm Suraj More.
And I'm Anuprita Mori. Happy Science Day. Even though we cannot meet you all and interact with you in person, this online version of our program is still a great opportunity for everyone, especially youngsters, to ask questions that they've always wanted to ask a scientist. We're very happy to see the hundreds of questions sent by mostly school and college students and their curiosity towards astronomy.
We are delighted to have our beloved Dr. Jayanta Narayakar, a distinguished astrophysicist and writer, as well as the founding director of IUCAA with us. He has been doing these Ask a Scientist sessions for many, many decades now, and you can see still the enthusiasm in him. Along with him, we also have Dr. Mangala Narayakar. She is a distinguished mathematician and writer. And then we have the current IUCAA director, Dr. Shomat Rai Chaudhary, as well.
We have received several interesting questions using the online interface. The questions this year span a broad range from fundamental questions of our existence to new science possible with upcoming technologies. We would have loved to discuss all of your questions, but due to limited time, we had to narrow down to a few interesting ones for our distinguished panel. So let's get started with the highly awaited Ask a Scientist program.
Thanks, Anu. So let's start with the first question for Dr. Jayant Narayakar. The question is, why do we only see one side of the moon? And how does the Earth appear from the moon?
Why do we see only one face of the moon, one side? And how will the Earth look if you see from the moon?
What is see right? Only
Because,
one?
why do we see only one side of the moon from the Earth? That is question 1. And question 2 is, how will the Earth look like from the moon?
So the first is, why do we
See
see?
only one face of the moon, not one side of the moon.
Okay, now you can see the following situation. Supposing you are the Earth here and somebody else is going around you. So if you stay putting in the same direction, then you will see both sides eventually of the object which is going around you. But if you are turning around too, and at the same time as the object is going around you, then it will act in such a way as to compensate for the effect. The result that you always keep the same side. And this has happened, what people call tidal interaction. It is like holding in one direction and putting in the opposite, all Gurutvakarshan. So this effect is to keep it facing you. And that is the reason that it happens.
I think you can have a model of it created by, if somebody who is supposed to be the Earth standing in the center and another person, the moon, going around it, ask the moon to face always towards the Earth while the moon is going around. This will give a better sort of imagination, because the gravitation twist that he explained may not be sort of very clear. But if this model can be created, then you can see that the person who is going around you, if that person is always facing you, you won't see the back of his head.
I think, as I said right in the beginning, you have two persons one standing here in the center, the other going round. And this one is turning towards this person who is going around all the time. So when this happens, you find that it's a very special size situation, and that is what is happening.
Yeah, it's quite interesting that the moon
Say one
always
thing.
shows the
Can I
same
say
face. Yeah, sure, please.
I just wanted to say one thing, that in IUCAA here, a lot of people would have visited IUCAA. In the science park in IUCAA, which is for people to play in, we used to have, and it's broken now, but for many years we used to have a play thing in which the Earth was at the center, and somebody could sit on a chair going around the Earth, and they were coupled such that the chair rotated once in the time the whole thing, and so somebody would push and the friend would sit on the chair and you could see you were always facing the Earth. So you could actually learn this by playing. I'm very sorry that that's broken now, and we will repair it. And so if any people are listening to this who can come to IUCAA later on in the science park, they can take a look at this.
That will be great. So we always look at the moon from the vantage point of the Earth. But how does the Earth look from the vantage point of the moon? That is the other part of the question. So if we are on the moon, then will we see the Earth rising or setting, or what will we see?
How do you see the Earth from the moon?
How do you see the Earth?
From the moon.
From the moon. You see we see the lunar crescent from here. So in the same way, if we are sitting on the moon and look at the Earth, we'll see the crescent of the Earth, and we'll see the part which is lit, and that part will again be like some kind of a crescent. But the problem is the following, that if you stand on the moon and look at the Earth, to say today and after a few hours, the Earth won't have shifted from where it was to another position. But what will happen is that it is staying in this apparently the same place. This is because as the Earth goes round, you are also turning around. And this synchronization causes the Earth to be to that crescent that you see, remaining the same from a given place.
Looks stationary.
Yeah. It looks as if it is not moving.
Yeah, that's something which is quite counterintuitive, because we always see things rising up and setting. But from the moon, if you look at the Earth, it just stays in the same place and is going round and round, I guess.
Very slightly, almost stationary.
Right. Great. Yeah.
Okay.
So maybe we can move on to the next question.
Yeah. So the next question is by Prachi Patil. She's 14-year-old and she's from Sangli, and her question is about atmosphere on other planets. Like, do they have atmosphere? How does it form? What determines the atmospheric content of a planet? Shramak, would you like to give it a try?
Of course. So that's a very, very, very interesting question. Actually, there is a belief that the Earth's atmosphere, the gases that are in the atmosphere like oxygen, nitrogen, carbon dioxide, these come from the activity of life on the Earth. That's not true. Actually, all the planets formed at the same time when the solar nebula collapsed to form the sun and the planets. And the elements that were there in that solar nebula went into all the planets, right? So Mars, for example, and Venus and Earth have the same elements that the Earth has. And now on each of these planets, there is a lot of activity that goes on, chemical activity, because of the variation in temperature. The planets receive the Earth's, the sun's light. And so there will be heat, there will be, there's a lot of pressure. And so chemical reactions go on. And so there's carbon there, there's oxygen there, there's nitrogen there. They, carbon and oxygen combine to form carbon dioxide. Nitrogen and hydrogen can combine to form, methane, etc. There lots of things will happen. Now, these happen because of conditions. For example, in volcanic activity, as you know, methane forms. So it's not that organic life forms these. Now, then over the planets have been around for 4.5 billion years, right? Over the ages, the atmosphere has remained in the Earth because the Earth's gravity pulls the atmosphere down. But in smaller planets, or maybe the satellites like the moon, the atmosphere that had formed because of the gaseous activity, the chemical activity, they have dispersed because the moon or the smaller planets did not have enough gravity to hold the atmosphere together. And in the atmosphere, different gases have different escape velocities. They are moving around randomly. And so carbon dioxide and oxygen and methane and nitrogen, they have different conditions in which they can escape. So certain gases escape from the atmosphere and certain gases remain. So Mars's atmosphere, for example, is 95% carbon dioxide or something like that, very high. But that has been produced all in the on Mars itself. It is not produced due to organic activity. But when people found methane, they thought, my goodness, there must be some organic material there. But then they realized methane is there because of some other chemical activity. So the atmosphere is always there. Moon's atmosphere is almost not there because Moon's gravity is so small that it could not retain its atmosphere. So the atmosphere, having atmosphere is natural. Actually holding on to the atmosphere is difficult.
Yeah, it is somehow, there is always this feeling that maybe we cannot go to other planets because there is no atmosphere there, but it's the composition as well as whether that planet can hold on to it, which becomes more important. Thank you, Shobha, for that answer. So let's move on to the next question. This is by Azan Khan, who is 18 years old. She is from Farrukhabad. So the question is, when you have supernova or when stars reach the end of their life cycle, then you form this ion, right, at the end. And then fusion stops. So how do we get elements which are heavier than iron? Like say gold, platinum, etc. So Javian, maybe?
Yeah. How are heavier elements than iron formed in the stars?
Heavier elements than
iron. Because up to iron, you have more or less a trajectory.
Yeah. See, after these elements like iron have up to iron have been formed, by then the star will have blown up into a very large size and a very, very hot star at that. And it reaches some kind of a what you call unstable situation. It cannot retain that state for long. So it can then explode or have minor explosions at the outer side. And as it explodes, the outer side goes out and falls on the star which is underneath. A situation will come that these neutrons and protons, which are freely moving in the outer part of the star, they combine with the existing nuclei, like starting like iron and so on. And then they will form these heavier nuclei, and then not with too many of them. In fact, the amount of gold in the star will be much less than the amount of iron in the star, because of the fact that the formation time is very little and the amount that is available to make into gold, for example, will be much less. So one can do all these calculations and estimate how these heavier elements are formed by having additions of neutrons and protons. And there are two ways they can combine. One is beta decay, which is neutron going to proton and electron, or some other reverse reaction. Now it turns out that the reactions are going at different rates. Beta decay is a slow reaction, for example. So all these things have to be included in your calculation. And this is the reason why definitive results began to come out only after computing facilities improved and one could do all these calculations more easily. And the famous paper in this context is B square FH, Burbidge, Fowler, and Hoyle. These four people, the scientists combined, each one contributing different part of their expertise. And then they were able to estimate all these different reactions. That was in 1956.
That's great. So it is really difficult to make gold. I suppose that is why it is so precious. Right? Shoma, could you also like to add something to this?
Yes. So then what happens is we also know that after a star goes supernova, then there are quite a lot of other things that happen. For example, like a star goes supernova, compact objects form, like neutron stars and white dwarfs and black holes. Now, then these neutron stars can merge into a black hole. We know that because we've detected them through LIGO. And a neutron star, and so material falls on the neutron star. It can actually have some really explosive effects, very high temperature, very high pressure. And it turns out the things like gold, platinum, etc., some of these metals actually form in merging neutron stars. The stuff that we've seen in gravitational waves, we know that it happens. Of course, if it becomes a black hole, then a lot of stuff goes into the black hole and you can't retrieve them. But in the process of these things happening, some of these higher materials that are found, elements that are formed, then in this explosive mechanism, then moves out into the rest of the galaxy. And there are some wonderful simulations that are being done to show how far these elements can go. And it turns out, normally they don't escape the galaxy, and maybe it goes to maybe some tens of kiloparsecs. And so one can see, I mean, once this kind of simulation is done, we would know the kind of things I'm made of, where they could have come from, or the gold that you're wearing in the form of a earring, where would they have come from? And they could probably come from maybe within a few hundred light years, that's it. And it's all made in various stars, right? And either inside a star, as JVN said, by the B2FH processes, or in heavily explosive phenomena. Like, for example, nickel is produced when the star explodes, and in the supernova remnant, as the supernova is expanding, nuclear reactions take part. And these things are made, stuff like that. And so so we are discovering all of this. But then how far can this element move from where it is formed to land in a planet like ours, and we can mine it and stuff like that, is a very, very interesting question. And people are actually doing simulations to find out how far you can go. And sometimes the galaxy can eject them, and it can go outside the galaxy. Most of it stays within tens of thousands of light years.
Yeah, that's really nice.
Yeah, so I mean, it's if you look at all these things that we actually use, they really come from stardust, right? And that's what astronomers like us would like to tell everyone. Okay, great. Let's move on to another question.
Yeah, okay. So the next question is by Shibani Chakraborty, who's a 19-year-old from Mumbai. I would like to ask this question to Mangala, ma'am, if possible. So this is a very broad question to ponder over, but it would be nice to hear your thoughts. Will computers replace humans in astronomy or in science general? Will computers replace humans in science or astronomy?
Yes. will computers replace people in working in science or astronomy or anywhere?
Will computer replace the...
Do you want to answer it? The question is for me, but you answer it, then I will answer it.
My feeling is that a lot of calculations which can be made analytically will continue to be made analytically, but there will be certain calculations which you cannot do analytically alone because it will take too long a time and you don't have the resources of doing the calculations, and the computer becomes a necessary tool for it. So such necessary tools will become more and more used, and therefore this will lead to computers playing an important role, but not, they can't do without it completely, but computers will be necessary and will be used more and more often. I can give you one example that this is what is called a four color problem, in which a long time problem was to explain that if you make a map on the earth of different countries so that neighboring countries are painted by different colors. If the countries are not neighboring, then they can have the same color. So what is the minimum number of colors that is needed? Now the answer expected was a four color problem. That means four colors will be enough to do this. But how do you prove it? The mathematician is not satisfied by your guessing or your intuitive feeling. He will ask for a proof. So when people finally got a proof, they found that they needed to have a large number of maps to analyze, to decide whether they needed only four colors. And they finally managed to prove this only by using a computer to enumerate all those figures. This figure, that figure was each identified by the computer, and the computer then showed that four colors are enough. Now, people were not very happy with this proof, but there was no way they could show otherwise. And so here is an example of the computer becoming important and essential for your investigation.
Yes, but the question was whether the computer can replace human being, at least at present, not only in our lifetime, but even in your lifetime. The answer is no. Why? Because computer does only what man tells the computer to do. Computer does not have the natural brain that humans have, that a child has. A 2-year-old brain is much, much richer than any super fast computer that you have on the earth. Why? Because a child's brain's learning capacity is so fantastic, and they are learning so many different things. It is not just language, but it movement with their own arms, their limbs. When the baby learns to recognize the relations, mother in the first place and then others, and then their responses to every speech, how do they differentiate the voice of mother and the voice of somebody else, or the looks of different persons, the smells. So all these things a child learns to sift and decide which is good for the child, which it wants. So there are so many complex activities a child is learning naturally. So what I mean, for me, God is the nature. So whatever the God has given to the human being, the brain, that is still not replaced by a machine, because the machine will do whatever you tell it to. You have to give the situations. Now, take the medical reports, for example. You give the medical reports, but you have to produce all the different readings of the blood sample, the bone scan, all those things. And then looking at those reports, the computer already has previously sort of given in the cases for which the situation is serious or which is not good. So the computer can compare and then help you to decide. But all this, how the computer should work, is totally decided by human beings.
Indeed, I mean, computers are getting more and more complex, but we have had a huge history, like billions of years of evolution working in our favor, I guess, for the moment. Shobhak, would you also like to add something to this?
See, I mean, computers, it's very hard to say. I completely agree with what has been said before. But I also must say, in my lifetime, I've seen computers go from huge things in which you put in large sheets of paper and whatever and cards, and then now it's on my phone. So I don't think 50 years ago I thought I would see computers go wherever it is now. So this is the stuff of science fiction, isn't it? And then Professor Naldekar has also written a lot of this kind of science fiction. If you remember his science fiction on artificial intelligence and PAM and things like that. So I mean, it's hard to tell where things will go. I would like to believe that can't take us over. I would like to believe that, but I might be proved wrong 50 years from now.
Yeah,
I think.
Sorry, go ahead.
Please go ahead.
I feel the example of chess will help. In chess,
yes,
there are computer programs to play chess with the best brains in the field. And for a long time, it happened that the human being, the human champion, won. But now the situation has come where the computer, in any given time, works faster than the human being able to do. Yeah. So it may still happen that there are certain tricks which the computer couldn't think of and we lost. But I think it is going to be harder and harder. That's my feeling.
Yeah, I think that the computers or machines, they are going to be as smart as our algorithms are going to be. And at least maybe for the near future, they won't really take over the job of thinking, which is what scientists do. But maybe a century from now or like a few centuries from now, there will be enough AI development that it will start to do things that we cannot even imagine now. So
yeah, so you can think about artificial intelligence where computers are then designing computer algorithms and so on, right?
Yeah.
So it can become quite complex. So we'll see how it goes. Okay. So the next question that we have is a personal question to Dr. Narayakar. This is from Krishna Kumar. He's a 17-year-old from Pune. The question is, how did you feel when you became the senior wrangler in the TRIPOS examination in Cambridge? What was your experience and
how did you feel when you discovered you were a senior wrangler in the Cambridge examination?
How did you
feel? What was your reaction?
Oh, the thing is, in the Cambridge examination, topping the list of wranglers was kept to be very secret, was not revealed. But what happens now and then, that somebody talks about something and it gets spread. And that way, some of the mathematicians or scientists who were wranglers, there was a discussion about their performance somewhere, and some of them were identified as senior wranglers. I remember when I won the wranglership, that is first class, I went to see my tutor, and the tutor congratulated me and said, good to be a wrangler, which is first class in mathematical tripos. Then I said that do you have any information whether what my position was in the class? So he smiled and he said, I'm not allowed to tell you. I know, but I'm not allowed to tell you. So I looked a bit disappointed. Then he said, you couldn't have done better. Then that was the nearest that he could do, like Narova Kunjarova in Mahabharata, as you know. So then he thought that he had given away too much. And he said, well, perhaps you could have done better, which is also true. If I stood first, some of the questions could be done even better, and I could have got even better language. So all these things were remaining there, and I didn't know the final answer until one newspaper man who had explored this thing, he telephoned me and said, I read that I have discovered that you were senior wrangler. And then he mentioned some of these problems.
But this was done many years after the exam.
Oh yes, not at the time of
this disclosure by the newspaper man was done after many years, not immediately.
Only about 10 years ago was it known. Whereas the examination was way back in 1958, 59.
I think the people also should know why they do not want to publicize who comes first, who gets the first rank and senior wranglership, because what happens is examination tests the students for their knowledge and their hard work and their capacity to produce answers. But what used to happen is the person who got the first rank always got a lot of credit and scholarships and all the honors. And the second and third rank students probably were equally good. But just because they could not do some problem or the other as well, they had a few marks less. So there was an uneven and unhealthy result as far as the first and the next rank holders were considered. That is why they decided not to disclose the ranks.
So I can give you one example that the famous physicist Maxwell, when he was a student, he was tipped to be a senior wrangler. So he was so sure of himself that he will be top. The results are announced at 9 o'clock in the morning in the Senate House, and people can go and attend the ceremony and come back with the result. So he didn't bother to go there because he knew he was going to be the top. He sent his valet, his servant, to go and listen to the results and tell him who stood second. So that's the student, that person, the valet, he went and came back with the result. Maxwell asked who stood second. So he said, you, sir. Because
somebody else was first.
Somebody else who was less likely to win had actually got better results.
Yeah, indeed. I mean, these kind of things happen, and that's why I guess this ranking can be a little bit tricky, right? But you have been a big role model for the youngsters around this country, and for us personally as well. So there were also questions regarding this, Anuprita.
Yeah, so you have been an inspiration to everyone, and I think this question is not just by one person. I think many people would like to know who's the role model for you. So if you could...
Who was the role model for you when you were a student or when you went to study at Cambridge?
Well, at different stages, different people were role models. When I was in school, my father, who was himself a wrangler from Cambridge, he was the role model, and I wanted to be professor of mathematics. That was my feeling. When I went to Cambridge and attended the mathematical tripos courses, at that time I could see some of the very brilliant people in action. And there were a lot of what you call people with who could be my what do you call
role models or ideals?
Role models. But Fred Hoyle, who lectured on electrodynamics, his way of approaching problems was such that I felt that after tripos, if I wanted to do research, I would like to follow his attitude of skepticism and not asking for proof when somebody makes a statement. And this is what I learned from him, and that is why I keep putting in questions which I feel have not been answered yet, but people take it for granted.
Yeah, indeed. I mean, this skepticism is so important, right? So I think this is the spirit with which we should celebrate Science Day, right? Where we should just have this ability or develop this ability in youngsters, especially, to question any of the aspects like dogma which come up, right, oftentimes, and many of the like fastly held beliefs. Right? So, Shomak, do you also want to answer about your role model?
Oh, a very difficult question, these role models. I mean, of course, academic role models are different from, as Professor Nalika said. I also grew up with a professor father who was an institution builder. He built various colleges and institutions. And certainly my father is my role model. For a different reason he was not a mathematics professor, and I became an astronomy professor. He was a literature professor. But the fact that he built institutions, he actually had a lot of students who thought he was a fantastic teacher, made me want to become a teacher. And likewise, when I went to Cambridge, as Professor Nalika said, he found in his lectures the person he used to want to work with. I too did that. In my very first month, I decided who I wanted to work with, and that was Don Lyndon Bell. And till his death, I think he was my second father. I worked with him very closely, and he was my mentor and guide all through my life. So these are, I mean, of course, there are many other role models, but I mean, in academically and career-wise, certainly they were my role models.
Yeah, thank you. That was useful to know. It's always good to have role models, and you should look out for them. Right? Yeah. So there's another question. This is regarding an interesting object which came in the solar system. The name of this object is Oumuamua. And so there has been talk about the origin of this object. So let me give the context. So there was this object which came into our solar system, and it was moving very fast. And it was just a visitor from from some other solar system, right, or from other star system. So it was not belonging to our solar system. It was on an orbit where it came to the sun and then just changed its path and went somewhere else. So there has been speculation about what this Oumuamua is. So the question is, do you think it could be a spaceship from another civilization? There are many alien fans here, I guess.
Do you know about this phenomena? There was some object which came from distant places, not from the solar system. It came very fast, went around our sun, and then changed the trajectory and went back. Well, what is the name again? I don't think I had heard it before.
It's called Oumuamua.
I can address.
It's a Hawaiian word.
Yeah.
Hawaiian word. It was like a comet, but not a comet. And because it had a trajectory which was not like a comet, but it was moving very fast, and it went around the sun and went back. So, do you think it could be some spaceship?
I don't know about.
He hasn't heard of it.
Yeah, no problem. I would like to ask maybe Shomak if you can.
I can take care of that. Actually, that happened very interestingly, because the reason Oumuamua actually was shaped like a cigar, an extremely sleek, long piece of rock, and it looked like it had been made by a civilization rather than naturally occurring. And the other thing was that it was on a kind of orbit which is very long, and it came from very far away. It was very clear it was not coming back. Whereas things like comets and asteroids often have orbits that seem like short period, or they come back and things like that. So this led some people to say, oh my goodness, this could be an alien spaceship, because it looked like those science fiction ones in which there is a small. And then a very influential scientist and astrophysicist, Avi Loeb from Harvard University, who has, and I will say this in public, who has the propensity of writing really outrageous theories about things, wrote an article, actually wrote a paper saying that this has to be something that's from outer space from an alien civilization, which spurred a lot of people to discuss this. Now, since then, there have been other things that have been discovered that are similar. Borisov is another one, which came the year after, which was very similar, a long kind of object that was found. And there is something called Project Lyra now that looks out for asteroids, which are finding things like that. So I'm pretty convinced it's not. I would love to believe it's an alien spaceship, but it doesn't look like it's very. There was no other really conclusive evidence that it could actually have aliens in them, other than the fact it's a funny shape and it was on a funny orbit. By funny, I mean unusual. I don't know. Maybe Surud and Anuprita also know something about it.
Yeah, so I think one of the reasons that it got so controversial is also that there was an acceleration in addition to the solar acceleration, which was also seen. And so that may have also introduced some more uncertainties. Of course, if these objects are coming close to the sun, there may be some sort of outgassing that might happen. And that could also propel it more than what you would just expect from the acceleration from the sun. So it remains to be seen. Most likely, of course, not. But I think that's the reason why people got quite interested about this.
Yeah, I mean, and also this is the first object, so to say, that we are aware of that has arrived from outside the solar system. It could be there are many such objects, but maybe our observations have not been tuned at that time, or the telescope maybe not as sensitive. And so going into the future, we will probably be seeing many more such instances, and it's going to be really interesting.
We have to keep observing and keep the records of them.
Yes.
That
is indeed. Indeed, that is very important.
If not in the next 10 years, if something similar is seen after 20 years, the records of whatever we have seen should be available to future generations.
Very
indeed.
And Indians are not very smart at keeping records.
Yes. We should definitely do that because, and I think astronomy is a field in which this usefulness of archival data comes up quite a bit.
Yes.
And I remember for the orbit of Uranus, for example, when it was discovered, they could go back many decades in order to find where Uranus was in previous images, right? And that helped to establish the orbit, and figure out that there should be Neptune.
So keeping the records intact and not tampering with them.
Yeah, all very important.
These things we have to observe as supporting science.
Yeah, indeed.
Yes,
indeed.
very much.
Yeah.
One more thing I would like to stress here is, since you were talking about working in science, different fields, like skepticism is necessary to test different theories and different predictions. What I want to state is that the very base is a curiosity. You should be curious about the space around you, about so many things around you, and you should want to know. You should want to know about so many things. So curiosity is the first requisite, and then hard work to find out the real answers, and of course skepticism. And what I like to say is a true scientist is always a Satya Shodhak. He wants to find the truth, and he will not compromise with whatever he has found.
Yeah, indeed. I mean, find the truth and stay on the path of truth, even if it contradicts your previous notions and beliefs. I think that is so much important, right? And something that needs to be inculcated in all the young people throughout the country and all over the world.
Yeah, so just along the line of curiosity, I think we have a curious question here from a 17-year-old from Mumbai. This is by Alok Tiwari, and the question is, was our galaxy also a quasar once? This question is for JVN. Was our galaxy also a quasar once?
Was our galaxy also a quasar long ago? Our galaxy, the galaxy in which we are, Akash Ganga, was it also a quasar before, in the past?
I don't see any reason, but if there is some evidence, I would like to read it. I am not aware of any proof of this kind.
Yeah, I mean, maybe we can frame the question in a different way, whether the nucleus or the central black hole of our galaxy, whether it was active before, in that way.
Yeah, indeed. So do quasars always stay the way they are, or do they change over their lifetimes or not? Maybe
I think this question is a little confusing for me. I'm not an astronomer, but I know just a little bit of it. Do you mean to say that galaxies can evolve out of quasars?
No. So the centers of galaxies, they have supermassive black holes.
Yes.
And when they are accreting, then they can become a quasar, right?
But the question was our galaxy also a quasar before? That means the galaxy has evolved out of a quasar. I did not know of such big sequence.
No, of course. I don't think that is not necessarily what the questioner meant, I guess. So I think it is just about whether, if you have a galaxy, can you have the central black hole in that galaxy become a quasar and then shut off and stop being a quasar, then become another quasar again after some years. So that, I think, is the line of questioning. Shoma, do you want to?
I can answer that. I mean, actually, what happens is that every galaxy, all major galaxies have a supermassive black hole in the middle. And depending on how massive the galaxy is, then if there's a supply of gas in the galaxy that falls into that black hole, in falling in, it creates a lot of energy that can be emitted in the form of a jet or in the form of some kind of a plasma moving at relativistic speeds, and as a result, this energy is emitted, and which can be seen from very, very far away, and that is what's called a quasar. So we call things that a quasar are, which you can see very bright from the centers of galaxies very far away, and that's why we call it a quasar. Now the question is, if some galaxy is very far away looking at us, will they see us as a quasar or not? And it turns out that the supermassive black hole in the middle of our galaxy is not very massive. It's only 4 million times the mass of the sun. Whereas in the centers of elliptical galaxies that lie in the centers of clusters and groups, they are far more massive. And they can be up to 1 billion times the mass of the sun, or even more. And so, and particularly since they are in the middle of clusters or groups of galaxies, the supply of gas that would fall in and cause this kind of outburst and activity, the probability is far more. And so the chance of a galaxy being an active galactic nucleus or a quasar is far more in elliptical galaxies and also in galaxies that are in groups or in clusters. The chance of a galaxy like us, which is not in really a group, it's in a pair of galaxies, quite isolated, and having a very tiny black hole, of having a huge outburst that's very far away as a quasar is small. So the chances are, I would say that our galaxy is not a very spectacular AGN, or has been in its lifetime, whereas there are nearby galaxies which actually can, we have seen Cepheid galaxies, other kinds of AGN, which can be very active. Spiral galaxies tend not to do that kind of thing.
Yeah, I remember some of these bubbles that were detected by Fermi as telling you something about the activity of the central black holes.
That's right.
That might be the reason.
That might be, yeah, but it might be a very small kind of outburst that would cause bubbles in the surrounding gas. But there isn't much gas in the local group, and just like you would have that kind of gas in the middle of a cluster, right? And so certainly there can be some activity, and of course there is a black hole, there has to be activity. But by a quasar, I think everybody understands that it is an extremely bright outburst that can be seen very, very far away, redshifts of 3, 4, something like that, as they were first discovered, things that were discovered, and so I don't think our galaxy would have become a 3C source, the kinds of things that we see in other galaxies. So all black holes have to be active. They have a duty cycle. Every 10 to the power 8 years, 10 to the power 90, in 9 years, they probably have some activity as gas falls in, but huge outbursts probably unlikely from our galaxy.
Thanks very much, Shomak. As we are coming closer to the end of this session, I would like to ask 2 questions combined together, which is regarding telescopes, maybe future telescopes and so on. So the question goes something like this. Will ground-based telescopes become obsolete after JWST? And how can amateur astronomers contribute to science when JWST is getting ready to detect faraway planets? So these questions are related to JWST, or telescopes, space-based telescopes versus ground-based telescopes, and how can just public, not just the amateur astronomers, but how can public contribute?
JWST is? Can you please explain JWST?
JWST is the James Webb Space Telescope. It is
Okay, James Webb Space Telescope.
It is the successor to Hubble, which was just launched, and it is right now being commissioned. We'll actually hear a talk about this in the evening.
All right. Can I start that? And of course you should contribute too, Surud and Anuprita, because you are great experts in this as well. What I want to say is, first of all, if ground-based telescopes become obsolete, it will be for a different reason. Ground-based telescopes will never become obsolete. JWST has gone up. So Hubble Space Telescope has been working in space since 1990 and has produced amazing results. But it's only one telescope, and it's a small telescope in space. It's given us things that we don't see from the Earth, like ultraviolet images and also high-resolution images. But astronomy is far more than that. There has to be a lot of ground-based telescopes to do all kinds of discoveries. There's so much to discover in the universe. One telescope can't make that kind of a difference. What JWST is doing, it's a much bigger telescope than Hubble Space Telescope, but it observes in the infrared. Hubble works in the ultraviolet, observing infrared, because going above the Earth's atmosphere and going to a very far location like the second Lagrangian point, it can look at the infrared universe. That we can't do from the Earth, because the Earth's atmosphere causes a lot of complications in the near infrared. And so JWST can give us a near infrared view. So you can say that JWST will do a lot of work in the near infrared that will give us new information, but that doesn't put any other telescope out of business. We've been doing JHK photometry in the near infrared from the Earth for a long time. JWST will do for near infrared science what Hubble did for optical science: high resolution images, deep images, planets, etc. But what about the rest of astronomy? If ground-based astronomy is killed, it will be killed by Elon Musk, because of this amazing number of satellites going up. Soon you will have banners in space and half the sky will be covered by these things, right? And so the activity of space tourism and unnecessary space vandalism is what is going to affect ground-based astronomy. And this is my personal view. And I'd like to know what you two think, Surud and Anu.
So we also work on some of these big telescopes which are built on the ground. These 8-meter class telescopes and 10-meter class telescopes. And then of course the 30-meter telescope that will come up hopefully in Hawaii, right? So like each of these things have their own niche, right? And of course we cannot send everything to space, because if you want to send something to space, it takes some time to develop. And by the time your telescopes get ready and gets launched, the technology also improves, right? So if you are on the ground, you can immediately use that new technology compared to trying to send it to space. Yeah. Repair missions are difficult. There are many, many complexities when it comes to space missions, right? So of course you would like to go to space, but there are lots of advantages that you want to make use of when you are on the ground, and you can do it, right? Also the size of the mirrors that you can put on these telescopes, right? You cannot put a really big mirror in space. That is very hard. And if you want to see very faint things, then it is better to have a bigger mirror than having to send it all the way to space. Right?
Yeah, and I just would like to maybe quickly talk about the other half of the question, since we have only a couple of minutes left. So about how amateur astronomers or just general public, how they can participate. I think one great way would be to participate in citizen science projects if these are going to be conducted. Maybe they are planned with the JWST surveys, or this is planned with any future surveys. You know, there are going to be many citizen science projects. So these are definitely one great opportunity for people to participate in, contribute to science, discovering new planets. These kind of things have been done, and you know, there is a great opportunity for everyone there. So
indeed, I mean, Kepler telescope, it was launched and many astronomers had already combed through the data, but still citizen scientists managed to find new exoplanets in them. So please keep an eye. So with this, we come at the top of the hour. And so we would like to thank our distinguished panel for being here. I know it has been, it must be quite tiring for JVN to join us. Every year he does this. And we are very happy to have him, and we are very thankful.
Thank you so much.
Thanks a lot, Shomak, for also being here and to answer these questions. These are things that many, many students look forward to. When I was young, I was also looking forward to these sessions. So thanks a lot, and we'll see you. The rest of the program will continue for the National Science Day. And remember that there will also be a talk at 6 p.m. By a JWST instrument scientist, Swara Ravindranath. So she will tell you about the James Webb Space Telescope directly from Baltimore. She is also involved in commissioning this telescope. So you will hear many, many new things about it. Thank you.
Thanks very much. Thank you.
Bye-bye.
Bye.
thrilled to see our idols, our great scientists, and be able to talk to them one-on-one. Just give us your feedback in the YouTube chat. We'll be looking forward to any kind of suggestions, and also to more questions if you have. Just put them there. We'll try to get them answered for you. All right. So we are coming to the next event, and of course we have so many of them lined up for you here. So please stick around for the rest of the journey. Our schedules are there, and our website has been linked in the description below. You can also take a virtual tour of IUCAA through even your smartphones. You just click on them and move them around in the virtual world, and you can go around IUCAA. You can find information about various highlights, showcases, and also see the posters, the research highlights, which we have put up at various places of the virtual IUCAA campus, something like a treasure hunt. So do that, and it will be available. It will be online for a we won't be closing it just today or tomorrow. So just find your own time through anytime this week, and come in and visit us online in the virtual mode. So now at 3 we have Professor Ram Prakash coming to us with a talk, which has a very unique title, a title that raises curiosity. So let's welcome Professor Ram Prakash on stage, and let us hear about whether we can see the ends of our universe. Welcome, Professor. The stage is yours.
Thank you, Samir, for this latest edition of the Science Day, which seems to be going pretty well, as far as I can see. And I'm happy to be here again, talking to a much wider audience than one usually gets to speak to. So this is a tremendous occasion, which I try never to miss year after year. Okay, so let me share my screen and start my presentation. Is my screen visible?
Yes, please. We'll make it full.
And I'm making it full screen and choosing a better pointer. So is everything good?
Thank you. All the best.
Okay, great. Thank you. Thank you very much. So as Samir mentioned, my title today is, can we see the ends of the universe? The universe which we live in, of course. We don't know yet whether there are other universes which we are, there may be other kind of intelligence available or lack of intelligence. But let's focus on our universe for today. And the question is, how big is it? Can we really see the ends of the universe as we can detect it? I'm qualifying that statement by stating again that can we see the ends of the universe as we can detect that? So keep that in mind. Maybe we'll come to that point again towards the end. So to understand that, before we get on to this, to discuss whether we can see the ends of the universe, we also need to first find out how big is the universe and how what are the distances we are talking about, and so on and so forth. So let me build a kind of distance scale in terms of various kinds of units which astronomers use, and then on that basis, how far away various objects are. To start with, many of us have probably heard of this distance unit called one astronomical unit. On Earth, when we measure distances, we measure that in meters or kilometers or miles, so on. But those are too small units to measure astronomical distances. So very often astronomers use this unit called astronomical unit to measure large distances. Now we know that the light travels about 3 into 10 times 8 meters per second. And there are, and it takes about 8 minutes to travel from sun to earth. So 8 times 60 times the velocity of light. Why 8? That is, we know that light takes about 8 minutes to travel from sun to earth. Not exactly 8, but approximately. So this is the speed of light. That is the time light takes to travel in seconds from sun to earth. So that is the total distance traveled by earth, by the light, which is 1 astronomical unit, 1.5 10 to the 11 meters. So it's a very large distance. Sun is at 150 million kilometers. More familiar units, 150 million kilometers away from us. So it's very far away. But in astronomical systems, even this is not a very large distance. This is our backyard, our solar system. So it's not very far. We often talk about light year as a distance unit. And light year is nothing but the distance traveled by light in 1 year. So there are about 3 times 10 to the 7 seconds, 3 followed by 7 zeros, that many seconds in a year times the speed of light. So that turns out to be about 10 to the 16 meters. So you can see that light travels substantially further than 1 astronomical unit or the sun-earth distance. It takes only 8 minutes for light to come from sun to earth, but the distance traveled by light in 1 year is much, much larger. Now, astronomers also use another unit. I will explain how that unit is defined first. So if I take a stick like this and draw 2 lines from the ends of the stick so that they meet at a point here, as shown here. So these 2 sticks, these 2 lines are imaginary lines from the tips of the stick, and this is where your eye is, and you're looking towards the stick. And there is an angle subtended by these 2 lines at your eye. Now, if you move the stick farther away, you can see that this angle becomes smaller. So the same stick, the size of the stick is the same, but it just moved further and further away. This angle becomes smaller and smaller. Now, if I take a stick which is 1 astronomical unit in size, this 1.5 to 10 to the 11 meters, that size stick, and then draw 2 lines and see how far do you have to go so that this angle is 1 arc second. So what is 1 arc second? If you know what is 1 degree, you can divide 1 degree into 60 arc minutes, and each arc minute again can be subdivided into 60 arc seconds. So this is like dividing the time, 1 hour into 16 minutes and 1 minute into 60 seconds and so on. So this arc second is a tiny angle compared to a degree. If you know, if you think of the full moon in the sky, the diameter of the full moon is about half a degree, 30 arc minutes. So you can see 1 degree is already a small angle in the sky. And if you divide that by 60 and then again by 60, this angle is very small. So you have to go very, very, very far to make this angle so small for this stick of size 1 astronomical unit. And that distance is called 1 parsec. And you can show that 1 parsec is about 3¼ times 10 to the 16 light years. Oh, sorry, 10 to the 16 meters, which is about 3¼ times a light. Okay, so 1 parsec is a few times light year. And astronomers very often use a parsec as the unit to measure distances to other objects. So what you should keep in mind is that 1 astronomical unit already is a very large distance, and 1 parsec is considerably more than 2 into 10 to the 5 times more than that. And that is a very, very large distance. Now, if we take this unit, 1 parsec, as our measure for distances, and if you measure the distance to the nearest star to our solar system, it's called Proxima Centauri. It's about 4.2 light years away, about a parsec away. Okay. So typical interstellar distances, distance from one star to the other in our galaxy, the Milky Way, is of the order of a parsec. But if you ask how big is our Milky Way itself, that's about 20,000 times that much, or 20 kiloparsecs. So typical interstellar distance is about a parsec. This Milky Way, our galaxy, is 20 kiloparsec. There are some small galaxies which are orbiting our own galaxy. They're called Magellanic Clouds. They're about 50 kiloparsecs away. The nearest galaxy itself to our own galaxy, called Andromeda, it's about a megaparsec away, a good fraction of a megaparsec away. You can see kiloparsec to megaparsec, so another factor of roughly 1,000. And the size of our visible universe is 4,000 megaparsecs, or another factor of 1,000 more, 4 gigaparsec. So you can see that when we are talking about distances in astronomy, from solar system size to interstellar distances, there's a factor of 1,000, then another factor of 1,000 or more, the size of the galaxy. That intergalactic distances are another factor of 1,000 larger. And if you think of the size of our universe, visible universe, it's about a factor of 1,000 larger. Now, why do we say the size of the visible universe? That is because the way we understand our universe, I'll come back to this later, the way we understand our universe, it took birth about 14 billion years ago in a process called a Big Bang. We call it a Big Bang. That is when the universe originated. So if you calculate the distance light could have traveled during the age of the universe, that is as far as you can see, because the light which started out at the time of, roughly at the time of the origin of the universe, has to travel to us, and the time it were taken over the age of the universe, that is as far as we can see today. We cannot see anything beyond that. This is like a horizon for us. If you go to the seashore, you will see a horizon where the sea seemed to end, or the ocean seemed to end, but really the ocean is not ending there. It's just an apparent horizon. And as far you can see, but that is because of the curvature of the Earth. But in this case, the horizon is because that is as far as the light could have traveled over the age of the universe. And that's as far as you can see. So that is about 4 gigaparsecs, okay, that distance. Now, my question is, can we see objects that far away at the edges of the universe? Which is objects which are 4,000 megaparsecs or 4 gigaparsecs away. Of course, we can see objects which are within the solar system. We can see other stars in our galaxy. We can see other nearby galaxies, other far-off galaxies. So how far can we see? What is the farthest we can see? Can we see the edges of the universe? That's the question. Now, in order to do that, telescopes are the tools which astronomers use. Astronomers make use of telescopes to see far and also see very faint objects in the sky. So if you look through a telescope and you ask somebody, what does a telescope do for you? You will say, yeah, when you look through a telescope, objects appear to come closer. But we have just learned that the objects are almost infinitely far away. So what do we mean by bringing objects closer? Now, that means two aspects. An object comes closer, you can collect more light from that object. And if that object comes closer, you'll start seeing more details. So objects become brighter and you're able to see fine features in that object. Now, if you analyze how a telescope works, for any telescope, it is the diameter of the telescope which defines how much brighter an object becomes. And it's what is called the focal length of the telescope, which defines how fine details you can see. So the focal length is shorter, you will see less detail. If the focal length is longer, your telescope will be able to resolve finer and finer details of those distant objects. Similarly, a larger diameter will collect more light from a distant star. To put this into scale, Galileo, about 400 years ago, was the first one to use a telescope, at least a recorded use of telescope, to study the sky. And he discovered many things, but his telescope had a diameter of about less than 2 inches. The modern telescopes, the largest visible light telescope, the optical visible radiation telescope, called the Keck telescopes, have a diameter of 10 meters. Compared to Galilean telescope, this is very large. Similarly, Galileo's telescope had less than half a meter focal length. The modern telescope, the largest telescope again, the Keck telescope, has 150 meters of focal length. So you can see that from Galilean times, when telescopes were first used for astronomy, we have come a long way forward. Our tools, the telescopes, have become much more powerful in both aspects, our ability to see faint objects and the ability to see objects in fine detail. In both aspects, we have come a long way forward. Now, here is a animated illustration on how a telescope make an object brighter and how a telescope allow us to see finer details. So you think of the star, which is radiating light in all directions. So a set of light rays, which started off from the star at the same time, would have reached a distance, a given distance away from the star after a given time. And as you propagate forward and forward, this sphere of expanding light would move further and further away from the star. But we know that these distances are enormous. Even for a star in the sky, the light has to travel very, very large distance, as we discussed in one of the previous slides, before it reaches us. So what happens is, by the time the light reaches us on Earth, the rays of the light, which in here seem to diverge away from each other, would appear parallel to each other. Why? Because this sphere, because of its infinite radius, almost become a plane surface. So these rays are becoming parallel apparently rather than diverging radially. So when I put a telescope here, this telescope is collecting light from that much area, the diameter given by the diameter of the telescope, that much area of this expanding wavefront from the star, expanding light sphere from the star. If I have a bigger telescope, I collect more light. A smaller telescope will collect less light from that star, and therefore the stars tend to appear brighter or fainter depending on the diameter of the light collecting aperture of the telescope. Now, on the other hand, how does the telescope allow you to see fine details? To understand that, I put a second star here. Now, if the telescope is able to see the light coming from these two objects separately, you will see two stars here looking through the telescope. But if the light coming from both of these stars appear indistinguishable, not separated, then the telescope will only see one blob of light. It won't know, we won't know looking through that telescope that there are two stars here. We'll only see kind of one blob of light in the sky rather than two independent stars. Now, if I do the same exercise and draw these spheres and see how the light arrives from the second star, the red star on the telescope, you can see that this also, although the light ray starts radially diverging from the red star, by the time the star travels these immense distances, they become parallel here, except that the wavefront from the red star is centered on this
point, while the wavefront from the green star was centered on this star, and therefore the rays are arriving at a tiny different angle with respect to the first star's rays. So if the telescope is able to measure this angular difference, it will see these two stars as two separate stars. But if the telescope is not able to measure this angular distance, and if it sees as all the rays apparently coming from the same direction, you will not see two stars there looking through the telescope. It will appear to be one point of one source of light in the sky. So the ability of the telescope to distinguish between the angle of arrival of these rays from these two objects is given by the focal length of the telescope. So the longer the focal length of the telescope, the smaller the angle the telescope is able to separate out, and therefore allowing us to see objects, these two objects as two separate objects. So that is why astronomers build very large telescopes to study objects in the sky. So in this slide, I've shown the top of a mountain called Mauna Kea in Hawaii. It's at a height of about 4,200 meters above sea level, almost half the height of Everest. And you can see that some of the largest observatories in the world. I mentioned the Keck telescope. There are two of them. They are on Hawaii, this mountain in Hawaii, these two Keck telescopes. This is the 8-meter diameter Subaru telescope. This is again an 8-meter diameter Gemini telescope, and so on and so forth. So among the biggest telescopes in the world, many of them are on top of this mountain called Mauna Kea in Hawaii at a very high altitude above the sea level. And so astronomers make a lot of effort to identify such good sites to establish these observatories and build these very, very large observatory facilities so that they are able to peer deeper into the sky and try to detect those objects at the very ends of the universe. Now, this is just a zoomed up view of the Keck telescope. You can see the primary mirror of the telescope. This is 8 meters in diameter. And I said there are two such telescopes sitting next to each other. And this is as high as a 10-story building. So it's a big structure built on a mountain, which is approximately close to half the height of Mount Everest above sea level. There's another telescope called the Palomar 5-meter telescope. So the primary mirror of this telescope is here. It's 5 meters in diameter. There's another telescope, William Herschel telescope, being constructed here. Its primary mirror is 4.2 meters, and this is the telescope once it is built and made operational. This image shows another mountain in the Chilean Andes, about 2,000 meters above sea level, and you can see 4 8-meter diameter telescopes. Each of these telescopes are 8 meters in diameter, and there are 4 of them. They are called very large telescopes. And you can see the mountain is so high that most of the clouds are below the mountain. So you get a clear view of the sky from such locations. That's one of the criteria which astronomers use to establish these observatories. They go to very high mountains so that most of the time the cloud layer could be below the mountain top. And then you can see the skies clearly. So this is just a slide showing some of the largest telescopes around the world. This row is about 4-meter diameter telescopes. These are 8 meters, these are 10 meters, etc., etc. And the blue ones are in the northern, at locations in the northern hemisphere. And these yellow-orange ones are locations on Earth in the southern hemisphere. So you can see a large number of very large facilities have been built over the past several decades by astronomers looking further and deeper into the sky. Now, astronomy is on the verge of the next big jump. Astronomers are building the next generation of astronomical facilities. So here are some slides which show what these new facilities are. One of them is called the Giant Magellan Telescope. It is an overall diameter of about 25 meters, 24.5. But you cannot make a telescope with a single mirror, which is 25 meters in diameter. So this telescope is made of 7 8-meter diameter mirrors. So each of them is 8 meters diameter. You arrange 7 of them to form an aperture, which is roughly 24 meters, 25 meters in diameter. There is also the 30-meter telescope, which are made of a slightly different configuration. They are made of this, the primary mirror of this telescope is made of a large number, about 500 hexagonal segments, which are packed together to form a single surface. Okay? So about 500 hexagonal units form the primary mirror of the telescope. Each of those hexagonal segments are only about 1.4 to 1.5 meters in size. And you need about 500 of them to create a 30-meter diameter mirror. This is an image of the European Extremely Large Telescope, which has a primary mirror of 39 meters. So it is again made of hexagonal segments, roughly 1.4, 1.5 meters in size, packed together, 1,000 of them, about 1,000 of such mirrors packed together to form a single surface. Now, if I look at, go back to this slide, I said that this row corresponds to about 10 meters in diameter. So if I put a 10-meter scaled circle here, the European Extremely Large Telescope is going to be this big in collecting area. It is going to be able to collect that much more light that compared to the existing telescope. So which means how far you can see into the edges of the universe and how faint objects you can detect at the edges of the universe are going to be tremendously increased, tremendously improved when these facilities become online and become operational. So I mentioned 30-meter telescope. I say a few more words about that in the next few slides, basically because India is part of an international consortium which is building this 30-meter telescope. You can see the primary mirror of the telescope again in this graphic. It's 30 meters in diameter, size of a small field, playground. So light comes from the top here. This mirror focuses the light onto this secondary mirror here. And then from the secondary mirror, light comes to the tertiary mirror here. And the tertiary mirror itself can then direct light into some of these instruments which are mounted on these platforms on two sides. And it is these instruments that analyze that light coming from the celestial object in various ways and allow us to study the properties of those objects, those celestial objects, understand more about their physical, chemical, biological conditions, and understand how they take birth, how they live, how they evolve, how they die, and so on and so forth for all these celestial objects out there. So these are crucial parts of the telescope. The telescope itself is a light collecting bucket. It collects that much light from those faint objects, bring that light into these instruments, which then further analyze that light to give us better insights into the properties of those objects which emit that light. Now is a view which shows how this consortium is going to build the telescope together. The consortium is made of institutions in Canada, China, India, Japan, and the USA. And these institutions share building parts of this observatory. For example, most of India's contribution is focused on the primary mirror of the telescope and keeping them together as a single surface. And also some of the science instruments, the telescope control software, etc., etc. And similarly, these other partners would be making other elements of the telescope. All put together, we will build this observatory over the next 10, 12 years in one of the two locations, either in Hawaii or in an island called La Palma off the coast of Spain in the Atlantic Ocean. So the Indian contribution is, as I mentioned, is mainly focused on the primary mirror of the telescope. So India would be making a fraction of the mirrors themselves. We are also making some of the sensors, which senses any tiny misalignments between these segments. As I said, about 500 of these segments have to be formed into a single surface of 30 meters in diameter. And the misalignments between these individual segments of the mirror has to be controlled to 20 nanometers. 20 nanometers is a tiny, tiny size. For example, the thickness of your hair could be about 100 nanometers, 100 microns. So one micron is 1/100th of the thickness of your hair, and then 1,000th of that is 1 nanometer. So 20 nanometers is a very, very tiny deviation in the alignment of these segments. And that has to be detected using these sensors and corrected using these actuators. And the entire correction and support system has to work in a controlled loop, continuously measuring any misalignments and continuously correcting for it in a way that it does not affect the shape of this mirror or the alignment with respect to each other. It's a very, very challenging problem. So almost everything that contributes to that system of the primary mirror is being built in India. We are also making a few of those segments out of the 500 segments. Some of them would be made in the US, some would be in India, some would be in China, and the remaining in Japan. So, as I said, we are building these enormous facilities together with astronomers around the world. The question is, what are we going to detect? What are we going to try to understand with these facilities? And how good is this instrument? In order to understand that, let us look at this graphic here. It shows the way we understand our universe today. In this graphic, we are sitting in the middle of this sphere. Okay? We are at the middle. And that distance to the edge is that horizon, which I talked about, which is the edges of the universe. So within that horizon, within the horizon of the universe, which we can detect light from using these big facilities, we understand that the galaxies in the universe, assemble them into clusters of galaxies, and these clusters then assemble them into superclusters and even bigger structures, and so on and so forth, and they get aligned into these filamentary structures. So the galaxies are not just randomly uniformly distributed. They are uniformly distributed, but not completely random, homogeneously filling this universe. They have these structures which are filamentary in nature. They align along these filamentary structures with big gaps in between where there are no galaxies, no sources of light, big voids, emptiness, total emptiness. So you can imagine these distances are 4,000 megaparsec or 4 gigaparsec. And we said the size of the galaxy is a few kiloparsecs, tens of kiloparsecs. So each of these tiny dots here may be a set of many galaxies. Take one dot there, it may be a set of many galaxies forming a cluster, and then they form a supercluster, and those superclusters form bigger structures, and they all align themselves into these filamentary structures. That is how the visible universe looks like today, as we understand. This is what we think our universe looks like. However, all that material which I showed here, which are visible to either through visible radiation, radio, or if you probe the universe with X-rays, radio waves, any radiation you can think of, anything which is electromagnetically producing emissions, that constitutes only about 4% of the total known material in the universe. 22% of the matter in the universe is unknown. We don't know what it is made of. That's called dark matter. 74% of what constitutes the universe is what we call the dark energy. We call it dark energy or dark matter because we don't know what it is made of. So that entire structure, which we showed in the previous slide, is just a tiny part of the entire constitution of the universe as we understand today. So from Galilean times, we come a long, long way with our abilities to see objects in the universe, and we can proudly claim that we can see to the very edges of the visible universe, objects out there, galaxies out there, with our powerful telescopes. But we still do not know what constitutes about 96% of this universe, as we understand today. So there are a lot of open questions to be addressed. And these facilities we are going to build, like the ones which I mentioned, including the 30-meter telescope where India is participating, is going to address these questions and try to find some answers to those questions. And the next generation of astronomers who would be utilizing these facilities would be living in a golden era of astronomy, trying to understand and try to find answers to questions which we can only imagine today and probably not even imagine today, unimaginable questions and the answers to them. Thank you very much. So to that bright future of those questions which you can imagine and which you cannot even imagine, let me dedicate this talk to all of you who would be making those discoveries in the next coming decades. Thank you for your attention.
Thank you, sir. Thank you so much. I'm sure, and I can read the comments in the YouTube section that they're really loving the talk. And thank you so much. So let's move on to the next talk. We have another professor from IUCAA with us here today, Shubhdeep Dey, sir. Sir, can we have you on stage?
I can hear you. Hello,
Yes.
Sivani, can you hear me?
Yes, sir, we can hear you.
Yeah. So
Can you just, you directly switched your slides on. That's fine. I was just going to say that the talk will be on quantum sensing using atomic clocks.
Yeah.
The stage is all yours, sir. Thank you.
Okay, yeah, thank you, Sivani, for your kind introduction, and thanks to all the viewers who are attending right now, or maybe who plans to see later on in the YouTube channel. So thank you for watching IUCAA Science Day program, not only my talk, but the entire program. So I'm planning to talk about this quantum sensing using atomic clocks, which is a bit different than probably what you have been hearing like in astronomy and all these things. It's directly not an astronomy, but it's very, very closely related to, let's say, present as well as particularly future astronomy. So the astronomy depends on observations. One of them, the observation instrument is obviously telescope. You just heard the talk by Professor Ramprakash. But then the future is actually quantum enhanced sensors. So sensors which will be depends on quantum mechanics principles and etc. And those sensors can sense a tiny bit of fluctuations or change of anything, and they will be much more sensitive to detect, let's say, dark matter, even dark energy, or small gravitational waves, and so on, so on. And those sensors should not only be placed on the Earth, but also on space stations in different planets, probably in the future. And they will be all connected in a network, and that would enhance the present capability or observation capability of the astronomy and obviously do a good science. But that's not the only purpose of these quantum sensors. This has many different other applications. I just took this example because we are in an astronomy institute. So let me begin, and in the beginning, let me just talk to the physics. Let me just explain. I mean, we know these all, but still, there are probably school students. So basically, the physics is the way we explain some physical phenomena, and for that, we take the help of different theories. One, the very common one is basically classical physics. There, we can explain bulk property of the materials, electricity magnetisms, like velocity of something, friction, all fluid mechanics, all these kind of things. But there are certain things which actually we cannot explain by normal classical mechanics. And to start with, even the structure of an atom, the right structure of an atom cannot be explained only by classical mechanics. There we need something else, and that's called quantum mechanics. In simple classical mechanics, actually, the electron will just fall on the nucleus. But when we take the help of quantum mechanics, then each of the electrons have the right orbits and they are orbiting in that particular orbit and they are quantized. Similarly, let's say diffraction or interference. There are several examples which cannot be explained by normal classical mechanics, and there we have to take the help of quantum mechanics. And also the quantum mechanics is not complete by itself. There are certain things which cannot be even explained by quantum mechanics. For example, the gravity. The gravity cannot be explained, gravitational force cannot be explained by quantum mechanics. Also, the existence of dark matter, dark energy, there are several open questions which even cannot be explained by quantum mechanics. So the quantum mechanics is also not a complete theory by itself which can explain everything. And for that completeness, we actually need further observations, and astronomy is actually one of the way to find out these questions. And for that, we need very precise, accurate sensors, and quantum enhanced sensors can actually play a very big role in the future to find out the details of these open questions and to make it a complete theory which can explain basically everything what we see around us. So in a simple word, what is the difference between classical mechanics and quantum mechanics? Just a simple way to understand. This is not obviously not the entirely correct definition. In a quantum mechanics, everything is quantized. So everything are discrete, and the size of this discreteness is very, 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 very tiny. For example, even if we talk about light, it's not a continuous light. It's actually photons, and these are like wave packets, and they are discrete photons which are coming, and that's so small that by our bare eyes we cannot distinguish them, but actually they are individual photons which are coming. And since they are so tiny and they can be distinguished, that actually helps us to measure very small changes or with a very high resolution, because you can just distinguish two different photons. So that means you can distinguish two different energies which are just slightly bit, a tiny bit different, which you cannot do it by classical mechanics. But since quantum mechanics allows you to discretize these things, photons, you can actually measure a very tiny bit of difference. And that actually helps you to build a sensor which are extremely sensitive. And then there are different other quantum phenomena. Photon was just an example, and I'm coming to that. So that's the beauty, that why quantum mechanics is important. So let me just take an example. The picture what you see here, this is a photograph of IUCAA's observatory, IGO, Giravali Observatory, and there is a nice road which is almost 360 degree and goes, the last turn actually, it takes 360 degree turn and goes to the observatory site. Now let's say you have been asked to measure the difference of height between point A and point B. How would you do that? Well, I would probably, if I have to do it, I would probably do it in this way. I would take a laser pointer or something similar to like that. I will point this laser towards from point A to point B, and then change its angle and make it vertical. Let's say I have some instrument to put it really vertically. I have some ruler to put it really vertical. Then I will measure this angle theta. And I will take another ruler from placing at point A, and maybe I will have a friend at point B, and then I will measure this distance d. This is also simple to measure. And once I know this distance d and this angle theta, then just using trigonometric formula, I can find out what is the height, right? It's simple. No, it can be quite accurate. But let's say now I asked you to measure the height of Mount Everest. Well, first of all, that place is not easy to do this kind of measurement, but still in 1954, Radhanath Sikdar, he was a young mathematician at that time, I think 19 years old or so. He actually used trigonometry to measure the height of Mount Everest, and he was very accurate to measure the height of the Mount Everest. What he did, he could not do exactly the same thing what I explained in my previous slide, but he did very similar to that, use the trigonometry. He was placing a pointer here and measuring this angle A. Then he moved his pointer by a distance d and again measured this angle B. And then by just simple trigonometry, this h is equals to d by cot A minus cot B. And since he measured this A and B angles, he could actually measure the height of the Mount Everest h. And he came up with a value 8,848 meter. At that time, China measured it 8,844.43 meter, which is something like 4 meter different than what Radhanath Sikdar was measuring. And there was a controversy who is correct. Recently, just few years back, China and Nepal made a joint venture to measure the height of the Mount Everest, and both of them measured 8,848.86 meter. So which is just 86 centimeter different than what Radhanath Sikdar measured in 1954, just by some simple ruler and instrument, something like that. So he was so accurately measuring that thing. But now let's say that's fine, you can measure the height of the Mount Everest, but let's say now I asked you to measure the change of height of the Mount Everest. Typically, Mount Everest is changing its height 5 millimeter per year. Now that is a difficult thing. You cannot do it by simple instrument, because measuring something, I mean, see this height is measured with an accuracy of centimeter, and 5 millimeter is much smaller than a centimeter. So how can you do that? Also, once I asked you to measure something with an accuracy of 5 millimeter over a height of, let's say, a few 9 kilometers and etc., you need to know what is actually the reference sea level, because your measurement is based on actual measurement of the sea level. Then you need a more accurate techniques to measure that. Just simple classical instrument won't allow you to do that. And obviously you need the calibration, proper calibration of your instrument. That is much more easier. So to measure the reference sea level, that is also a question. So you need a very accurate way to measure the base sea level. That is also changing in time to time due to tide, even like regular tide and low tide and high tide. This sea level is actually changing. There is an average value. So you need to know that very accurately. So for all this kind of measurement, that was just an example, a quantum enhanced technology which can measure very tiny bit of things will be helpful. And over last 120 years since the beginning of the quantum mechanics, now we are in an era where we are actually using quantum phenomena to make devices. See, 120 years back, Max Planck, it started with Max Planck, and the actual name of quantum mechanics was given by Max Born, or maybe I'm other way around. So then there are a lot of quantum hypotheses, like quantization of the photons. As you see, like photons are not continuous thing, they are wave packets. And then uncertainty principles, we know about that. Then particle, rather than particle nature of a particle, wave nature, so wave particle duality. So any particle actually have a wave nature, wave particle duality. That is one of the main important thing about the quantum mechanics. Since that era, then we observe different quantum phenomena like atomic structure, interference, spin of an electron, like boson, Bose condensations, regenerate Fermi gas, and there are several. And then we observed some quantum phenomena, which nowadays we are actually using to build a device. Now the quantum enhanced devices, few of them are already available. For example, quantum computer, quantum communications, atom interferometry, quantum clocks, and so on, so on. And today I am going to little bit talk about the atomic clock. I won't be able to talk all these things in my today's lecture. So to realize all these quantum sensors, there are different platforms people use. For example, ultra cold atoms and ions, where the atoms or ions are very close to 0 degree Kelvin temperature, is one of the platform. Then nanowires, ion crystal, superconducting qubits, quantum dots using nitrogen vacancy centers, and so on. These are all different platforms which are used to build the quantum enhanced technologies or instruments. You can see here, like NIST in USA, they have actually made very tiny chips. This is just a centimeter size, or actually it can come on tip of your finger, which can measure temperature, current, voltage, time, and length very, very accurately. Just a tiny bit of chip of everything. This is a quantum enhanced sensor. Quantum computers are also sort of coming slowly. It's a emerging technology, but it has been demonstrated quite well, and also a few of them are available, but it's not a computer which can come on your desktop at this moment. It will not replace your desktop computer in next few years, but maybe eventually in 10 years time scale or 20-year time scale, that would be the case. So keeping all these things in mind, India, together with many other countries also, they are coming up with quantum missions. And India has also launched quantum missions, or actually announced in 2020, and soon it will be launched. And there are 4 different verticals where India wants to realize quantum mechanics in actual applications. And one of them is quantum sensors and metrology, because that is very important. If country need to grow, for example, you want to put a clock on your satellite, you have to put the best clock that you can do, and that can be only done by quantum mechanics. Similarly, if you want to measure change of the gravity, you can only use the quantum sensitive instruments to do that. You cannot do it by just a classical instrument. Similarly, earthquake, and so on, so on. So in next few slides, I'll talk about the clocks. Clocks, I don't probably need to explain it very well. It has an pendulum and it has a counter. So the pendulum oscillates and the counter counts. So if you want to measure a very accurate ultra stable clocks, you need to have a very stable oscillator, and you need to have a very good counter to count these oscillations. So clock is actually very old. Even if we think about our Indian history, since the time of Indus Valley civilization 5,000 years ago, at that time there was also clock that is called water clock. But since then until now, the accuracy of the clocks has improved by several orders of magnitude. So at that time, probably the accuracy of the clock was something like 10-15 minutes. And today, the accuracy of the best clock is like, if I put if the number is 10 to the power minus 19 to 10 to the power minus 20, but that essentially means the clock is accurate to 1 second over the age of the universe, and even actually longer. So that's the basically sort of history of clocks. And why the like atomic clocks are much better, because the oscillation frequencies are very large. It's not the pendulum is oscillating once in a second, but pendulum is oscillating 10 to the power 15 times in a second. So if you miss only one count, you are actually missing a very tiny fraction of a second. That is sort of quantization. Yeah, it's a most stable oscillator. The atom is an atom. You take it here or you take it to any other places, even in space, the atom properties doesn't change. There are a little bit of perturbations. Those things can be also identified and measured very accurately. So that can be like taken into account in the actual clock operation. And also there are very sophisticated techniques to cool the atom to nearly 0 degree Kelvin that reduces many of the systematic effects, like the tiny perturbations which can happen due to electric field, magnetic field, or Doppler shift, etc. Those are reduced to nearly null. So a very accurate clock can be produced using the properties of an atom. That's why atomic clocks are so great. Now coming back to my earlier the actual example, like if you have to measure the height of a Mount Everest. So actually, if you place a clock, let's say at the bottom of the Mount Everest and one clock at the top of the Mount Everest, these clock ticking rates are different. And the clocks are so accurate that they can actually distinguish that. As you go higher and higher from the Earth's surface, your ticking rates are much faster and faster. So that means if you have a twin, let's say brother or sister, then let's say one person is sitting at the bottom of the mountain and other person is on the top of the mountain. The person who is on top of the mountain, he or she will age much faster compared to the other boy or girl. And I'm not going into the mathematical detail of that. So basically, let's say coming to here, so the best microwave cesium clocks can measure a height difference of 100 centimeter, which is not that good. Like as I took the example, like we want to do sub centimeter or millimeter scale, but the present optical clock, they can actually measure a height difference of millimeter, even lower than a millimeter. So now let's say you have, this is the picture of the Mount Everest. If you have two such clocks, optical clocks, one is at the bottom of the Mount Everest and one on the top of the Mount Everest, and then you can easily measure that what is the tiny bit of change of height of the Mount Everest in every year. And that is actually just, it will happen in very soon. So here I am showing a compact picture of the optical clock, which is being developed by European Unions called OptiClock, and they are putting everything in just a small box basically, and that would be probably available in couple of years, which is little bit delayed because of the COVID and etc. And then one can actually put one such clock at the bottom of the mountain and one such clock somehow lifted to the top of the mountain, and it will actually measure this millimeter difference. And that's very important because that is connected to several geological things, even probably like when India will be flooded or not, and etc., or any countries, those things are very important. So measuring the height of this any place, not only Mount Everest and etc., this is called geodesy, geodetic measurements. These are very important for our future basically. And optical clock shall play a very bigger role to do that. And this was only one example. There are several others. I will not be able to go through all of them. In our daily life, actually, we use very precise clocks in navigation, communication, surveillance, and so on, so on. And similarly, for fundamental science, like let's say searching dark matter, even detecting gravitational waves, like detecting cosmic microwave background, and so on, so on, they rely on very accurate clocks. So basically, what I wanted to, the take-home message is, an very accurate clock has an applications to improve quality of our daily life, to explore fundamental science. In all these things can be done when you have a very, very good clock. And actually, many of them we are using without knowing that we are actually using the using very accurate clocks in our daily lives. So this clock in last, let's say 75 years, the improvement of the clock, particularly the atomic clock, was enormous, starting from 1945 by Rabi. That was during the time of Second World War. He came up with the idea that atoms can be actually used as a clock, and then his students Ramsay actually found out the spectroscopic techniques that can be used to find out frequency of an atomic transition very, very accurately, called Rabi's spectroscopy. And then many things has happened. I am not going through all of them. And now we are in an era where we have the atomic clock, which can actually measure a small change of gravitational field or Newtonian field, or even further in the future, like gravitational waves or cosmic microwave backgrounds, and so on, so on. So far, there are 12 Nobel Prize which have been awarded in different technical things related to physics, which atomic clock community uses in their techniques. For example, it started with Rabi. Rabi first proposed the atomic clock idea. Then Ramsay, he developed the spectroscopic techniques. Then Demelt and Wolfgang Paul, they developed the ion trapping techniques, which actually is used to produce trapped ion clock, and that's what we are going to do here at IUCAA also. Then Bill Phillips, Cohen Tanuji and Steve Chu developed the laser cooling techniques, which cools the ions or atoms to nearly 0° Kelvin temperature. And then for the atomic reference measurement called frequency comb, that was developed by Wineland, Hans, and John Hall. And Ted Hunch, John Hall, and Glauber. And in 2012, Wineland was awarded Nobel Prize for quantum, basically trapped ion systems, to use it for the quantum sensitive measurement, which at present is also used to build the best trapped ion clocks and so on. So just last slide, in the precision quantum measurement lab at IUCAA, we are building one such atomic clock that will be based on trapped ytterbium ions. And if you want to know more about that, you can visit this virtual link, and there will be more videos which can explain those things further. Thank you.
Thank you, Dr. Shubhadeep. What a lovely talk, a novel topic, which is sometimes it seems it's not related to astronomy, but it's so much of physics there. And thanks for making it so lucid. Everybody should visit this, the PQM lab here through the IUCAA virtual tour. The link to the walkthrough of IUCAA, the virtual walkthrough of IUCAA, is in the description below in this video. So please make sure you go there. We'll just take a few minutes for a question which has come up from the audience. So let's take the simpler question, maybe, which relates to astronomy. So the question is that let me bring it here. Right. So is it possible to use quantum mechanics for communication, and especially maybe intergalactic communication?
Yeah, actually, that would be probably the future. See, first of all, yes, the quantum mechanics is already in use for communication, called quantum communication, where entanglement of the photons are being used. And that has been extended up to an intercontinental distance. Let's say from India to Canada, there is a plan to do the quantum communication, and which is done by satellites. It can be also done between two different planets or even further away. The only problem is sending a light photons from one planet to the other planet, because it will be the intensity of the light will go very down and down and down. So once that problem is solved, then yes, the quantum communications can be actually used for like very long distance communication. I mean, yeah. So that's a more technical problem.
Great. So I think that the other questions are getting more complicated. So this would be the best way to end this session, which was very novel, and you presented something very very modern and cutting edge, but in a very simple way. Thank you for that, and being part of this lovely program on National Science Day.
Okay.
So after thanking Shubhadeep again, we'll move on to our next event, which has two more researchers from IUCAA, Professor Deepankar Bhattacharya and Professor Neeraj Gupta, coming in, and they will be having a different interaction. So this is not going to be a regular talk, but of course it will focus on some aspect of astronomy. In fact, a very important aspect of astronomy, of which India is proudly a part of. So the stage is yours, professors. Please take it away.
Thank you, Samir, for arranging this. And I will request Neeraj to make some remarks, and then we can start.
Yeah, I think Deepankar, we also would like to show some slides in case.
So shall I start on the slides already?
Yeah.
Okay.
Yeah, we can start the slides as well while we talk through. I think one of the things we thought we would like to start with is that everything around us actually emit radio waves, right? And when we talk about radio waves, they are physically nothing different from the radiation like optical light that we are more familiar with. They follow the same principles that are encapsulated in Maxwell's equations like almost 200 years ago or so. So let's first talk about what is it special about radio waves in our lives and in astronomy in general. Like why is it that we should be interested in looking at universe in radio waves, especially at a wavelength which we cannot see with our eyes? Can it be fun? Or it's going to be dull? I think let's talk about that.
Yeah, so the electromagnetic wave comes in various wavelengths, right? So wavelengths could be short, very, very short, then you get gamma rays. Intermediate, you get X-rays, then you get optical, which is our eyes are sensitive to optical. And then it can get longer and longer, and at some point you reach radio. And we use radio waves, as Neeraj said, today for all types of communication. So these are waves which are generated by mankind, and we use that for communication. But all cosmic objects emit radio waves. And once we started looking at the sky in radio band, one found objects which were never imagined before. So if you look at the distribution of radio intensity in the sky, for example, in our galaxy, we will take two of these panels and compare. This is optical. So you can see that this is the Milky Way, and this dark band is a lot of dust in our galactic plane, which obscures some of the light from the center and surroundings. In radio waves, it looks like this. And clearly, you can see that the dust has no effect here. So you can see through wherever dust was present, and you can see radio emission from many, many different sources, which you would not otherwise have seen in optical. And also different types of sources, which were not even conceived before the advent of radio astronomy, came into view when radio astronomy started. And radio astronomy therefore opened an exciting new chapter because we started learning about different aspects of the universe. So Neeraj, maybe you can quickly introduce the very beginnings of radio astronomy, which was an excitement in itself.
Well, as it often happens in science, the foundations of what is to come in experiments are somewhere all hidden in the theory long ago. In this case also, like there were some very early experiments conducted by Hertz, which demonstrated that like radio waves do exist, like EM waves at radio wavelengths exist, I mean to say. But the discovery or the start of radio astronomy, which we would mark as first detection of radio waves from an astronomical source, was very serendipitous. It was actually Jansky. He was an engineer. He was working at Bell Labs, and he was not interested. He has nothing to do with astronomy in this experiment. But on the right-hand side in this view graph, we can see that he built a strange kind of an antenna. And using this, what he was trying to do was to investigate noise that was coming through in transatlantic communication. And in those days, these communications were like very expensive, like they were special, like it cost a lot of money. So it was essential to ensure that it was good. And then he found a certain kind of a periodic signal in his observation, which through very rigorous investigation, he was actually able to pinpoint that it is coming from a region towards the center of our galaxy. So this was the start of radio astronomy as such. Yeah.
Yeah. And then radio astronomy went on to discover some really fantastic objects. For example, quasars, which is an acronym for quasi-stellar radio sources. We know today that they are among the most energetic objects in the universe. There is a very, very large black hole sitting at the center of a galaxy and then chomping up matter from interior and throwing out extremely powerful jets. And those jets are producing this emission. And these were first seen in radio. And later on, were some of them also had optical counterparts, some didn't. And these also, objects of this type are also the largest objects we see in the sky. Some of the galaxies which produce these jets, and the jets move really far, far away, millions of light years away. And you see these objects which are millions of light years in size. They're called radio galaxies. They are really the largest objects that we have ever experienced, and they're seen only in radio wavelengths.
So Deepankar, you are saying that in this top left view graph, the emission that we are seeing in red actually seen only at radio wavelengths. If I take an image of sky at optical wavelengths, I will not even know that such a thing exists there.
Yeah,
that's
exactly.
Fantastic, actually. Yeah,
that's fantastic.
And it's happening in 50s, actually, right? We are talking about like 70 years ago. This is what
70 years
fantastic.
Ago. Indeed.
Yeah.
And then some of the most important tools of understanding the universe was this very specific spectroscopic transition of hydrogen, which was predicted and then was detected in using radio telescopes. This transition, hyperfine transition of hydrogen, occurs at a very fixed frequency, on 1420 megahertz. And it's bang in the radio band. And this has become one of the most important tools of studying the evolution of gas right from the beginning of the universe till today.
And
similarly, Neeraj, go ahead.
Yeah, no, as a student, I found it very inspiring. When I say as a student, it was 20 years ago, because this transition was actually predicted by Hendrik van der Hulst as part of his PhD thesis. And the discovery was made by 3 different groups across the world. So it also brought out a very nice demonstration that how science is done collaboratively and competitively across the world.
Yes, so this is an example of something that was predicted, and then people made an effort, and then they discovered it. A completely different type of situation occurred here in the discovery of cosmic microwave background. So the 2 engineers, Penzias and Wilson, they were looking for noise coming from the sky, just like Carl Jansky was doing in the 30s. So this was in the 60s. So they were, of course, things had become much more sensitive, and they were looking for very low-level noise coming from the sky. And they discovered some excess noise. They had no idea that this was actually predicted theoretically some years ago. And as being the radiation left over from the Big Bang explosion, which gave birth to our universe. And so that discovery was made, as far as they are concerned, serendipitously, but it had already been predicted before. And then when it was realized, this became one of the major discoveries in astronomy, leading to a Nobel Prize in 1978. And something that was totally unexpected. No one had predicted, and the people who discovered it were looking for something completely different. But careful look at the data, really careful look at the data, found there was some periodic signal coming from some part of the sky, and initially it was not sure whether it was sky. And then the graduate student who was working on this, Jocelyn Bell, persevered and really made a critical discovery that it is indeed coming from the sky. And these were pulsars. And all of us know about pulsars. These are extremely exotic objects, neutron stars, whole sun squeezed within 10 kilometer size, very strong magnetic field, very bright radio radiation. Without the radio band, we would not have known the existence of these objects. And of course, it led to the Nobel Prize in 1974. And using these pulsars, gravitational waves were discovered. And that was also awarded a Nobel Prize in 1993.
So each one of these discoveries have actually, many of them have won Nobel also, as mentioned in slides, but they have also become full-fledged fields in their own right today, right? Like we talk about quasars now, millions of quasars known, and people use them for all kinds of, to understand black hole as well, and us to do cosmology and everything.
Right. So maybe we should now talk about the SK itself.
Yes, but before going into SK, I would like to ask you quickly that what is it that we need to do to detect radio waves? Is it really just like we do it optical, we take a lens and take a photograph of the sky? Is it same or is it slightly different here?
Right. So what we detect the radio signal with is a radio receiver, which even your mobile phone has a radio receiver. So this radio receiver has to be put in a place where radio signal is being collected by, let us say, a dish. And so you have dishes like this, which are signal collectors, and then they concentrate the signal at the focus where we put the radio receiver. Now, the bigger the dish, the more signal we can collect and more sensitive the radio telescope is. Another aspect of it is how fine a resolution do we have in the sky. Two very nearby radio objects, if we want to distinguish them, then we need a very fine resolution in the sky. The resolution is actually determined by the distance between the farthest parts of the telescope and also the wavelength. So for a radio wavelength, if you take a typical dish, you have a certain resolution in the sky, which is often not enough for a significant study at the level of sensitivity that we want to go to. So techniques have been devised to put parts of the telescope further and further away, and then combining the signal. And this is the technique of radio interferometry, where you have not one dish, but you have many dishes, and you spread them around over a much larger area, like the GMRT in Kodat, which is 80 kilometers away from here in Pune. And that has 30 dishes spread across many kilometers. And each dish is 30 meters in size. But it is the largest distance between two parts of the telescope. It's the largest distance between two dishes. That's what gives you the significant resolution, which allows us to study objects in detail in the sky. And this technique, particularly once you spread out the dishes and then the Earth rotates, then that rotation can produce a very detailed map of the sky, and it's called aperture synthesis. That also fetched a Nobel Prize to Martin Ryle in 1974.
This is fantastic, because if I was to take even the largest, one of the largest telescopes, let's say GMRT, which has 45-meter dish, and if I aim it at sky, the resolution it will give me close to like half a degree. And with that, like I cannot even see details of even moon or even say near star forming regions in Orion Nebula, which I'm sure a lot of us have seen. So if interferometry was not possible, then we wouldn't really be doing competitive astronomy at radio wavelength. So this is something really important. But now two questions come to mind. One is that, of course, as you said, like we should now talk about what SKA is. So the question is that why do we really need to make bigger and bigger telescopes, and how big is even possible, and what is it new, and what are the new things that we are going to discover with that? Because in previous slides, when we were talking about, it seems that a lot has already been done.
Right. So a lot has already been done, but there is, as we say, that what we have done is only the tip of the iceberg. There is a huge iceberg sitting under the tip that we have detected. And all that can be done only when you go more sensitive. Now, the interesting thing about astronomy is, if you go more sensitive, you can see these objects which are further and further away. The objects which are further and further away are also closer and closer in angle in the sky. So it is not enough to just increase your signal collecting power. You have to also simultaneously increase the resolution, that is the ability to tell two objects apart. So these two together drives the advancement in astronomy. And there is a whole lot of things that we will be able to do If you go more sensitive, so that means actually see objects much further away throughout the entire universe, right from the time the new objects started forming, which are emitting radio waves, to today. So if you want to study the entire history of evolution of the universe, we need to go deeper. And if we need to go deeper, we also need to be sharper in our vision. And these two together has driven the need for the square kilometer array. It is going to be the world's largest radio telescope.
So
square kilometer, yeah, go ahead.
So existing telescopes have like what, 20, 30, 40 kind of dishes. When we are talking about SK and when we say that it's going to be world's largest telescope, what is the kind of scale that we are talking about here? And where will it be built actually? That's the question.
Right. So we are talking about hundreds of dishes and hundreds of elements. And the telescope is going to be divided into two parts, because the idea is to cover a range of wavelengths, all the way from very large wavelengths at frequencies such as 50 megahertz to relatively short radio wavelengths like 14 gigahertz. And one type of collecting element cannot cover this entire range. So it has been decided it will be built into two parts. One covering the low frequencies, 50 to 350 megahertz, which will be built in completely habitation-free regions in Western Australia. The other will be a collection of dishes, which will be built in South Africa, which will go to the higher range of frequencies. So
why are we building this in Australia and South Africa? And Samir, in his introduction, mentioned that India is proudly part of this collaboration. So it seems that the scale of this telescope is so big that it's something which cannot be built by a single country or a single group. We need to all bring in together our resources and collectively build this telescope, which will allow us to do things which have not been done before. But still the question remains that could we have built it in India itself?
Right. So first of all, let's look at the scale. So square kilometer array stands for the total radiation collecting area of 1 square kilometer. So 1 kilometer by 1 kilometer, which will of course be built up by adding all these small elements. But in the first phase, we are not even attempting that. We are attempting 1/10 of a square kilometer, so 0.1 square kilometer area. And the estimated cost of it is about 1.5 billion euros. So clearly, it is very difficult for any single country to put up that kind of resources just for astronomy.
So this is a mega project, as we say.
This is a mega project. And that is why many countries have joined hands. Right now, 8 countries have already signed the treaty to build the SK, and 3 more are in a stage where the process is very far in the high stages of the government, should be finished soon, and India is one of them. India has not yet signed the treaty, but the things have progressed quite far, and hopefully within a few months we'll get the government clearance to sign it. But in the interim, there is a cooperation arrangement that has been signed between India and the SK. So total 8 countries have signed, and 3 countries are like India, where the cooperation arrangement is currently in place. A total of 11 countries, and there are others who are thinking of joining, who have not yet made a commitment. So the cost is going to be divided between them. Secondly, to build the telescope and get the maximum sensitivity out of it also depends on how much interference the telescope receives from man-made things nearby. And the 2 locations that have been chosen in South Africa and in Australia are currently the world's best sites as far as radio interference is concerned. The minimum amount of interference is present. And there is no such place in India, unfortunately, where there is reduced interference. And also India is very close to the geomagnetic equator, which has additional interplanetary interference coming through the solar wind, and so that causes scintillations, which are quite strong at Indian latitudes. So therefore, India would not really be the best place to build this kind of telescope, even if we had all the money. Of course, it is not something that is within India's resources right now to be able to do. But even if we did, we may still look for a place where it is much quieter in terms of interference.
Yes, we have to, when we put in so much effort, we have to get the best out of it. We have to really work collaboratively. And so when all these countries are coming together, they are, of course, bringing their resources. And when we say resources, first thing in the mind comes to land and money. And this slide is nicely showing that what is being attempted in terms of collecting area, which Dipankar, you were talking about. So what this view graph is showing is that collecting area that different telescopes have. So in the bottom, if you look at, we can start with dishes, which are like fixed aperture. They are fixed to the ground, but they are in diameter 300 meter, 500 meter, something like that. So they are so huge, but we cannot steer them, right? It's difficult. They become so heavy. So then we start to move, we want telescopes which can actually point to different locations in the sky. So on the right hand side, there are these various single dish telescopes, which we can look at. They are, as we can realize from the size of the circle, that they are a bit smaller than the fixed apertures that's shown at the bottom. And they are like, there we are talking about dishes which are like 100 meter and so, and then we, for example, in GMRT, which are like 45 meter diameter, that's also a huge collecting area. Square kilometer array, the dish component of it is going to have dishes of the size of about 13.5 meter or maybe 15 meter diameter. That is being decided, but there will be several hundreds of those. So overall collecting area will be huge, and it will be very, very sensitive telescope. So we have talked about these dishes. We are looking at this huge amount of land, which is in away from RFI, where we are going to build this telescope, and also away from ionospheric interference. So all this sounds good, but to make this, what else these countries are bringing in? Like, for example, what I'm thinking is that, let's say I am sitting here in India, these telescopes are being built now in Australia and South Africa. I am an engineer right now, let's say. And so how can I contribute to this? What is India doing in making this
Exactly.
telescope?
I think that is a very pertinent question. So the telescope is going to be located in South Africa and located in Australia. So how do we contribute? Now, this SK observatory, which is like a consortium, which is committed to build this telescope, has also broken down the task of building the telescope into several small pieces of contributions. And depending on the level of commitment each country has made, this task has been distributed across these countries. So every country has got allotted a piece of work, that one or more pieces of work, which they will need to contribute to this telescope. The task that has been given to India, there are several tasks. So let me go through the kind of tasks that India has been tasked with. The major part is the observatory monitor and control system. So this is a software which is going to be at the heart of both the SK telescopes, SK1 low and SK1 mid. It is going to control the telescope. It is going to decide, based on the current situation in the observatory or based on command, what to switch on, what to switch off, what mode to operate in, how to get the data, collect the data, disseminate to the corresponding data paths and so on. And if any particular element is misbehaving, how to handle this, either quarantine it or send a signal to somebody to look at it and repair it. All of that is going to be managed and monitored by this software. And this is going to be a software which is the design of the software was led by India, and the realization of the software is also going to be led by India. But the entire contribution is not from India. So there will be teams from multiple different countries which will contribute to the software itself. But a large part of the contribution will come from India itself. So this is going to be the biggest contribution of India towards square kilometer array. Then there will be some hardware and electronics for the SK1 low that India will contribute, for which fabrication is starting in Bangalore. Then there is some hardware and electronics for the dishes. Also, India will contribute. That's in the cards. And once the data is collected, then the data from the data science has to be produced, for which several data pipelines have been created for different kinds of tasks. So this is called science data processing and handling. One of those pipelines, which relates to search and discovery of pulsars, the software for that is going to be contributed from India. So these are the different aspects in which India is going to be involved. And of course, many other countries are involved in many other ways. Some country will build dishes or some of the dishes. Some country will build the elements. Some countries will contribute largely in cash. So there is various different ways of contributing to the SK observatory. But Indian contribution, as I mentioned, has been assigned to these specific areas. And these are all very major undertakings. And the proposal that has been made to the government for funding this endeavor also has with it a large component for the involvement of students and also early career researchers and engineers to get in and actually do specific tasks which will lead to the delivery of these components that you have to do. And so once the funding is granted, then all the institutions that are involved, there are about 30 odd institutions, about 25 odd institutions involved in India SK consortium right now, and that number is growing. So those institutions will then recruit people, which will be young students, young engineers, to contribute towards this.
So this is an international project in which India is a major partner and not only contributing to build it, but also preparing in all other aspects to use it for science. And I think this view graph brings out very nicely the kind of way SK will improve how we view the universe. There's a comparison of how things or different parts of the sky are visible when we look at with the current facilities, and how the SK will bring about the sharpness and depth in those images. Now, with this kind of a thing, I think it will be a good time to talk about now what kind of science it can do actually, I think, because that's what we are eventually building it for.
Exactly. So, as I said earlier, the desire is to explore the evolution of the universe, right from the time it was born till today. There are several aspects of it. There are several different ways we can do this exploration. We talked about the very important hydrogen emission hydrogen line, the 21 centimeter line, 1400 megahertz line. That probes the distribution of hydrogen wherever it exists. And since the universe is expanding, as you go to larger and larger distances from us, this line appears at lower and lower frequencies or longer and longer wavelengths. So by looking at the distribution of this line emission at various different wavelengths, we can map the distribution of this hydrogen gas all the way from very early universe to today, including many, many galaxies in which this gas is distributed, And it is not only in galaxies, but also around galaxies. And there could even be objects which are mostly gas rich. You don't even see much stars there, but it is basically a blob of gas which has not yet converted itself into stars.
So we are actually going to be able to understand that how gas is actually getting converted into galaxies, not only in the current universe, but actually looking at the first galaxies and first stars as well.
Exactly, exactly. And even before the gas got into galaxies, the diffuse hydrogen. And right now, if you look at today, the medium between galaxies is completely ionized. That's because so much radiation producing objects are present, not only stars, but also more energetic objects, that these ionizing radiation has completely ionized the intergalactic medium. But this was not so earlier. In the very beginning of the universe, things were ionized, and then it cooled, they all became neutral. And it took a long time for the first ionizing astronomical source to start operating. So in between, the gas was neutral. And when the gas went from neutral state to ionization state, marks an era where astronomical sources started appearing. And this is basically like the birth of the bright universe, cosmic dawn. And this can be probed very well using the SK telescope. Neeraj.
So yeah, so I was looking at this. There are these two huge volumes of SK science that have been written by international scientists, and it talks about that SK will actually be also sensitive to detect not just you were talking about neutral hydrogen from galaxies, but also when we have all these galaxies distributed and traveling from distance, how they get modified by the distribution of matter, and the kind of precision measurement that will lead into the field of cosmology and understanding of dark energy, that is quite mind-boggling, like how like sort of a telescope can look at those fine details of the universe. And there's one more thing which I find quite fascinating, that when we talk about radio waves, we are all immediately the physical process that comes to mind is the non-thermal emission, not the thermal. Here we are talking about interaction of electrons in the magnetic field. But we have very little understanding of how magnetic field is observationally distributed in the universe. We all know theoretically that it plays a very, very important role at all scales in the universe and at all stages of the universe. And SK is going to be the telescope which will actually completely change this view of our universe.
Yes, so map of the magnetic field in the universe. This has not yet been possible so far. And this is something that SK will attempt, and that will be very, very exciting. Just the map of the distribution of magnetic field across galaxies, across material between galaxies. And this will be fascinating. And that's something that SK is designed to do, which will be one of the firsts. In addition,
yeah.
So
I was going to ask you, do you think we will be able to find some new friends in the universe with SK also, or we?
Yeah, so see, SK is sensitive enough to detect airport radar in a galaxy far, far away. So many tens of light years away, if there's a galaxy or if there is a star on which there is a planet where there is life and they are operating an airport radar, SK will be able to pick it up. And of course, why only airport radar?
So we are hoping that they produce as much RFI as we do.
Exactly. So the sign of life appears to be, sign of advanced life appears to be filled with radio waves. Right. And we should be able to detect this radio waves generated by any advanced civilization very, very far away with SK. And so what we know as this SETI, Search for Extraterrestrial Intelligence, will get a real boost with SK. But in addition to that, why only talk about intelligent life which produces radio interference? Maybe there is super intelligent life which does not produce radio interference, but they will produce biomolecules. And these biomolecules have their spectral signature, and that is something that SK is also going to be able to detect. So therefore, it is not just through the extravagant radio interference that life produces, intelligent life produces, but also through biomolecules. SK should be able to, will be certainly a better instrument in probing much deeper for the existence of life in the universe. Whether or not we will detect it is still a matter of speculation, but we will certainly be able to look much better with SK than we have been able to so far.
Well, so this looks like a telescope for future. I hope my son is also watching it, because I'm looking forward to using it in next few years. Like it starts, the construction has already started, and I think first few observations may start in few years of time, but it's going to do these fantastic things over in coming decades. So it's possible that in 10, 15 years time, my son will also be using it.
Indeed, Neeraj. But maybe you can also share your experience with this small part of SK which has already been built and which you are using extensively.
Yes, and that's a very important part of doing science and engineering, which is that when we, even though our ambition may be to build the largest telescope, we cannot build it on the day one, because with the increase in scale, there is enormous increase in complexity also. There are new challenges that come forward, which we have to understand, to process data, to make images out of the data. So to all those things, the way to do these things is to take one step at a time. So what international community has done is that they have built what is called SKA precursors. One is operating in Meerkat. It's a Meerkat telescope in South Africa. It consists of 64 dishes. So and it has been decided that in first 5 years of its operation, it will carry out large survey projects which are along the lines of which are aligned with the theme of SKA. So at IUCAA, we are leading a project, a large survey project, which will observe certain areas of sky using 1500 hours of this telescope, and it will it is looking at cold gas in galaxies at different stages of the universe. That's the main goal of that survey. And at IUCAA, we are bringing in about 1.5 petabytes of data, which we are processing over 3 years. It's very, very huge compared to what we have been doing till now. So it's a lot of new learning for us. And as we have been looking at the flavor of SK is international. So the composition of our team is also international. It is an international effort where we are all have our own science teams, and we are also bringing in our own different softwares and new approaches to process data. We are putting it in all together and trying to understand that how best we can use Meerkat telescope today, so that in next few years when SK is online, we can start using it also efficiently and correctly.
Yeah, thank you, Neeraj. And that brings me to the last thing I want to mention, and that is the data size. So you mentioned 1.5 petabytes of data over 3 years. When SK is fully operational, it is going to produce 500 petabytes of data every year. And processing, managing, transporting, distributing that size of data is an enormous challenge. And that is where there is a fantastic opportunity for our young generation of engineers, students, and so on to contribute. There are some plans, but SK is hoping that by the time SK comes online, there will be more revolutionary plans in place to be able to handle this data, which doesn't exist yet. And that is where I think the future generation of young engineers should take it up as a challenge and then contribute. Thank you.
Yeah, thanks. It's fantastic. Samir, over to you.
Thank you, professors. This was a very unique mode of telling information, which is of such importance to the astronomical community, but also of such more such interest for the people who are joining us today live on this webcast. Thank you very much for creating this, and also in sharing this in very lucid manner. We have some questions, so we'll directly go to them, and very relevant and intelligent questions. The first one asks about optical versus radio astronomy. So how do you compare the reach of both of these compared, with the optical and radio facilities available today? This is asked by Vikas Shukla.
Okay. Yeah, maybe I will say something and Neeraj can add to it. Optical astronomy looks at certain kinds of objects, of course, which produce optical light. And as I have already mentioned, that if we want to go deep in the universe, the wavelength of the light becomes longer and longer. So whereas powerful telescopes like Hubble Space Telescope in space has been able to go very deep, and large telescopes like 30-meter telescope and so on, which are being planned, will also be able to go pretty deep. If you really want to understand universe at its early stages as galaxies are forming, we have to move out of optical band. We have to go down to infrared. This is what JWST, which has just been launched, is going to be able to do. So you can think of JWST as the extension of the optical band to deeper into the universe. Okay, so it will have an excellent reach, and it will certainly produce fantastic new information, which we are all looking forward to. And SK will do the same, but with complementary type of objects. So it's not the same objects. Mostly, it is not going to be the same objects which are going to be seen at both these objects.
Yeah, so as Deepankar, you also highlighted about the role of neutral hydrogen's 21-centimeter line. It's exclusively in radio, and hydrogen being the most abundant element in the universe. And if you can look at this element at a wavelength which is unaffected by any dust, any intervening material, that's the best of both worlds, right? Which is what radio waves bring to us. And then another thing that we were talking about, the magnetic universe, right? That's something which, again, like very unique to radio. It cannot be done at any other wavelength. And of course, then things like pulsars and various kind of experiments that can be carried out with pulsars, and complex molecules that Deepankar, you were talking about, that we can look at. Many of them happen in millimeter, and if they are redshifted, then they would of course again come to lower wavelengths. So there are so many things which can be done only at radio, but we have to look at all these things in a collaborative spirit, like that we look at, we have this one universe, perhaps once, maybe let's keep it one for this talk to keep it simple, because there can be many also. But we have to look at it but it's a complex situation. We have to understand it and look at it in as many ways as possible. Yeah.
Sure. Great answers. And in fact, let me tell you, Neeraj also works for the 30-meter telescope project. So it's in both the boards here.
Yes.
So the next question is also very relevant, that would a combination of the southern and northern hemisphere and putting detectors in both of them give a better resolution for SKA?
The SKA currently is planned to be built only in the southern hemisphere. This is South Africa and Australia. But the two sets of telescopes are not being combined in an interferometric fashion. So there will be interferometers among themselves in a given site, but we are not using the Earth's size for getting extra resolution. So there are telescopes like that, which are called very large baseline interferometers. You would have heard of something that was very much in the news, Event Horizon Telescope. That is a network of that kind, where telescopes are distributed across various hemispheres, and they're brought together to get the very fine resolution that is required to map a black hole. But SK is looking for something different. So there is space for both. So EHT kind of telescope will also work and look at finer and finer details of nearby objects. SK is designed to go very deep and look for something very, very far away.
Dipankar, as we speak, an SK VLBI conference, so people have also started thinking about like, okay, see, because these instruments are so complex that if we think today, it takes maybe 15-20 years for it to become real, because the amount of work that one needs to do, the amount of resources that one needs to gather are tremendous. So people have actually started thinking. So there is a project called SK VLBI which exists, and people are now thinking that how we can use different telescopes which are scattered across the globe to link with SK and then do astronomy. And today's time, when people talk about linking telescope, they talk about real-time linking. Because
Yes.
gone are the days when people collect data as different data on tapes and then send it across. That takes months, and it takes a lot of time.
So now we do all by fiber and then bring the signal together. Yes. Yeah, so that is a natural extension of the SK. And you are right about the lead time. SK, as we know, the concept started in 1991, so it is 30 years already.
Yes.
So and construction is just starting. So actually, construction started at the 30-year mark.
Yes.
It started last year, and it will take 10 years to finish the construction. So that's the kind of timescale that is involved in this sort of instrument.
So these are very deep questions. Samir, are these professional astronomers asking questions?
I have no idea. This is a very great equalizer kind of an event that anybody can ask questions. So I think that we'll keep that as the last one. Although the discussion was so interesting and engrossing, you also cleared up how this science of astronomy is such a global science. It's not a competitive science, but it's more of a collaborative one.
That's right.
And it kind of invites and unites the best minds across the world. And Indian students, Indian professionals are all part of it, and they have a chance to contribute to the future of knowing better this universe. So thank you for putting this together, and we hope that we'll keep having more such sessions, more such fun sessions for all the people who have cared to join us on this YouTube stream. Thank you very much.
Thank you very much. Thank you, Samir. Thanks for the team. Thanks to the team who have
thank you.
Helped us.
It's our pleasure.
Pleasure.
Okay. So now we have kind of come to the last few events of the day, but not the least, of course. And we'll have a special talk on one of the projects just mentioned by Professor Dipankar, the James Webb Space Telescope, which is right now up there in space, 1 million miles away, getting ready to observe the universe. It's just been launched 2 months back, and it's out there looking forward to observing the space in infrared, all its infrared glory. We have a talk about it by actual active scientist, instrument scientist, Dr. Swara Ravindranath at 6 p.m. And while we are getting to that place, we have some more presentations which Shivani will give to you. I just want to let all of you know that after these presentations, we'll have a short break in the stream, but you can come back to the same live link, and at 6, we'll start the next event, which will be the special public talk in the evening, and that will be followed by a live sky show session. We're also looking forward to that because we are hoping that the sky will remain clear, and we'll be able to show you some deep sky objects, some really good images taken from a telescope right here, a special telescope that we are trying to bring for you today. So over to you, Shivani.
Thank you, sir. So before giving the introduction of the next event, I would like to thank all the presenters today. Like everyone has come together to bring this event, build this event really nicely. So the first half of the event has been really nice. It was all about astronomy and astrophysics. But in addition to astronomy and astrophysics, what more IUCAA does? So you must have seen the walkthrough clip of the IUCAA campus, in which at the end we just showed you the outreach center that we have. at IUCAA, which is called the MVS, Muktangan Vigyan Shodhika, which is the outreach center in IUCAA. And here we have different programs for kids in schools, for students of the college, and also for teachers, basically. So there are different programs ranging from science toys demonstrations. We actually do some hands-on science toys. Then we do telescope making. We have basic astronomy sessions for teachers. We do sky watches and much more. So recently we have been working in IUCAA, the outreach center has been working with the ZP school teachers in Pune to develop some new scientific aids or new teaching aids that we can say to make science fun and to make it interactive in the classroom. So that the kids can understand the concept more, and there is a bit of a fun element to that too. So now we'll be presenting to you a compilation of some videos. So before this event, before the Science Day that we are celebrating today, we had launched a competition for some teachers in this program, the ZP School Teachers Program. The teachers have sent some videos and will be playing some selective videos for you here. So this program will be like mixed in English and in Marathi. So आपल्या इथे जर मराठी ऑडियन्स पण असेल तर तुमच्यासाठी पण आम्ही हे काही व्हिडिओज मराठीत घेऊन आलो आहोत की ज्याच्यात तुम्हाला वेगवेगळी खेळणी बघता येतील आणि ती तुमच्या मुलांना, तुम्ही शिक्षक असाल तर ती तुमच्या मुलांना वर्गात तुम्हाला दाखवता येतील. तुम्ही मुलं असाल तर ती अगदी सोप्या सामानातनं, अगदी घरगुती मिळेल अशा सामानातनं तुम्हाला घरी सुद्धा बनवता येतील. सो जास्त वेळ मी घेत नाही आणि आपण आता व्हिडिओला सुरुवात करूया.
नमस्कार, मी कसार सुरेश, एडेश्वर विद्यामंदिर एडगाव या शाळेमध्ये कार्यरत आहे. 18 फेब्रुवारी या दिवशी आयुका पुणे आणि विज्ञान अध्यापक संघ पुणे यांच्या संयुक्त विद्यमाने मुलांसाठी आपण सायन्स विज्ञान कसं सोपं होईल यासाठी काय करू शकतो, तर त्यासाठी आपण वेगवेगळं त्याच्यामध्ये काहीतरी नवीन आणायचा असा विचार केला आणि त्या दृष्टीने माझ्याकडे एक मॅजिक बॉक्स आहे. या मॅजिक बॉक्समध्ये एकूण 40 पीस आहेत. त्यामध्ये 24 स्टिक आहे आणि 16 बॉल आहेत. याच्या साह्याने आपल्याला इयत्ता 10वी त्याचबरोबर इयत्ता 9वी या वर्गामध्ये आपण सायन्स ज्या वेळेला शिकवतो त्यावेळेला रसायनशास्त्र त्यांना कसं सोपं होईल या उद्देशाने हे मॅजिक बॉक्स अतिशय महत्त्वाचं कार्य करतं. आता त्याच्यामध्ये असणारे हे जे बॉल आहेत आणि स्टिक आहेत त्या कशा पद्धतीने याच्यामध्ये ठेवलेले आहेत ते सुद्धा आपल्याला दिसतं आहे. त्यानंतर याचा उपयोग कशासाठी होतो तर रसायनशास्त्रामध्ये कार्बनी संयुगे आहेत इयत्ता 10वीला आणि त्याचबरोबर कार्बन कंपाऊंड आपण इयत्ता 9वीला त्या ठिकाणी पाहिलं तर त्यांना आपल्याला त्याचं स्ट्रक्चर, कार्बनी कंपाऊंडचं स्ट्रक्चर कशा पद्धतीने, त्याचबरोबर सहसंयुज संयुगे कशा पद्धतीने तयार होतात, त्यानंतर मूलद्रव्याचा जो अणू आहे तो अणू इलेक्ट्रॉन शेअरिंगसाठी कशा पद्धतीने देतात हे आपल्याला या मॅजिक बॉक्सच्या साहाय्याने दाखवता येतं. तर सर्वप्रथम आपण काय करूया की सहसंयुज बंध जे आहेत ते बंध कसे तयार होतात. फॉर एक्झाम्पल आपण हायड्रोजन घेतला. सपोज हा एक बॉल आहे, हा एक हायड्रोजन आहे आणि इथे या ठिकाणी मी तुम्हाला एक मॅग्नेटिक स्टिक दाखवतो आहे. ह्या मॅग्नेटिक स्टिकला हा एक हायड्रोजन या ठिकाणी येऊन या ठिकाणी बसलेला आहे. त्याच्यानंतर मी दुसरा एक हायड्रोजन या ठिकाणी या तुम्हाला मेटलचा बॉल एक हायड्रोजन आहे असं आपण समजूया आणि हा दुसरा हायड्रोजन असेल. 2 हायड्रोजन एकमेकाला एका एकेरी बंधाने जोडले गेले आणि त्याच्यामुळे यांच्यामध्ये एक एकेरी बंध निर्माण झाला आणि अशा पद्धतीने हा सहसंयोज बंध तयार झाला. त्याच्यानंतर आपल्याला दुहेरी बंध कसा तयार होतो, हे अणू काय करतात, परस्पर भागीदारी करतात इलेक्ट्रॉनची. मग परस्पर काय करतात, 2-2 इलेक्ट्रॉन भागीदारीमध्ये देतात आणि त्यांच्यामध्ये एक दुहेरी बंध तयार होतो. मग हा एक ऑक्सिजन आपण मानूया आणि हा दुसरा ऑक्सिजन आपण मानूया. अशा पद्धतीने ऑक्सिजन मध्ये हा दुहेरी बंध या ठिकाणी निर्माण होतो. त्याच्यानंतर आपल्याला नायट्रोजनचं एक उदाहरण तिहेरी बंधासाठी घेता येईल. फक्त आपण एक स्टिक या ठिकाणी घेऊ शकतो आणि हा तिहेरी बंध आपण दाखवू शकतो. अशा पद्धतीने हा तिहेरी बंध निर्माण होतो. हे झाले सहसंयोज बंध. आता यानंतर आपल्याला कार्बनी काही संयुगे आहेत. त्याच्यामध्ये तुम्हाला मिथेन असेल, इथेन असेल, त्यानंतर आणखीन बेन्झीन असेल, त्याच्यानंतर सायक्लोपेंटेन असेल. हे सर्व आपल्याला या पेटीच्या मध्ये असणारे जे बॉल आणि स्टिक आहे यांच्या साह्याने विद्यार्थ्यांना प्रत्यक्षात हाताळायला देणं सोपं होतं, म्हणून त्यांना आपण प्रत्यक्षात स्ट्रक्चर तयार करायला सांगू शकतो. जसं की आपण आता या ठिकाणी मिथेनचं कशा पद्धतीने स्ट्रक्चर तयार होतं हे आपण या ठिकाणी पाहूया. पहा, या ठिकाणी आपल्याला 4 स्टिक लागतील आणि त्याचबरोबर 5 बॉल लागतील. एक कार्बन म्हणून आपण मध्यभागी घेणार आहोत आणि हायड्रोजन 4 बाजूला 4 आपल्याला घ्यायचे आहेत. या पद्धतीने आपल्याला या ठिकाणी मिथेनचं सहजतेने स्ट्रक्चर तयार करता येतं. मग सायन्स आपल्याला सहज सोपं व्हावं यासाठी या उपकरणाचा आपल्याला उपयोग होतो. आता याच्यामध्ये हे मी फक्त मिथेनचं स्ट्रक्चर तयार केलेलं आहे. त्याचबरोबर इथेनचं पण होईल. त्याचबरोबर सायक्लोपेंटेन त्या ठिकाणी तयार करता येईल, बेन्झीन तयार करता येईल. विविध स्ट्रक्चरे आपल्याला या पेटीच्या साहाय्याने करता येईल आणि विद्यार्थ्यांनाही या संकल्पना सहजतेने समजतील असं मी आत्तापर्यंत 10 वर्ष जवळजवळ 10वीच्या विद्यार्थ्यांना 9वीच्या विद्यार्थ्यांना विज्ञान शिकवतो आहे. त्यामुळे त्यांना सहजतेने ते समजतं आणि अगदी त्यांना कन्सेप्ट लगेच समजतो. धन्यवाद. यानंतर अजून एक मी उपकरण तयार केलेलं आहे आणि ते म्हणजे आपला अणू. आता एलिमेंटचा अणू कशा पद्धतीने असतो याचं स्ट्रक्चर, फॉर एक्झाम्पल मी या ठिकाणी क्लोरीन दाखवलेला आहे. आता हा जो क्लोरीन आहे पहा, या ठिकाणी ही पहिली कक्षा आहे, त्याच्यानंतर ही दुसरी कक्षा आहे आणि ही तिसरी कक्षा आहे. आता आपल्याला सर्वांना माहिती आहे की क्लोरीनच्या पहिल्या कक्षेमध्ये 2 इलेक्ट्रॉन असतात. किती इलेक्ट्रॉन असतात? 2. आणि दुसऱ्या कक्षेमध्ये त्याच्या 8 इलेक्ट्रॉन्स असतात आणि तिसऱ्या कक्षेमध्ये त्याच्या 7 इलेक्ट्रॉन असतात. अशा पद्धतीने हे इलेक्ट्रॉन सुद्धा या ठिकाणी मी वसवलेले आहेत, ते पण मेटलच्या बॉलच्या साहाय्याने. अशा पद्धतीने मुलांना सायन्स सोपं जाईल असा माझा मानस आहे. धन्यवाद.
विद्यार्थी मित्र, मी श्री कांबळे डीडी संत निमनाथ स्वामी माध्यमिक विद्यालय बोंगवली, तालुका भोर, जिल्हा पुणे. आयुका ही एक नामांकित संस्था. या नामांकित संस्थेसाठी हा आपल्या वर्गातील इयत्ता 8वीचा व्हिडिओ, हा व्हिडिओ आपण त्यांना अनेक विद्यार्थ्यांना दाखवण्यासाठी, प्रेझेंटेशनसाठी मी हा त्यांना पाठवत आहे. विद्यार्थी मित्र, आपण रासायनिक अभिक्रिया हे प्रकरण पाहत आहात. या रासायनिक अभिक्रियेमध्ये वेगवेगळ्या प्रकारच्या अणूंचा, वेगवेगळ्या प्रकारच्या रेणूंचा कसा सहभाग येतो, कसा होतो, तो आपण प्रत्यक्ष या चुंबकीय फळ्याद्वारे आज आपण या ठिकाणी पाहणार आहोत. विद्यार्थी मित्र, या ठिकाणी पाहत असताना समोर माझा हा इयत्ता 8वीचा वर्ग हा समोर आहे. या 8वीच्या वर्गाच्या समोर हा पाठ मी सादर करत आहोत, कारण का हे प्रकरण 8वीचं आहे आणि 8वीच्या या प्रकरणामध्ये आपल्याला हा व्हिडिओ आपण सर्वांनी पाहूया. यामध्ये आयनिक संयुग कसं होतं, या आयनिक संयुगाची निर्मिती कशी होते हे आपण प्रत्यक्ष बघूया. वेगवेगळ्या प्रकारच्या शास्त्रज्ञ डॉल्टनच्या मते हा जो अणु आहे हा नुसता भरीव आहे अशा पद्धतीने डॉल्टनने त्या ठिकाणी सांगितलेलं होतं. परंतु यानंतर परत रुदरफोर्डनं त्याच्यावरती संशोधन केलं आणि असं वाटलं की हा जो अणु आहे कडेनी या ठिकाणी इलेक्ट्रॉन फिरत आहेत अशा पद्धतीने या रुदरफोर्डला त्या ठिकाणी दिसून आलं. रुदरफोर्ड नंतर आपल्याला थॉम्सन हा शास्त्रज्ञ, या शास्त्रज्ञाने अशा पद्धतीने कलिंगड कापल्यानंतर कणेच्या ज्या बिया आहेत त्या इलेक्ट्रॉन आहेत अशा पद्धतीने त्या ठिकाणी त्यांनी दर्शवलं आणि मध्यभागी काहीतरी चार्ज आहे आणि मग त्याच्यावर संशोधन झालं की अणु कसा आहे. म्हणून अशा पद्धतीचा हा अणु, ह्या पद्धतीचा अणु आहे. म्हणून या पद्धतीचा अणु आहे. हा अणु मध्यभागी प्रोटॉन आणि न्यूट्रॉन कडेने इलेक्ट्रॉन फिरत आहेत आणि त्याला 4 कक्षा आहेत. किती कक्षा आहेत? 4 कक्षा आहेत. आणि या 4 कक्षाला नावं दिली KLMN अशा 4 कक्षा. आणि त्या 4 कक्षांना व्हॅल्यू आहे. व्हॅल्यू म्हणजे किंमत. पहिल्या कक्षेमध्ये कमीत कमी 2 इलेक्ट्रॉन, दुसऱ्या कक्षेमध्ये 8 इलेक्ट्रॉन, तिसऱ्या कक्षेमध्ये 18 इलेक्ट्रॉन आणि चौथ्या कक्षेमध्ये 32 इलेक्ट्रॉन अशा पद्धतीचे इलेक्ट्रॉन त्याच्यामध्ये विखुरलेले आहेत. म्हणून विद्यार्थी मित्रो, आपण एखाद्या आयनिक संयुगाची निर्मिती कशी होते, संयुग कसं तयार होतं ते आपण प्रत्यक्ष बघूया. म्हणून पटकन मी थोड्या वेळासाठी या ठिकाणी कागद लावला होता. विद्यार्थी मित्रो, या ठिकाणी आपण एखाद्या इलेक्ट्रॉनचा अभ्यास करताना या ठिकाणी सोडियम क्लोराईड Na+Cl या दोघांचा अभ्यास करणार आहोत. सोडियम आणि क्लोरीन हे 2 मूलद्रव्य अणु एकत्र कशा पद्धतीने येतात ते या ठिकाणी बघूया. त्यांचा संयुगबंध, आयनिक संयुगबंध कसा होतो ते आपण बघूया. विद्यार्थी मित्रो, या ठिकाणी पहिले जे सोडियम आहे या सोडियम मध्ये कमीत कमी 8 इलेक्ट्रॉन असतात. हे माझे वेगळ्या प्रकारचे इलेक्ट्रॉन आहेत. हे पण इलेक्ट्रॉन आहेत. सोडियम इलेक्ट्रॉन, क्लोरीन इलेक्ट्रॉन हे आपण या ठिकाणी बघूयात. मी काही इलेक्ट्रॉन काढून ठेवलेले आहेत. विद्यार्थी मित्रो, या ठिकाणी पहिला आहे सोडियम. या सोडियम मध्ये पहिल्या कक्षेमध्ये 2, त्याचं जी काय पहिली कक्षा आहे या पहिल्या कक्षेत कमीत कमी 2 इलेक्ट्रॉन सोडियम मध्ये, दुसऱ्या कक्षेमध्ये 8 इलेक्ट्रॉन आणि तिसऱ्या कक्षेमध्ये 1 इलेक्ट्रॉन. म्हणजे त्याचं जे बंध आहे तो 11. याच्यामध्ये 11 इलेक्ट्रॉन असतात सोडियम मध्ये. क्लोरीन मध्ये 17 इलेक्ट्रॉन असतात. पहिल्या कक्षेमध्ये 2, दुसऱ्या कक्षेमध्ये 8 आणि तिसऱ्या कक्षेमध्ये 7. म्हणजे तिसरी कक्षा काय होते, व्हॅल्युएबल आहे. पण तिसऱ्या कक्षेमध्ये जर 2 किंवा 2पेक्षा अधिक वेगळ्या प्रकारचे अणु एकत्र येऊन त्यांच्यापासून नवीन उत्पादित बनतं, आयनिक सहसंयुज बनतो, सहसंयुज बंध बनतो. अशा पद्धतीचे बंध या ठिकाणी तयार होतात. म्हणून या ठिकाणी बघा, पहिल्या कक्षेत 2, दुसऱ्या कक्षेमध्ये 8 मोजायचे आहेत का नाही. 1 2 3 4 5 6 7 8 आणि शेवटच्या कक्षेत 1 इलेक्ट्रॉन. आता क्लोरीन मध्ये बघूया आपण. पहिल्या कक्षेमध्ये 2 इलेक्ट्रॉन, 17 आहेत ना. पहिल्या कक्षेत 2 1 2, दुसऱ्यात 1 2 3 4 5 6 7 8 आणि शेवटच्या तिसऱ्या कक्षेत 1 2 3 4 असेल. आता मला अजून किती लावायचे आहेत? चल बरं विद्यार्थी, तू ये पुढं. मला अजून आता शेवटच्या कक्षेत 7 आहेत. ये बाळा तू पण. विद्यार्थी या ठिकाणी येत आहेत आणि लावायच्या मधला 1 इलेक्ट्रॉन वर तू अलीकडे तोंड कर. आता तू 1 लाव बाळा. बघा, विद्यार्थ्यांचा सहभाग घेऊन अशा पद्धतीने किती झाले मोजा?
1 2 3 4 5 6.
अजून किती राहिला? 1 राहिला. वा, व्हेरी गुड, छान. म्हणजे विद्यार्थ्यांना अशा पद्धतीने छान संकल्पना समजते, स्वतः विद्यार्थी सहभाग घेतात आणि छानपैकी मोज. आता बाळा तूच मोज तू हे पहा हळूच खाली ओके मोज आता
1 2 3 4 5 6 7
7 पहिल्या कक्षेमध्ये 2 दुसऱ्या कक्षेत 8 तिसऱ्या कक्षेत 7 बघा बसा खाली विद्यार्थी मित्र म्हणजे आपल्याला आता सोडियम आणि क्लोरीन शेवटचे कक्षा व्हॅल्युएबल आहे म्हणजे त्याच्यामध्ये एकात 1 इलेक्ट्रॉन जास्त आहे तिसऱ्या कक्षेमध्ये आणि इथं यात 7 पण 1 इलेक्ट्रॉन देणं सोपं आहे 7 इलेक्ट्रॉन घेणं अवघड आहे म्हणून हा सोडियम काय करतो की बाबा चल मी तुला माझा 1 इलेक्ट्रॉन देतो म्हणजे तुझी शेवटची कक्षा अष्टक पूर्ण होईल त्याला अष्टक म्हणतात आणि अष्टक पूर्ण झाल्यामुळं ते दोघं जण एकमेकांमध्ये येतील मग एकमेकांमध्ये येताना बघा सोडियम प्लस क्लोरीन इज इक्वल टू सोडियम क्लोराईड Na प्लस का झाला तर सोडियमने 1 इलेक्ट्रॉन दिला म्हणजे तो आयन झाला एक आयन सोडियम 1 इलेक्ट्रॉन दिला सोडियमनं आणि क्लोरीननं 1 इलेक्ट्रॉन घेतला म्हणून त्याच्यात वाढ झाली म्हणून Na प्लस Cl मायनस 1 घेतला त्यांनी म्हणून मायनस तो झाला म्हणून या ठिकाणी दोघंही एकत्र आले आणि दोघंही एकत्र आल्यामुळे शेवटचे अष्टक पूर्ण झालं शेवटचं अष्टक पूर्ण झालं मग अष्टक पूर्ण झाल्यानंतर चल बाळा तू विद्यार्थिनी पाठीमागची आणि तू एक ये आता दोघी तिथे उभा राहा आम्हाला शेवटच्या कक्षेत तू दाखव 8 इलेक्ट्रॉन आहेत का मोजून दाखव 1 2 3 4 5 6 7 8 व्हेरी गुड पलीकडचं तू मोजून दाखव
1 2 3 4 5 6 7
इथं 7 हा म्हणजे दोघांच्या कक्षेत शेवटच्या कक्षेमध्ये बसा थँक्यू समजलं छानपैकी फार सुंदर समजलं बसा वा व्हेरी गुड तर विद्यार्थी मित्रांनो अशा पद्धतीने आपल्याला आयनिक संयुगाची निर्मिती झाली आणि त्यापासून सोडियम क्लोराईड Na प्लस Cl मायनस इज इक्वल टू Na प्लस Cl मायनस सोडियम क्लोराईडची निर्मिती झाली सोडियम क्लोराईड म्हणजेच मराठीत काय म्हणतात मीठ सोडियम क्लोराईड म्हणजेच काय मिठाची निर्मिती झाली छान आजचा हा पाठ या ठिकाणी आपल्या सगळ्यांना समजला धन्यवाद
Hello my dear students, how are you all? I hope you all are fine. Myself Mr. Rohit Suresh Damre. I am working as an assistant teacher in Sundarbai Marathi Vidyalaya, Karadi, Pune 40. Today we are going to learn something interesting about the structure of an atom. Students, do you know that first of all the Indian philosopher Kanad he stated that there is a limit to divide matter into small particles. The indivisible particles were named by Kanad Muni as a Parmanu. Later on, the Greek philosopher Democritus he stated that matter is made up of small particles and these cannot be divided. So the smallest particles were named by Democritus as an atom. Because in Greek language, atmos means the one that cannot be further divided. British scientist John Dalton he put forth his atomic theory in 1803. So according to this theory, a matter is made up of the smallest particles, which is known as an atom. So atom it is a hard and solid structure and which is indivisible or indestructible. The plum pudding model of an atom it was discovered by Sir J.J. Thomson. So according to Thomson, the positively charged particles they are placed everywhere in the atom and a negatively charged particles they are embedded in the atom. So Thomson he compared his structure of an atom with the structure of watermelon. Do you know watermelon? Then the Rutherford he explained atomic model with the help of his scattering experiment. There is a positively charged nucleus at the center of atom. Almost all the mass of the atom is concentrated in its center of the nucleus. The negatively charged particles they are called which were called electrons. They were revolved around the nucleus, and the total energy, the total negatively charged particles they are neutralized by the total positive charge which are present in the nucleus. So positively charged particles and negatively charged particles, they are of equal amount, hence the atom is electrically neutral. I have the structure of an atom. So this is the structure of atom, in which you can see that at the center of this structure of atom there is a nucleus. There is a nucleus which is made up of positively charged protons and neutrons which does not have any charge. While outside the nucleus, the electrons, the negatively charged electrons, they are revolving around the nucleus in a particular orbit. So you can see here that the electrons, they are revolving around a nucleus. So the first orbit from the nucleus, that orbit is, he called it, the Niels Bohr, he called it as L orbit, K orbit. The second orbit, it is known as L orbit. The third orbit, it is known as M orbit. Now the first orbit, that is K orbit, it has a capacity of 2 electrons in it. So you can see here, the first electron is here and the second electron is here. So the 2 electrons, they are revolving in that first orbit. And this formula of electrons, that how many electrons should be there in an orbit, it is discovered by a formula that is 2n square. So where n is the number of orbit. So according to that formula, the second orbit, that is L orbit, it has a capacity of 8 electrons. That is 8 electrons, they are revolving around this in the second orbit. Similarly, the third orbit, M orbit, that is, it has a capacity of 18 electrons. So according to this formula, the M orbit, it will have 18 electrons in it which are revolving around the nucleus. So the electrons which are revolving in a particular orbit, they are having their fixed energy amount. So whenever they have to jump from one orbit to the another orbit, they have to emit some energy or they have to accept or gain some energy. Means when the electrons from the upper orbit, they are going to the lower orbit, they must have to lose energy. While if the electrons, they have to go from inner orbit to the upper orbit, then they must have to gain electrons. So students, so I have made this structure of an atom with the help of a foam sheet. It's a very simple model, foam sheet, and I have just colored it, just placed a centrally placed circle is nothing but the nucleus, where I have shown electrons, positively charged protons, and neutrons which does not have any charge, and a small concentric circles I have placed across this nucleus, on which a small circles of black colored foam sheet I have placed them here, so which represents the electrons. So do you like it?
मी कुलकर्णी आशिष हणोक. आपण जो विषय निवडलेला आहे रासायनिक अभिक्रियांचे प्रकार आणि त्यासाठी जे खेळणं बनवलेलं आहे, कारण खेळणाधारित अध्यापन पद्धतीचा वापर करून आपण पाहणार आहोत. तर या खेळण्याचं नाव आहे विस्थापन घड्याळ. तर सर्व वयोगटातील मुलांना खेळणी आणि खेळांचं आकर्षण असतं. खेळामध्ये सहभागी करून घेणे, त्यांना विज्ञानाच्या मूलभूत संकल्पना समजून घेण्यात रस निर्माण करणे, हे विद्यार्थ्यांना मानसिक तसेच स्वतःच्या कृतीने शिकण्याचा अनुभव घेण्याची संधी प्राप्त करून देतात, ज्यामुळे त्यांची समस्या सोडवण्याची कौशल्य सुधारतात आणि त्यांचे विज्ञान सामग्रीचं ज्ञान देखील सुधारतं. धातू इतर धातूंच्या क्षारांच्या द्रावणांची कशी प्रतिक्रिया देतात याबद्दल आपण या खेळण्याच्या सहाय्याने माहिती घेणार आहोत. आता या ठिकाणी इथं चकती केलेली आहे आणि ह्या चकतीवरती 5 समान भागामध्ये चकती विभागलेली आहे आणि 5 भागांमध्ये आपण धातूंच्या वेगवेगळ्या क्षारांची नावं लिहिलेली आहेत. जसं की या ठिकाणी तुम्हाला दिसेल झिंक सल्फेट सोल्युशन, कॉपर सल्फेट सोल्युशन, लेड नायट्रेट सोल्युशन, ॲल्युमिनियम सल्फेट सोल्युशन, त्यानंतर आयर्न सल्फेट सोल्युशन, आणि या चकतीवरती आपण इथं एक लाकडी पट्टी बनवलेली आहे, ॲरो. त्या ॲरोवरती मी आत्ता जे 12 धातूंची नावं वाचलेली आहेत ते 12 धातूंची नावं या ठिकाणी या पट्टीवरती स्केचपेननी लिहिलेली आहेत. तर या पद्धतीने घड्याळाची जशी रचना असते त्या पद्धतीने हे विस्थापन घड्याळ आपण बनवलेलं आहे. या घड्याळावरती हा काटा संपूर्ण व्यवस्थित फिरू शकतो आणि कशा पद्धतीने हा खेळ खेळायचा आहे आणि विस्थापन अभिक्रिया जी आहे ती समजून घेताना विद्यार्थ्यांना या घड्याळाचा आपल्याला उपयोग करता येईल. विस्थापन घड्याळ हे घड्याळासारखी रचना असल्यामुळे याला विस्थापन घड्याळ असं म्हटलेलं आहे. तर विस्थापन घड्याळ वापरून खेळ खेळत असताना हा खेळ आपल्याला वर्गाच्या आत किंवा बाहेर खेळला जाऊ शकतो आणि सर्वसमावेशक वर्ग वातावरणामध्ये सर्व विद्यार्थ्यांना, ज्यांना शिकताना अडचणी येऊ शकतात किंवा येऊ शकत नाहीत, अशा सर्वच प्रकारच्या विद्यार्थ्यांना एकत्र शिकण्याची संधी प्रदान करतात. शिक्षक विद्यार्थ्यांना, आता हा खेळ आहे त्यामुळं शिक्षक काय करणार आहेत तर वर्गातील विद्यार्थ्यांचे गट करणार आहेत. शिक्षक विद्यार्थ्यांना गट अ आणि गट ब अशा 2 संघामध्ये विभागतील. शिक्षक त्यांच्या हातामध्ये हे विस्थापन घड्याळ ठेवतील. या पद्धतीने हे विस्थापन घड्याळ विद्यार्थ्यांकडे दिले जाईल. म्हणजे विद्यार्थ्यांचा कृतीयुक्त सहभाग आपल्याला या ठिकाणी घेणं अपेक्षित आहे. शिक्षक त्यांच्या हातामध्ये विस्थापन घड्याळ ठेवतील आणि प्रत्येक संघातील एक सदस्य सुलभकाच्या म्हणजे शिक्षकाच्या पुढे उभे राहतील. त्या ठिकाणी खेळामध्ये जशी नाणेफेक असती तशी या ठिकाणी पण शिक्षक नाणेफेक करतील आणि प्रथम संधी मिळालेल्या गटाला विस्थापन घड्याळाच्या घडीवर दर्शवलेल्या कोणत्याही एका धातूचं नाव घ्यावं लागेल. या ठिकाणी आता जो संघ, ज्या संघाने टॉस जिंकलेला आहे, ज्या संघाने नाणेफेक जिंकलेली आहे, त्या संघाचा एक विद्यार्थी काय करेल तर ह्या लाकडी पट्टीवरती आपण जे धातूची नावं लिहिलेली आहेत यापैकी कोणत्याही एका धातूचं नाव त्या ठिकाणी तो विद्यार्थी घेईल. मग 12 धातूंची जी नावं लिहिलेली आहेत, आता उदाहरणार्थ विद्यार्थ्याने लोखंड या धातूचं नाव घेतलं. तर या ठिकाणी इथं आपल्याला दिसेल, या ठिकाणी इथं लोखंड हा धातू आहे. समजा हा लोखंड धातूचं नाव जर घेतलं तर आपल्याला विद्यार्थ्यांना काय शिकवायचं, विस्थापन अभिक्रियेच्या संदर्भात आपल्याला शिकवायचं आहे. तर लोखंड या धातूचं नाव जर घेतलं, गट अ चे सदस्य विस्थापनाची चकती स्वतंत्रपणे हलवतील आणि ती चकती स्वतः थांबेपर्यंत प्रतीक्षा करतील. स्टिक ही कोणत्याही धातूच्या क्षाराच्या द्रावणाच्या दिशेने थांबेल, जसं कॉपर सल्फेट. आता उदाहरणार्थ ही स्टिक आपण हलवली आणि ती स्टिक जर कॉपर सल्फेट या द्रावणापाशी जर थांबली, कॉपर सल्फेटच्या द्रावणापाशी जर थांबली, या ठिकाणी इथं कॉपर सल्फेटच्या द्रावणाचं नाव आहे, ही स्टिक कॉपर सल्फेटच्या द्रावणापाशी जर थांबली तर काय होईल पहा, स्टिक कोणत्याही धातूच्या क्षाराच्या द्रावणाच्या दिशेने थांबेल, उदाहरणार्थ कॉपर सल्फेट. आता गट ब च्या विद्यार्थ्याला आपण खालील प्रश्न विचारणार आहोत. लोखंड धातू, कारण ह्या स्टिकवरती लोखंड धातूचं त्याने नाव घेतलेलं आहे. लोखंड धातू कॉपर सल्फेट द्रावणामधून तांब विस्थापित करेल का, हा प्रश्न ब गटातील विद्यार्थ्याला विचारला जाईल. आणि जर करत असेल तर त्या अभिक्रियेचं संतुलित रासायनिक समीकरण लिहायला सांगायचं आहे. जर ब गटातील समूहाचे सदस्य योग्य रीतीने उत्तर देऊ शकत असतील तर त्या गटाला 1 गुण मिळेल. जर तो किंवा ती संतुलित रासायनिक समीकरण योग्य रीतीने लिहितो तर गट ब ला आणखी 1 गुण मिळेल. पहा, उत्तर जर बरोबर देत असेल, रासायनिक समीकरण विद्यार्थी लिहिणार आहे फळ्यावरती, म्हणजे त्या विद्यार्थ्यांचा कृतीयुक्त सहभाग या ठिकाणी घेणार आहे. आणि म्हणून या दोन्ही प्रश्नांची उत्तरं जर गट ब ने दिली तर त्या गट ब ला 2 गुण मिळणार आहेत. आणि जर गट ब या प्रश्नाची योग्य उत्तरं देण्यास सक्षम नसेल तर गट अ ला उत्तरं देण्याची संधी दिली जाणार आहेत. आणि गट अ नी जर या प्रश्नाची, दोन्ही प्रश्नांची उत्तरं बरोबर दिली तर हे मार्क जे आहेत, हे गुण जे आहेत ते गट अ ला मिळणार आहेत. आणि मग याच पद्धतीने खेळ सुरू राहणार आहे. तर अशा पद्धतीने जास्तीत जास्त गुण मिळवणारा जो संघ असेल तो या खेळामध्ये विजयी घोषित केला जाईल. तर अशा रीतीने खेळाआधारित अध्यापन शास्त्राचा वापर करून आपण विज्ञानातील वेगवेगळ्या संकल्पना विद्यार्थ्यांना समजावून सांगू शकतो. IUCAA आणि विज्ञान अध्यापक संघ, जिल्हा विज्ञान अध्यापक संघ, पुणे जिल्हा विज्ञान अध्यापक संघ यांचा मी आभारी आहे.
नमस्कार विद्यार्थी मित्रांनो, मी रावसाहेब चौधरी, आपणा सर्वांचं स्वागत. आज आपण चुंबकीय पाणबुडी किंवा डान्सिंग बॉल या प्रयोगाची माहिती पाहणार आहोत. आपल्याला माहिती आहे, कोणत्याही वाहकातून विद्युतधारा वाहताना त्या वाहकाभोवती चुंबकीय क्षेत्र निर्माण होतं. या प्रयोगासाठी लागणारं साहित्य आहे 1.5 व्होल्टची बॅटरी, तांब्याची तार, टाचणी, थर्माकोलचा बॉल, पाणी आणि काचेची परीक्षा नळी. प्रथम काचेच्या परीक्षा नळीला तांब्याच्या तारेचे 20 ते 25 वेढे घ्या. तारेचं दोन्ही टोकाचं आवरण काढा. अर्ध्यापेक्षा जास्त पाणी परीक्षा नळीमध्ये भरा. त्यानंतर टाचणीसह थर्माकोलचा बॉल परीक्षा नळीमध्ये टाका. तो आपल्याला तरंगताना दिसेल. परंतु जेव्हा आपण विद्युतधारा चालू करतो त्यावेळेस त्या तारेमध्ये चुंबकीय क्षेत्र निर्माण होतं आणि टाचणी चुंबकीय क्षेत्राकडे आकर्षित होते. अशा पद्धतीनं या ठिकाणी आपण विद्युतधारा चालू केली, बंद केली, चालू केली, बंद केली, तर तो बॉल आपल्याला डान्स करताना दिसतो. अशा पद्धतीनं आपण डान्सिंग बॉल किंवा पाणबुडी या प्रयोगाची माहिती या उपकरणाच्या साहाय्यानं पाहू शकतो. बदलणारा विद्युतरोध किंवा रेझिस्टन्स पेन्सिल हा प्रयोग पाहणार आहोत. आपल्याला माहिती आहे की कोणत्याही पदार्थातून विद्युतधारा वाहते तेव्हा तो पदार्थ सुवाहक असतो आणि ज्या पदार्थातून विद्युतधारा वाहत नाही तो पदार्थ दुर्वाहक पदार्थ असतो. तर या प्रयोगासाठी लागणारं साहित्य आहे एक लाकडी स्टँड, स्लीपरचा तळ, बल्बसह होल्डर, पेन्सिल, क्रोकोडाईल पिन, सेफ्टी पिन आणि 1.5 व्होल्टच्या 3 बॅटरी. अशा पद्धतीनं सर्व साहित्याची जोडणी केली असता पेन्सिल जी आहे ती अशा पद्धतीनं तासून घ्या की जेणेकरून तिचं ग्रॅफाइट हे पूर्णपणे आपल्याला दिसेल. कारण या प्रयोगामध्ये ग्रॅफाइट हेच विद्युतरोधाचं काम करणार आहे. आपण जेव्हा विद्युतधारा सुरू करतो तेव्हा परिपथ पूर्ण होतो आणि बल्ब आपल्याला पूर्णपणे प्रकाशित झालेला दिसतो. परंतु जसजसं आपण डाव्या बाजूला जाऊ तसतसं ग्रॅफाइट हे परिपथामध्ये येतं आणि आपल्याला विद्युतरोध वाढलेला दिसतो आणि बल्ब कमी प्रकाशित झालेला दिसतो. पुन्हा आपण जसजसं उजव्या बाजूला जाऊ तसतसं ग्रॅफाइट हे विद्युत परिपथातून कमी होतं आणि आपल्याला बल्ब हा जास्त प्रमाणामध्ये प्रकाशित झालेला दिसतो. अशा पद्धतीनं आपण या प्रयोगाच्या साहाय्यानं बदलणारा विद्युतरोध म्हणजे काय ते पाहू शकतो. या प्रयोगासाठी लागणारं साहित्य आहे एक नट बोल्ट, पुठ्ठ्याचे स्टँड, 2 पुठ्ठ्याच्या चकत्या आणि एक छोटी स्केल. याच्या साहाय्यानं आपण विद्यार्थ्यांना क्लॉकवाईज डायरेक्शन आणि अँटी क्लॉकवाईज डायरेक्शन म्हणजे काय ते सांगू शकतो. जेव्हा आपण हा स्क्रू क्लॉकवाईज डायरेक्शनने फिरवू तेव्हा त्याची डिस्प्लेसमेंट आपल्याला डाऊनवर्ड दिशेने दिसते, म्हणजे तो स्क्रू टाईट होतो. याच्या उलट जेव्हा आपण हा स्क्रू अँटी क्लॉकवाईज डायरेक्शनने फिरवू तेव्हा स्क्रू रिमूव्ह होतो आणि त्याची डिस्प्लेसमेंट आपल्याला अपवर्ड होताना दिसते. फ्लेमिंगचा डाव्या हाताचा नियम आपण एका छोट्याशा प्रयोगाने पाहणार आहोत. या प्रयोगासाठी लागणारं साहित्य आहे एक प्लॅस्टिकचा बॉक्स, तांब्याची तार, मॅग्नेट आणि 12 व्होल्टची बॅटरी. अशा पद्धतीनं साहित्यांची जोडणी करून घेतली आणि तांब्याची तार या ठिकाणी वाहक म्हणून कार्य करणार आहे. जेव्हा या वाहकातून विद्युतधारा वाहते तेव्हा फ्लेमिंगच्या डाव्या हाताच्या नियमानुसार आपल्याला त्या तारेचं विचलन झालेलं दिसतं. अशा पद्धतीनं आपण फ्लेमिंगचा नियम पाहू शकतो. फ्लेमिंगच्या नियमानुसार अंगठा वाहकावरील बल, तर्जनी चुंबकीय क्षेत्राची दिशा आणि मधले बोट विद्युतधारेची दिशा दाखवते. या नियमाप्रमाणे आपण विद्युतधारा चालू केल्यानंतर अशा पद्धतीने आपल्याला वरच्या दिशेने बल प्रयुक्त होते आणि या तारेचं विचलन झालेलं दिसतं. यानंतर आपण विद्युत चलित्राची रचना आणि कार्य एका प्रयोगाच्या साहाय्यानं पाहणार आहोत. या प्रयोगासाठी लागणारं साहित्य आहे 2 स्ट्रॉंग मॅग्नेट, तांब्याची तार, माचीसचा बॉक्स, लाकडी बोर्ड आणि 12 व्होल्टची बॅटरी. प्रथम एक टूथपिक माचीसच्या बॉक्समध्ये बसवून घ्या. त्यानंतर तांब्याच्या तारेचे साधारणपणे 12 ते 15 वेढे देऊन ABCD कॉईल तयार करा आणि ही तयार झालेली कॉईल 2 चुंबकाच्या मध्यभागी अशा पद्धतीनं बसवून घ्या. त्यानंतर जेव्हा आपण विद्युतधारा सुरू करतो तेव्हा विद्युतधारा A कडून B कडे, B कडून C कडे आणि C कडून D कडे वाहते. त्यावेळेस उत्तर ध्रुवाकडून दक्षिण ध्रुवाकडे चुंबकीय क्षेत्र निर्माण होते आणि आपल्याला हे कुंडल फिरताना दिसते. तर प्रत्यक्षात आपण कृती करून पाहूया. अशा पद्धतीनं आपण या प्रयोगाच्या साहाय्यानं विद्युत चलित्राचे कार्य कशा प्रकारे चालते
फॉर जॉईनिंग. आणि आम्हाला अशी आशा आहे की तुम्हाला सगळे सायन्सचे प्रोग्राम्स आवडले असतील. आणि लेट्स मीट फॉर द पब्लिक टॉक बाय स्वरा Ravindranath at 6 o'clock. Meet you. Bye.